that's something that is clear. It should handle multiple modalities, so you can understand the sound and the video and everything, right? And there may be other properties that our models should have. I'm not listing here. Maybe I don't know which ones they are. Also, another question is what tasks should we be solving? And there's many obvious candidates like object recognition. That must be necessary to understand video. 3D reconstruction to understand the structure of scenes. Action recognition, so we can assign certain actions to certain characters. Obviously, low-level things like tracking, correspondence, flow. And there may be many other tasks that are very important and we still don't know about it, or I'm not listing here. So, the way I'm going to structure this talk is I'll go through some of the work we've done at DeepMind in the area of video over the last few years, and then I'll kind of like make it go through or go to end up in a recent paper we've done, which is about a new model called the perceiver. So I'll connect everything we've done to this new model afterwards. So first I'll talk about reactive and fast. And we had a paper in ECCV 18 that tried to deal with this problem. So let's say you have a video of a person playing basketball and you want to track their joints. So obviously you need to have a very fast system because the person can move very quickly, and the model needs to be very responsive in order not to have a delay between the predictions and the motion of the player. So the obvious candidate system for doing something like this is just throw a deep res net at every frame and predict a heat map for all the various key points for every frame. But this is obviously not ideal because this is expensive. So it's a lot of computation for every frame, whereas the frames barely change at high frame rates, like 25 frames per second. And yeah, so there'll be high latency. So you need a very fast computer to do this at this frame rate. There may be some other utilization of hardware resources if you have parallel processors, because these models are very sequential and need to be computed layer by layer, and they'll have high memory requirements as well. So our idea in this 2018 paper is very simple and is as follows. So let's consider the basic model I just described on the left, and let's say that the horizontal axis shows time. So there's multiple images, image 0, image 1, image 2, coming over time. And the vertical axis is showing the layers. So in this case, it's a neural network with 4 layers. So a very simple example. So then the image 0 gets converted into prediction 0, y0. Image 1 gets converted into prediction 1, and so on. So what we proposed was instead to change basically the arrows of the computation such that the prediction for image 0 only gets done a few frames later, like with a fixed offset, like 3 in this case. So it goes from I0 to Y3. But Y3 is actually trying to predict Y3. So the trick to do this is that the model needs to predict it. So at frame 0, it needs to predict what output will be at frame 3, basically. So, and this should be possible to do by learning a predictive model. Like feature prediction is something that is quite common in computer vision. And if you can do this, if you can do this prediction, then you can run all the layers in parallel. And if you have parallel resources, then all of them will be very reactive. So latency will be very low. So, and we've shown that this can be done, and we have some visualization here of pose estimation with very low latency, using this predictive behavior to achieve this. So afterwards, we followed up this line of work into not just reactive and fast, but also to have models that can process and integrate information online. So for online learning in video, and that can do it over a long time period. So that can scale to very long videos. And this is called the sideways model that we published last year first in CVPR. This is work led by Mateusz at DeepMind. And it expands the idea of these massively parallel video models, not just from inference, but also inference and training. So with backprop, it changes backprop to be parallel and very efficient. So again, I'm showing here one of those diagrams. Now I'm showing time on the horizontal axis, so actual computation time. And on the vertical axis, I'm showing network depth. So if you have an input frame X at T1 that goes through the network. As it goes through the layers, time never stops, time keeps flowing, and you get progressively deeper in the network, and you get a prediction Y T1. You compute a loss, and then you can compute gradients, and then you can update the weights of the network at the end. So obviously, time never stops, and this the deeper the network is, the longer it takes before you can update your weights. Now, in Sideways, what we do is we expand the massive parallel model that is shown here on the left from inference to training. And what it does now is that both computing activations and computing gradients and updating weights can be done all in parallel. And the main trick to do this is that instead of doing correct backprop where the activations from frame 1 are used to update or to compute the gradients later on for frame 1, we use whatever activations we have at that particular point in time, which may be slightly noisy and slightly different from the original activations, but since the video is usually smooth, they're good enough. And that way, basically you can update the weights of the network without having to do a full forward and backward pass for each frame. And basically, we don't need to buffer activations. We don't need to store activations. We can, every frame just compute all activations in parallel for all the layers and update all the weights also in parallel. So this allows to scale up to much longer videos and training on longer videos. And this CVPR, we did one extension of Sideways that allows for better modeling of time by introducing skip connections between frames, shown here at the bottom. So basically, the previous model was taking frames in independently on the forward pass. Now, both on the forward pass and on the backward pass, so the multiple frames get combined through skip connections. And yeah, we can compare that, or we report on the large-scale experiments on kinetics that the latency of this depth parallel model is lower than using, say, batch parallelism, and that we can train on much longer videos. So here we show that on the right that we can use a 40 batch size of 40 videos of 10 seconds compared to a single video using regular backprop when using skip Sideways. So instead of a larger batch, you could also use like a 40 times longer video. All right, so that's it for the reactive, fast, and training over long videos part. Now I'll talk a little bit about accurate and robust models for arbitrary tasks and about action recognition. So we did quite a bit of work at DeepMind on this part. Namely, we introduced the kinetics dataset, which is now quite popular. It's a bit like ImageNet, but in the video domain, and also similar to ECF101, but like a much larger scale. So we have classes like giving or receiving a worth, lawnmower racing, hopscotch, pushing car, and another 600 plus classes. And these are composed of videos from YouTube, all 10 seconds long, and each video has a single label. So it's a simple classification problem. And so this was quite a successful benchmark, and many very interesting architectures and powerful architectures have been benchmarked there, starting from 2017, where we had I3D. There's also S3D, R2 plus 1D, non-local models, many other ConvNets over the years. And this year, the transformers started doing very well on this benchmark, and models like Timesformer and Vivid have shown great performance in kinetics. And we kept improving the data set over the years. So every year there was basically a short paper about kinetics, increasing the number of classes, the number of examples. But in the meanwhile, we thought we should move to more complex tasks, namely spatial-temporal action localization. And we did this merger with AVA, which is the reference data set in that area. So the AVA looks a bit like this. So there's a video, and then there's a bounding box around each person, and there's a number of atomic actions associated with each person. So one issue with AVA was that there was very few videos, even though they have a tremendous number of annotations because they annotate densely every second, every people. They only have 430 videos. So what we did was to go and get 240,000 kinetics videos and annotate one frame in each, and merge them together. So, and this became AVA Kinetics. which has a much more diverse set of videos. So you can see that now these videos have both the AVA annotations here on the left and also the kinetics classes. In this case, it's alligator wrestling. So then we did also a bit of work on AVA. So the original AVA model used flow and RGB, like two modalities using i3D, and it used like a proposal mechanism using a ResNet, and that was the original baseline. So we did some improvement of that initial model. We basically simplified and added a bit of data augmentation and a few more tricks, and we did very well on the first AVA challenge. So we basically tied for first that year. So that was work led by Rohit, who was an intern at the time. Later on, Rohit improved this model and basically added a transformer head to the model instead of just a simple linear one. And this was a paper in CVPR 2019. And one interesting thing about this model is that it produced very interpretable heat maps. So when trying to recognize the actions for the person in the middle, shown here with a box, the model attends to faces, hands of the people around it, and also some objects, which we found quite interesting. So it's doing something that makes sense, right? It's not just like a full heat map over the whole video. It's quite meaningful parts that get selected. So this is like the action recognition work we did mainly past few years. Then we also tried the different types of tasks, namely one that has to do with disentangling imaging factors of variation. So here I'm referring more explicitly to reflections. So for example, if you have a robot that goes on the street and sees this puddle in the middle of the road, it shouldn't confuse it with real trees, right? So it does look like trees, but it's just a reflection. So it should safely ignore it and move on, rather than stop there with fear of hitting a tree. So this is an important problem for, say, self-driving cars and so on. And so there we proposed a model that is basically an encoder-decoder model with 3D confidence for both parts. We use i3D in this case. And what we do is we combine random videos from kinetics. We blend them together to make them look like they have some reflections in them. And then we just train the model on millions and millions and millions of such pairs of videos blended together to separate them back. So it's as simple as that. And this was a paper led by JB, also in CVPR 19. And we observed that it actually transferred to real settings in some cases. For example, here there's a person driving and there's some trees, and you see that there's some reflection on the windshield, and the model correctly separates this video into two layers, one just showing the person and the other one showing the sky and the trees, and with reasonable accuracy. Then we also did an extension of this to multiple modalities. So this was the controllable attention for structured layered video decomposition paper, also led by JB. So here the difference is, compared to the visual centrifuge, is that instead of just inputting a video, it also inputs the corresponding audio from one of the original videos. So one input is the blended video, the other input is the audio from just one of the videos. And the model is trained to produce just one of the original videos corresponding to that audio. It's a bit like you're looking at something through the window and you hear some noise corresponding to one of the layers, so you can attend to just the layer that corresponds to that noise. And again, there was a bit of architecture design necessary for this, because you have the audio and you have the video, so you need to merge them together somehow. And we did some pooling and some sampling and the usual tricks there to combine the signals before the decoder that produces the corresponding layer corresponding to the audio. And here's an example of the model operating.
Get it, girl.
Let me play it again. So,
get it, girl.
So you can see that there are these two videos, one of a drummer, one of a girl. They get blended together, but the model is given the audio from the little girl, and is able to separate the correct layer corresponding to that little girl. I'll just play it again.
Get it, girl.
Can you hear this correctly? Is it all fine? Yes.
Yes, I believe we
Yeah,
can.
we
Yeah.
can.
Good.
Yeah.
Just a little bit of feedback before I end up discovering 1 hour later that nobody could listen to me. Thanks. Okay, so other tasks that we could be solving. So we also did a bit of work on video grounded and supervised translation from with videos. So the problem there was, let's say you have videos, some of them from YouTube, some of them in English. For example, one where there's someone saying, "I need to mix the eggs with the flour." So we have a speech-to-text model that saves those words, and those words are associated with video, typically instructional ones. And then we have also videos showing roughly the same things, but in a different language. So with French people breaking some eggs. Now, can we learn to translate automatically the words from French to English and vice versa by just watching lots of videos where people are handling eggs? So that's kind of the problem we dealt with here. And it's done in a supervised way. So there's no paired data. We just have loads of videos showing common objects in different languages, and they're not really like paired together. And this is an interesting problem because it's related to the language acquisition problem. So when you're a child and you don't know any words, you may already have some internal concepts. It's called that mentalese. And when you hear other people talking while doing things, it's kind of like a translation problem between the actual words of say the parents and the internal concepts of the child. And yeah, we also proposed a model there. Basically, there's like a shared video encoder, an i3D model that is shared for all the videos. And then we have dedicated language models for the various languages, for English and French, say. And then basically we use a contrastive loss that pulls together the matching videos and text and pulls apart non-matching videos and text. And because the video encoder is shared for all the videos, the words corresponding to those videos in the various languages get to be pulled together. And yeah, we did some retrieval study where we see that a good percentage of visual words get correctly translated in this setting. Yeah, so I was mostly talking about all this previous work in part to advertise it, but also to make the point that a lot of the work and research that we do in computer vision is messing up with architectures, right? So every time we have a different set of modalities or a different task, we need to like do a bunch of adjustments to our models such that things work and to get good results. So here's just a short compilation of some of the models I've talked about in the first few minutes of the talk. And it's not just us, obviously. So if you look in the literature, there's great papers dealing with multimodality. For example, I'm listing here some work from our lab, from Relly and Andrew. Also some work from Facebook. And you can see that it's complex. So you need to have a model for each modality, and then you need to have some way to fuse them. It can be early fusion, can be mid fusion, can be late fusion. There's many tricks that people do and many, kind of like architectural patterns that are used to do this. And every time people need to try them all and see what works best. And it's not just in vision plus audio. There's also, for example, in self-driving cars, there's very interesting papers that combine lidar with images, and these models can get quite sophisticated. So, for example, in this particular paper, which is quite popular, there are 3 different inputs. So the lidar gets projected to 2 different views, and then there's a fusion of the lidar with the image in the middle of the network, and then there's some tricks to get and some parts of the architecture that we deal with generating boxes and classification. So again, a lot of customization to each particular part of so each particular application and modality sets. So one more example, a very interesting model called GPV1 from Urbana-Champaign. Again, a very powerful model, but again, a very complex one as well. So you have a vision part, you have the language part, cross-model module, language decoder, vision decoder. There's quite a bit of machinery that is needed to put all of this together. So these multimodal architectures are typically quite complex, and they vary a lot depending on tasks and the sets of input modalities. And so this brings me to the main topic for the rest of my talk, which is about this project we have at DeepMind to vastly simplify perceptual modules called the perceiver. And the idea of what we want to do is have a model that is a black box that just receives an input matrix. It can be anything, can be various modalities stacked together. It could be text, video, audio, lidar, you name it. And it also receives a query matrix asking the perceiver to generate a certain type of outputs that may depend on the task you're interested. And then the perceiver just generates the corresponding output matrix. And this potentially could be used for any of the tasks I talked so far in this talk, and also for any combination of modalities. So, and we have done something that looks like this, but it's under review right now and it's not out yet. So I'm going to talk about the first iteration towards this goal, which it uses a fixed task. It can handle any combination of modalities, but produces a fixed task, which is typically classification. So this is what I'm going to talk for the rest of my talk. And this is an ICML paper. So I don't know if there's any questions so far before I start talking about the perceiver. I'm not really tracking how the question process works.
Actually, if anybody has any question, can raise his or her hand in the Zoom meeting, and on YouTube channel, people can just write their question in the chat section.
Okay, so I'm not following the YouTube channel, but if there's a
question, I'm just taking care of that, and if anybody asks questions, then I will ping you.
Cool. Thanks a lot. Yeah. Okay, so let me tell you about the perceiver. So if you look at the real world and the type of data that is out there, quite a lot of it is very high dimensional. So things like vision, obviously, we know it's very high dimensional, and some animals have many eyes, like 8 eyes, some have 2 eyes, but a lot of inputs coming in. Things like audio can be high dimensional, even like proprioception can be high dimensional if you consider like a human body where we feel all our tendons, all our skin, everything, touch sensing, text data. There are lots of high dimensional structures out there for us to sense. And the goal of the perceiver project is to develop an architecture that can handle them all without any change to the architecture itself. So the advantage of the perceiver is that it's not only domain agnostic, but it also decouples the model depth from the input size. So you can build very deep models independently of the resolution of your input, even if it's like very large, doesn't matter. So it's the same in terms of how deep of a model you can build. So obviously there's this model called the ConvNet, which is quite dominant still in vision. And it's very scalable. So that's the great thing about ConvNets. They can scale to hundreds of thousands of inputs. So one problem with ConvNets is that they bake in very domain-specific structures. For example, ConvNet for images will bake in a 2D grid structure throughout its network, making it unsuitable for 3D signals or 1D signal. And it also makes it hard to combine different signals that have different spatial structure. For example, say audio and images or video. On the other hand, the other behemoth architecture, the transformer, it makes very few domain assumptions, so it's very easy to combine different signals. But they, as we all know, they scale poorly with the input side. So that's the relative strengths of these two models. And so for those of you who are not familiar with why the transformers and in particular self-attention scales well, I'll just cover that first. So let's say we have an input byte array, and I call it the byte array within this perceiver nomenclature, because the inputs are domain agnostic. They can be anything. They're just like basically bytes. Right, so and this byte array is M by C. So there's M inputs. Each of them has a fixed dimensionality of C. And the first operation in self-attention is to compute queries, keys, and values. So those scale linearly with the number of inputs. It's just like a convolution, basically. And yeah, of course, M can be very big. For images, it can be 50,000 for image, let's say. And then the second step, that's where things get expensive. So computing the attention map, basically. So here it's a square matrix in the number of inputs. So it's M squared. So again, going back to the example of images, if you have 50,000 pixels, you can't typically build a square matrix with that size. And you can't even probably do a shallow network on that, much less a deep network. And then the final step is to compute the features, and that's another quadratic step. It needs to do a matrix multiply with this big attention matrix. So the way we go about fixing this quadratic scaling is to introduce a cross attention that is linear in the input size instead of just doing this self-attention. This is how it looks like. So instead of mapping queries, keys, and values all to the same size, we have a mapping from a latent array to the queries that is much tinier. So instead of having m inputs, it has or m vectors, it has n vectors, where n is typically much lower than m. Let's say if you have m equal 50,000 pixels, then n is typically going to be, say, 512 or 1,000. So much smaller. And so both of these operations, mapping the latent array and mapping the byte array to queries, keys, and values, they're both linear in the number of units. Now, so having this latent array, when you compute the tension between the latent array and the byte array, now you get a smaller matrix that is n by m instead of being m squared. And since that n is small, then this is manageable. And then finally, instead of the final operation being quadratic, it's again OMN because of this latent array that we created. So basically, at that point, the output latent is independent of the input size, and it's tiny, so we can build arbitrarily deep networks. So let's say if instead of the 50,000, now we have just 1,000. Now we can stack together many self-attention layers on that input, which is just 1,000 dimensions. So we can build very deep networks now. So an overview of the Hall perceiver model. So we have this latent array that is initialized randomly and is learned. It's a bit like an RNN initial state, and we have the byte array. We have this cross attention, which is like a reading mechanism. It's like the model is reading the inputs. That is OMN. And then we have a stack of transformers that can be very deep because it operates on this n squared, so on n inputs rather than m. So it operates on the latent array, it's just making deeper features out of the random initialization of the latent array. And then we optionally iterate this process. So if you have a very small latent array, we found it beneficial to go back to the pixels or to the inputs and read again and improve the content of the latent array, informed by the previous read of the inputs. And for relatively small data sets like ImageNet, we found it beneficial to share weights between the repeats, or the model can have many parameters. And finally, at the end of the model, we average the features and we project into logits as usual. So the model doesn't have any biases, or domain biases. It doesn't assume any grid structure for the inputs. It doesn't assume that there are patches. It's not really an image model, basically. It's a model for any type of data. But we can still put prior information about the domain into the training, not by changing the architecture, but by concatenating some encodings with the inputs. So for example, for ImageNet, instead of just feeding in RGB values, you can also put some position encoding, a bit like a NERF. So for example, Fourier feature encoding. That way, the model still receives the spatial information, It's just not baked in into the architecture. It's baked into the data. Yeah, so in terms of results on ImageNet, a ResNet 50 gets something like 77.6. A VIT model also gets around 77.9, at least the original one. So we also tried the transformer. So we can't, basic transformer, like a stack of transformers. For those, we can't really input very high resolution images. So the maximum we could do with decent training time was 64 by 64. And that's quite a bit worse than the ResNet 50 or the VIT models. You get just 57%. But with these tricks, this architecture I just described, so we can get as good or slightly better than ResNet 50 or VIT. So with a perceiver, when using 2D Fourier features concatenated with the RGB values. So in red, I'm showing the models that exploit patches or grid architecturally. And in blue, I'm showing the models that are very domain agnostic and don't assume any knowledge of patches or grid. So to show the power of not needing knowledge of patches and grid, we also have an experiment where we permuted the pixels with a fixed permutation. So we permute all the images in ImageNet always with the same permutation. And we tried it, the ResNet model, and it does much worse, of course, because now the locality assumptions it builds upon are violated. And the VIT model also is quite a bit worse, although significantly better than the ResNet. But this is like a mathematical fact that the transformer or perceiver, they don't change at all. Based on permutation, it's totally permutation invariant, so the results would be the same. We haven't even run this experiment because it's not worth it. And we also ran an additional experiment where we didn't even feed any type of positional information to the perceiver. So we didn't feed Fourier features of the position to the perceiver. Instead, we learned for every pixel positional encoding from scratch. And surprisingly, that does still quite decently at 70.9%. And this is like totally domain agnostic, so not even the inputs encode any spatial information. So the model learns about space fully from scratch. Of course, I mean, so there's still the augmentation. The augmentation still has some, still feeds in some priors about the domain. So we use standard augmentation in all cases. Okay, so another interesting thing to look at is to visualize the cross attention of the model. So so what I'm showing here is 9 attention maps out of 1,000. So there's 1,000 latent vectors. Each one attends to the inputs, and here I'm showing 9. And you can see it has this wavy pattern. So it attends to particular locations more than others. And it also attends to certain colors more than others. So this observation about the colors is because we're not overlaying the original image here with these heat maps. They're just heat maps. So if you can see the object, it's because there's some color dependency in the attention. And we're also showing here on the right now the attention maps for the model with the learned position encoding. They're quite different. And you can see that they're a bit noisier. I guess ImageNet is not big enough for the model to learn perfect positional encodings for 50,000 pixels. So it's kind of like pointy. But still, you can see that there's some color dependency and there's some spatial dependency in this case as well. And we used exactly the same models for ImageNet also for point cloud classification. And again, it outperforms models like ResNet for VIT with various patch sizes. And to use these models that are typically for images, what we did was to render images of the point clouds. Whereas for perceiver, we can just directly input the point clouds, similar to transformer, but we found that the perceiver did a bit better than transformer. And the final results are somewhat competitive with a specialized model that also does extra domain-specific augmentations and featurizations. And finally, and more relevant to this workshop, we also tried exactly the same model, but now on audio set, audio video classification. So the main difference from what we did in ImageNet is now we have multimodal positional encodings instead of just spatial positional encodings. Some more details about the experiments we did there. So we used 32 frame clips, and then independently, we basically split up the video into 32 frame clips, and then we average at the end. For the audio, we used either a spectrogram or we used raw audio. And for the video, in this case, we had to use patches because the model scales well up to a few 100,000 inputs, but not more. And you know, a video, even a 32 frame video at the standard resolution, can have millions of points beyond what the model can do. So we use these 2 by 8 by 8 patches. In total, the model had around 17,000 inputs. And so just explaining a little bit, how do we build the byte array, the input byte array for the perceiver in the case of multimodal data. So let's assume that we did this on pixels, and so every video sample would have 3 values for RGB. So let's assume that each input is a pixel. Then we would concatenate the Fourier encodings of the X, Y, and T positions, position, and form a little vector for each pixel. And then for audio, we would not have the X and Y, we would just have the T. So we would concatenate the audio value with the Fourier encoding of time. And now we have these 2 vectors, one for a pixel and one for a raw audio sample, and they're different size. So we need to do something about that because we need to fit in a matrix, and we need to form a matrix out of this data. So what we do there is we concatenate a modality encoding of different size, such that the end size of each vector is the same. So in this case, let's say that audio has 130 dimensions, then we're going to add a bigger modality embedding than to the video, such that in the end they have the same dimension. And so it's kind of like a padding, but a padding that also serves the role of informing the model about the nature of each input, if it's audio or if it's video, and so on. And so the results in audio set, again, the model is competitive with the state-of-the-art. So there's a couple of state-of-the-art models that came out last year, G-Blend and the Tension AV Fusion, and the perceiver model without any customization to this task. So the same model that worked well for point cloud classification and for ImageNet classification also does well in audio set and gets close to the state-of-the-art. And it's a single model. It's unlike these other models that have a branch for the video and a branch for the audio with specialized models for each. And in the case of G-Blend, they also have a specialized optimization scheme for dealing with multiple modalities. Whereas here, we didn't have to do much. We only did a bit of augmentation of the video and the audio in the sense of dropping them. So we would drop randomly with some probability either the video or the audio to force the model to learn both. So that helps a few percent. Yeah, so we can also visualize the attention maps for the video. So we did 2 iterations of cross attention, in this case for audio set. And you can see that the first cross attend, there's a bit of a funny spatial structure. Whereas in the second cross attend, it's much smoother. Another thing to note is that the first cross attend, there seems to be more of a spatial specialization, so that there's more dissimilarity between the various maps, because I guess the model is trying to look at different positions in time and space for each of them. Whereas in the second one, it's more uniform a little bit. So the model already probably has an idea of where the main objects are and is attending more to those. And I have some more examples for different videos. Here's a dancing video. Same type of visualization happens. The first one has this like a funny pointy structure, whereas the second one is a bit smoother and more uniform. So the resolution of these attention maps is 16 by 28 by 28 because we're using these 2 by 8 by 8 patches. So some more examples. Here it's a car. Again, you can look at you can see that certain cross attention maps focus on different areas. For example, this one doesn't care about the top too much. cares more about the center. This one more about the bottom. And there's some color dependency in some of them as well. Whereas the second crossed end is smoother and more focused on the card, possibly. Another example showing similar behavior. So these are very short clips. They're just 32 frames long, so 1.5 seconds. So I'm looping them here. And I think this is the final example I put in the slides. And yeah, same behavior as before. So earlier on, we had trained a higher resolution model. And so all the previous visualizations are from the same model that we have in the paper. But this one had a pretty funny structure. Let me show you. So basically what happens is that the last frame looks quite spatial, like the attention map, whereas all the previous frames look like space-time frequency detectors. So it's like looking for motion until the very last frame where it's more like about spatial content. And in this model, this was actually the norm. All of the attention maps would have this behavior of looking for just motion, and then at the very end, on the last frame, looking for content, which we found to be a very interesting strategy. Yeah, so I'm coming close to the end of my talk. In terms of conclusions, I have more questions than conclusions. So looking back to the 70s, there was this impetus in AI that kind of weighing down as we faced challenges, the community faced the challenges and difficulties of building AI. So what happened was that the field broke up into many different subfields like vision, NLP, robotics, and so on. Now there seems to be a lot of energy again in things like multimodality, putting audio, video, text together. Maybe it's time to re-aggregate back a little bit AI. So another conclusion or tendency I see is that there may be less architectural work in the horizon, hopefully, but more general ones. So instead of people building specialized architectures for all combinations of modalities and tasks, say semantic segmentation, detection, reconstruction, and whatnot, maybe there'll be a consolidation of work in a few architectures that can do many different tasks and many modalities. And I think if this happens, there'll be more time for doing brain computation and less need for GPU or TPU computation. So we have lots of talented researchers in the field that will have to do a lot of thinking about, namely, what are the important tasks or problems to work on in video. I think that's a very difficult problem that machines are not good at solving, and we humans have more of a chance. So I think that's we'll all spend a bit more time thinking about, for example, what are the right problems to work on. And going back to my running example of the Umbrella Academy, if maybe we can discover what are the right problems to work on such that we can understand, for example, possession by a spirit and the impact of that, and the fact that the actions that someone that is possessed by a spirit are not of them, but of the person possessing them, and so on. This is just an example for complex computation we do as humans, and that machines, this seems very hard for machines. And that concludes my talk. I'll just put a little video also from Umbrella Academy here. In case there's any questions, this is the time. Thank you.
Okay, thank you for your great talk.
Thanks.
So, yeah, we have some questions from the YouTube channel. Yasser has asked that, can you please compare perceiver versus VIT on flops, input type, positional encoding, number of parameters, etc.?
Yeah, so let me see. So I don't remember how many parameters VIT has, but the ImageNet model we put in the paper has 40 million parameters, the perceiver. So in terms of flops, it's way more expensive, maybe an order of magnitude more expensive. So that's not our selling point, clearly. So our selling point is just domain agnosticity and scalability. So we don't need to do a lot of processing on the inputs. We can just feed them in, and yeah, I mean, new models like this tend to be more expensive often, and we hope computation will keep up. And yeah, we're also looking at ways to make the model more efficient.
Great. And let's see. Okay. Any other questions from Zoom or okay? We don't have any questions yet from channel YouTube channel. Okay. There is someone raising hand. Okay, you can unmute yourself and ask your question.
Yeah, so thank you for a great talk, Zhao. You had this visual recognition with the dog example, and then you basically scrambled it. It was a fixed permutation as far as I understood, and it didn't seem to harm too much the performance of your perceiver system. On the other hand, you mentioned brain computation and so on. So the brain does not seem to be doing that, right? The retinotopy, the fact that there is a particular spatial organization is nicely kept intact in subsequent layers of the brain. So it seems that in biology, the system really does try to go for dedicated type of analysis for specific sensor types, rather than trying to be generic and agnostic, as you call it.
Thanks, Luke. That's a great question. So thanks for asking it. So I guess here we're trying to model not just the brain, but a bit evolution. So evolution finds a way to deal with any kind of sensor configuration by adapting the brains of the animals through time and through multiple lives, right? So maybe that's closer to what we're trying to do. But in a sense, the retina and the visual processing system, it may be, as you're saying, from some phase on, from some depth on, but for example, the retina is not totally like an image, right? So there's like an area of for high resolution, the fovea, and there's an area of low resolution, and then these get converted into like a highly scrambled fibers that go through the optic nerve, and then I guess they may get unscrambled back later on, but I don't know if it's that clear that it's like an image in the brain, a very array-like image in the brain. Plus, it's also reversed, for example, right? So the brain needs to like.
But that is not so important, I think. But there is really an image in the brain, and people have been showing that you can see almost the image as in the theater if you look at the outer cortex. So this is very nicely kept spatial organization, and I was wondering whether in the end it is then not better to use dedicated channels once you decide on the sensor that you want to use.
Yeah, I mean, definitely. I mean, specialized is always better than general. I mean, we see that for example, in computers, right? So if you have a CPU that is very general, it's not going to be as fast as, say, a TPU when you have a particular domain in mind. But on the other hand, there's advantages to CPUs as well, in that you can do arbitrary computation, and when you find something that you're happy with, then you can specialize it back.
Mm-hmm. Okay, thank you.
Thank you.
Okay. See if there's any other questions. So it seems that we don't have any other questions. Yeah. Thank you so much.
Thank you for the invitation again.
Sure. And yeah.
Bye.
Bye.
It seems like our next speaker has problems getting in, right?
Yeah.
So yeah, let's.
So, Essen, maybe we can wait for like 10 minutes.
Yeah,
like
she's sending emails right now. You see, do you see the emails? Yeah.
I didn't know.
Yeah, maybe we can wait for her and then.
So she's struggling with, she's unable to log in for some reason, because of some reasons.
to log into the
Have
Zoom?
like
So she said I cannot log in. I used the link in the username and password. So I don't know how can we fix that now.
let's do 5 minutes of 5 or 10 minutes of like entr'actes in between the talks, and then help her get in.
Okay.
So I also had this issue, and what I did was I had to register an account with Zoom, which I hadn't done before, and then using the registered account, then it was okay. Also,
Okay.
sent me the link, the meeting link, like the meeting IP. That was easier as well.
So okay, sorry. So you have to use a registered account in order to log in. Is that what you're saying?
Yes, so that's what the bond system was saying.
Okay, I think so it's because of the restrictions that we have posed. Something to learn. Okay, I will just try to write her.
Okay, let's check if
By any chance, do we have a possibility to update that rule something? I don't know if it is possible, and if would that apply right away? So somebody seems posted that needs a student email address or company email address. I think it's because of the restrictions.
yeah, she should have a registered account to log into Zoom.
Actually, it seems that we have Dima in. Do we want to switch presentations?
I would propose that let's wait for a few minutes. What if she's trying? I dropped her an email.
Okay.
Just it would look really weird.
Hello, Dima.
Hello. I joined and I found silence. I thought my speakers are not working.
No,
It's a chit chat session, you know.
yeah, we are waiting for Cordelia to get on. She has problems getting on Zoom. Yeah.
Just that, Mohsin, could you apply that? Could you check the restrictions that we have applied for students and?
Actually, the problem is that I check if I can change it, but since the meeting is running, it doesn't allow me to change
Okay.
its settings here. Even using a Gmail account or something, she can log in. It's not really needed to be like a university or company account. Yeah.
It's weird. So she's asking which registered Zoom account. I don't have one. Usually I just click and the link works.
Because she has a Gmail account, or like, because she can even log in with Google.
Okay. Just give me 2 minutes and then we can take a look. So Joe, what do you mean? Like you had to sign up to 10 minutes to get the email?
So I had to sign up for a Zoom account. I didn't have one. So I pressed the button sign up, and then they sent an email, but it took a few minutes to receive it. And then I put the password, all that stuff. It takes a few minutes to fill it up.
Okay, we can, well, it's weird. I'm also not aware of these issues, So
I think Vivek and Mohsen, if Dima's ready, we can probably switch Cordelia and Dima, if that's an option.
yeah, I just dropped her an email. I just would like to give another 2 minutes, and then because if she shows up after 10 minutes, I just think it is gonna be quite awkward. Just like let her reply this email, and then we can just switch.
Okay.
Maybe I can write her. Switch. Yes, she's here. Fine. Great. Hi, Cordelia. Thanks for joining, and sorry for this issue, Yes, she's here.
I think she's connecting audio now.
Okay.
She's connected.
Hi,
Yeah,
Cordelia.
now it worked out. I had to register for Zoom, actually. It's not convenient.
Yes, it's weird. It's very weird. But thanks for joining. It was something to learn from.
Yeah, usually I just had another meeting with Zoom, and usually I don't need to have an account. Anyway, let's start. It doesn't matter. I'm here.
Yeah, wonderful. Awesome.
Thanks.
Okay, our next speaker is here. Thanks her for joining us, and sorry for the inconvenience. So Cordelia, the stage is yours.
All right, let me share the screen. Okay, can you see the slides?
Yeah.
Yes, perfectly.
All right, so hello everybody. Today I'm going to talk about large-scale learning from multimodal videos. Today, there's a lot of video data available online, and it's growing daily. There's, for example, all the TV channels are recorded since the 60s. There are 30,000 hours of video uploaded every hour, and there are 770 million surveillance cameras worldwide. This is a lot of data which we would like to be able to analyze and access to. What are examples of automatic video understanding? Here are two examples of action classification. On the left, birthday party, and on the right, grooming an animal. Both these examples are part of the TrackVid multimedia event detection task. Another task is text to video retrieval. Given a query such as children playing football, you would like to find the corresponding video clips which represent children playing football. Below a few examples. In the long term, we would also like to be able to obtain a complete description of a video. For example, here, as the head waiter takes them to the table, they pass by the piano and the woman looks at Sam, etc. And so why do we want to use a multimodal video representation? If we want to precisely understand the video content, we have to access to all modalities simultaneously. If we look at the example on the left, we can see that the man is serving food to the woman. However, only if we have access to audio, and here the question, is this Indian? Can we infer that the man is serving Indian food to the woman? Furthermore, the large amount of multimodal video representation, video data can be used for large-scale cross-modal supervision. For many videos, for example, the how-to videos, people actually say what they're doing, and so we can use the corresponding speech transcribed as RSR as a weakly supervised signal. In the following, I'll start by presenting our video BERT approach. It learns from the large amount of videos available online, which come together as speech transcribed by ASR. ASR stands for automatic speech recognition. Here is an example, but in the meantime, you're just kind of moving around your cake board. So basically, you can see that people are describing what kind of actions they're doing. We extend the BERT model to learn the correspondence between video and the speech transcribed by ISR. Furthermore, we show that we can learn from large-scale data, for example, from cooking and instruction videos. First, a small overview over the BERT model. The BERT model is a bidirectional encoder representation from transformers. We can see on the left an example for pre-training. Given one or two sentences as input, it can mask out certain words and predict those masked out words. This allows us to learn the correspondence and the context for these masked out words. Once we have completed this pre-training, we can then use the model and fine-tune it to specific downstream tasks. The BERT model is based on a transformer. What are transformers? Transformer models are great for processing sequences, such as text, but also images and videos can be expressed as sequences. The model relies on the self-attention between all tokens of a sequence. You can see here that these are the input tokens on the bottom, and then we model all the correlations in each of the layers until the top layer. So basically each token looks at all the other tokens, and so we can really learn what are the interactions, for example, between the words in a sentence. Our video BERT model extends the BERT model by taking as input the text obtained by ASR but also the video features, which are 3D convolutional features for 1.5 second time intervals. So we have as input a bunch of these video features, which describes the video clip which corresponds to the text. This gives us a multimodal transformer, and we do masked language modeling as in BERT for the language tokens, but also for the video tokens. The video is represented with 3D convolutions for short 1.5 second time intervals, and clustering and the cluster centers can be used for masking. In more detail, the 3D convolutions describe the video clips, the short video clips with the chunks of 1.5 seconds in space and time. And the clustering allows us to tokenize the features obtained with the description. So we have the video, full video clip, which corresponds to the language, is chunked into small clips of 1.5 seconds. For each of them, we extract a feature vector based on 3D convolutions, and then we cluster them and use the cluster centers as input to the transformer. We train our video BERT model on 300,000 cooking videos. Cooking videos, such as the example on the right, come with speech which describes the content of the video. Keep rolling tight and squeeze the air out to its side here in this example. Once we have this model trained on this large amount of data, we can then use it for zero-shot prediction on previously unseen videos. Here, for example, the two examples on the right, for which we predict correctly the verb make and the noun pizza. If we now look at the quantitative results, the table on the left compares a supervised approach trained on the UQ2 dataset for training and tested on the test split to our video BERT model, which was trained on a large amount of unsupervised data. You can see that the performance is on par. So you can see that the video BERT model learns the video language correspondence, and it's close to fully supervised accuracy. The table on the right shows the impact of the training size. You can see that the larger the amount of videos we use for training, the better the performance. And we can see that it's not yet saturated, so we can expect that using more data further improves the performance. You can also see that by fine-tuning our model on the downstream task, here captioning for cooking videos on UQ2, we can also outperform the performance and shows that this pre-training helps. However, if we look at another downstream task, which is action anticipation on egocentric cooking videos, we can actually see that video BERT is significantly worse than the supervised approach. And why is this the case? It's the case because actually for this task of video anticipation or action anticipation, the clustering approach is not fine-grained enough. If you look at a few examples of clips and the corresponding centroids, we can see that the centroids don't represent the data well in all cases. And this fine-grained classification is important for action prediction. We have then hence revisited the training objective of video BERT. Instead of doing the clustering, we now mask the features which are not clustered and use noise contrastive estimation to predict the corresponding feature which has been masked out. This is for visual information only, and to combine the visual and the text information we have on top of the BERT model and the visual transformer, the cross-modal transformer, and we then optimize the cost for the masking of the words, the masking of the visual tokens, and the alignment between video and text. We can now evaluate this model on action prediction for different data sets. Different state-of-the-art data sets are 50 salads, breakfast, and the ActivityNet dataset. Here we pre-train our model on how to 1 million and the how to 1 million dataset, and then fine-tune it. The table below shows results. The first column for breakfasts, first one for average pooling. So you can see if we make the window before the window which we use for prediction larger, you can see that average pooling actually doesn't change. Basically, we just pull the features, we have the average, and the longer we make the videos, it won't really change the average descriptor. If we use an LSTM model on top of the same S3D features, we can see that the performance improves slightly. If we now use our CPT transformer model, we can see that there is a significant increase with respect to the length of the video, and it outperforms the other approaches. You can see that we obtain similar results for salads. Here, actually, the performance of average pooling even goes down. So if the window is too long, average pooling just smears out the features. And again, we can see that our approach outperforms LSTMs. So we can see here that the transformer models long-range temporal dependencies for video clips. If you look at the parameters of our visual transformer, we compare here the number of layers and the number of attention heads. The table on the left shows that best results are obtained for a shallow transformer with only 2 layers. 4 layers are kind of equivalent, and after that the performance drops. And the table on the right evaluates the performance with respect to the number of attention heads. We can see here that 4 attention heads obtain the best performance. So the best results are obtained for 2 layers and 4 attention heads. This is much smaller than what people use for language. So what is a possible explanation? Possible explanation is that here we have the continuous pre-trained features, which are a much stronger signal than the features, the language features, which are just the individual tokens. We've also looked at the impact of the pre-training size. You can see that again, if we use, so this is the size, the percentage of the how to 1 million videos which we use for pre-training. If we use more data for pre-training, the performance improves. As before, what's also interesting is if we add a cross-modal loss, we can further improve the performance. So if you look, for example, dataset 100%, no cross-modal loss, this means we pre-train on the visual part only. And then if we add, in addition, the language for pre-training, we'll see that the performance improves. So we can observe here again that more data helps, and the cross-modal objective also helps to improve the performance. We have seen that VideoBird and the extension CBT allow to model jointly video and text. It can be used for stereotype prediction and pre-training. It allows to model long-term temporal dependencies and the dependency between video features and text. However, it's restricted to instruction and cooking videos where the speech matches mostly the video. To avoid this, we have looked into a way of doing cross-modal supervision, the approach speech to action, where we can actually generalize to any kind of movies. Here, we use the speech for action supervision. As I said before, the speech is often unrelated to the visual content in the general movies, which wasn't the case for the cooking videos, because often people speak about actions in the past, actions that will happen in the future, or they talk about something which is completely unrelated to the actions they're performing. And many atomic actions like sit, stand, etc. occur frequently with all kinds of speech segments. Our approach here, which works for general movies, learns when the speech is indicative of an action and what action it is likely to be. So here, for example, we have, hello, yes, operator, I accept the charges. This speech is clearly representative of the action answering phone. So how do we do our cross-modal supervision? We take a corpus of movie screenplays to train our speech-to-action classifier. This corpus has speech, which is the input to the action classifier. It has scene descriptions, and from these scene descriptions, we can obtain action labels. So here, for example, an agent hands him the phone. This is a clear indication of answering phone. So now what we have is we have pairs of speech and corresponding action labels. We can train a speech-to-action classifier, and we can then use the speech-to-action classifier to mine from a large set of movies corresponding action labels. In more detail, movie screenplays, as I have said before, contain both speech and scene descriptions with actions. We can use the verbs in the scene description to determine the action. We then have the training data, which is our speech action pairs mined from the movie screen scripts. And we can then encode the speech with the BERT model and train on top of this a speech to action classifier. So now we have a given speech. We can train this classifier and predict an action label corresponding to the speech. Here are a few examples. The class phone, corresponding speech which occurs often is hello. May I have the number? Honey, I asked you not to call. He's not answering the phone. Hello, it's me. The label dance. Come on, I'll take a break and we'll all dance. Ladies and gentlemen, the first dance. I don't feel like dancing. Want to dance? She's a beautiful dancer, and so forth. We can now mine data from unlabeled movie clips. We have a large amount of movies, and we can now apply the speech to action classifier to these closed captions of the movies. We take the movie, transcribe the speech with ASR, and then chunk it into sentences, and then feed these sentences into the speech to action classifier. And obviously at this stage, the screenplays are no longer needed. So we have really performed cross-modal supervision. We take screenplays to learn this classifier, speech to action classifier, and then apply them large amount of movies. Obviously, this is not perfect, but this gives us video clips with weak labels for the different actions. And here, a few clips mined for run. You can see the corresponding speech, and you can see the video clips. You can see that in these examples, people are running. So these are correctly retrieved clips. Other examples for phoning. So again, you can see here that people are phoning in all of the clips. And then here you can see clips for hit. You can actually see that the example on the bottom left is incorrect. So basically, backhand, snap down, round off, reach into the back. So if we just look at the speech, it's plausible that this is hitting. So this is an incorrect example. And then obviously if you use these examples, you have to take into account they're not all correct, but this was already the case for our cooking and instruction videos. Another example, clips mined for drive. You can see that in most examples they drive. And then if you look at the top right example, he made a U-turn on an empty street. This is actually not driving, but it's police officers discussing some infringement of the traffic laws. So here actually it is incorrect, but if you look at the speech only, the most probable prediction would be that somebody is actually driving. If you look at the quantitative results, here we take the AVA data set where we have 1.6 million labels for 80 atomic actions. Data set is very long-tailed, because basically here we have just annotated a set of movies, but some of the actions don't have many examples. And so our approach for mining examples for these rare actions shows that we can mine 2 orders of magnitude more examples for the rare and mid classes. You can see this here, that for some of the classes in training data, in blue, the mined examples with speech to action. You can actually see that we are able to mine significantly more data for some of the actions. And then if we look at the results on the AWA data set, the top row shows the results for fully supervised. The next row shows if we just use keywords in the speech to mine clips for training. The next one shows results if we use just our mine clips, so it's zero shot, we just use our cross-modal approach for mining and no annotations. You can see that in some cases, actually, this zero-shot approach significantly outperforms the training on the fully supervised data. For example, for driving, for phoning, it improves. For kissing, it goes down by a bit. And then in the bottom line, you can show that if we combine the mined information with the supervised data, we improve in all cases over the full supervision. And you can see here for 8 out of 14 classes, fully supervised is outperformed by zero-shot learning, and fine-tuning improves the performance for all classes. And finally, here we can see that we can also mine clips for more abstract actions, such as counting and following. We can see that this wiki-supervised learning can exploit a large amount of data available online. It relies on the correlation between multiple modalities, video, and language. Open issues is how to scale it to general noisy data and how to balance between different data sources and objectives. You have on one hand all the movies where it's relatively hard to directly correlate the speech and the visual content. On the other hand, we have web images and web videos where there is a strong correlation, and then the instruction video where there is a very strong correlation, because in many cases people actually say what they're doing. And in the final part of my talk, I'll introduce a multimodal video transformer. The first step is to design a video vision transformer. The idea here is to extend the video transformer width, which was designed for static images, to videos. So here, instead of modeling using a transformer to model the relations between video features or between video and language features, what we do here is we model directly, we use a transformer to model directly the relation between image patches or patches and tubelets in a video. And for video, it's important to design factorized variances to be able to handle a large number of tokens more efficiently. The vision transformer vid, what it does, it splits the image into small patches, then it flattens out these patches and uses a linear projection to project the patches into tokens. It uses a position embedding to order these tokens, because the transformer doesn't take into account any ordering information per se, and then has an MLP head on top of the class token to predict the classes. Okay, this is the video transformer. So how to extend this to videos? The first idea is to just consider the video as a big image and extract patches from this image. Of course, this is not the best way of doing. So how would we do it better for videos? We extract 3D spatial temporal tubelets and use these tubelets to project them into tokens. So here the tubelets are patches at the same relative location, extended into time. So basically the tubelets have coordinates the size of x times y, so here 16 times 16, times the number of frames which are used to construct one tublet. And this captures better the temporal information in the tokenization stage, and it works better than uniformly sampling or just mapping out the video into one image. And so basically this is an alternative to 3D convolutional neural networks. Here, similar to 3D convolutional neural networks, we extract the 3D tubelets to encode them into tokens. We then project the tubelets by a linear projection and obtain the tokens. We add the position, and then we can model with our transformer relation between all the tubelets in the video clip. So this extends the idea of patches in an image to tubelets in a video. However, there are more tubelets in an image, in a video, than patches in an image. And so this means that the complexity is quadratic in the tokens and gets very large. And so in order to take this into account and accelerate the compute, we have introduced different factorized variances. One of them, which I'll show here, separates the encoders for spatial and temporal information. This reduces the complexity in the compute and is less prone to overfitting. The spatial encoder here is initialized from a pre-trained vid model. And so if you look what it does, we take the video, extract the tubelets, embed them to tokens as before, but then instead of measuring the interactions between all tokens immediately, we perform the first take care of each image separately. So we model the relations for tubelets which correspond to one image or to one region first separately, and then have a second layer where we model the relation, the temporal relation between the resulting tokens obtained for each of these images. If we compare the different variances, we can see here that for kinetics 400, the spatial temporal variant where we really encode the relation between all tubelets works a bit better. But then for EpiKitchen, where we don't have enough training data, actually the factorized variant works better. And we can see that both of them outperform an average pooling baseline where we just extract the features with a transformer per image and then average them. And also see that with respect to runtime, the factorized encoder is only very marginally more complex than the average pooling baseline. We've also observed that regularization is important to train these transformers, particularly if data set is relatively small, such as EpiKitchen. We can see here top 1 accuracy. The top row shows if you use the standard augmentations with random crop, flick, and color jitter. Then we add Kinetics 400 linearization, which improves the results a bit. Important is stochastic depth. This is you spring layers in the transformer. That's similar to dropout, but here kind of spring, we ignore layers in the transformer. Then you can see that random augment, label smoothing, and mix up, which are all data augmentation techniques, further improve the results. So basically all these techniques are very important in the context of transformers. Here we obtain a 5.3% gain on EpiKitchens. If we compare to the state of the art, we can see here that our approach outperforms the state of the art on Kinetics 400. And then on the top, we compare to methods which don't use any large-scale data for pre-training. On the bottom, we compare to methods which use large-scale pre-training data sets, and you can see that this further improves the performance. We can also see that the size of the transformer allows to improve further performance. Obviously, it gets slower. And similarly on Kinetics 600, we also outperform the state of the art. And now we have a transformer for video, but we want to take into account for our video, we would like also to take into account the audio, so to have a truly audiovisual multimodal transformer. Here we take as input the images, so the videos, we have the same video projections as before, and we have the audio spectrogram patches. So the audio is represented by a set of spectrogram images. So we represent the audio by spectrogram images and then split those images into patches. And what's new here is we introduce a new form of such a multimodal transformer. Standard ways of fusion are late fusion, so we extract features for the video and the audio modality separately. Early fusion, where we learn the relations between the tokens from the start. Like this would be all the video and all the audio tokens are combined from the start. Or what we're showing here in the second illustration from the left, we can also do this early fusion starting from the middle of the layers. So this would be called mid fusion. And then what we introduce here is bottleneck fusion. So instead of measuring the relations between all video and all audio tokens, we measure the relation between the video tokens and the bottleneck tokens, and similarly, the relation between the bottleneck tokens and the audio tokens. So this allows for the video and audio signal to learn their representations independently, but have them connected via the bottleneck tokens. And B, it's obviously also less complex because basically it's not quadratic in the number of tokens, but it's only quadratic for one modality, and then combine the two modalities by this relatively few here 4 bottleneck tokens. And again, bottleneck tokens can be used from the first layer, or we can only use them starting at higher layers. And if we look at the performance, we can see here, this is results for the audio set and for bottleneck tokens. We can look at which layer we actually do the fusion. And here it goes from 0 to 12. In blue, the vanilla transformer. In red, the bottleneck. And we can actually see that the bottleneck transformer outperforms the fusion, the vanilla transformer, and we can see that basically only if you combine the information only at the last layers, they're kind of on par. And what's interesting, if you look at the result on the right, we can actually see that the bottleneck transformer in red is much less complex than the vanilla transformer, which combines as uses the full combination of the two modalities. So it has a significantly lower compute. If you look at the results on EpiKitchen, the state of the art is at 38.5. If we use our features and late fusion, we're at 37.9. And then by using our bottleneck transformer, we obtain 43.4. So we outperform the state of the art, but also significantly all the other variants of combining the modalities. And similarly, for the audio set, the first row shows the state of the art. Second row shows that our features and late fusion outperforms the state of the art. And then if we use our multimodal bottleneck transformer, we outperform significantly late fusion. And then just to show the impact of the different modalities, on the left, the top row shows the results obtained by vision-only features. The second row with audio features. So Epi Kitchen is mainly based on vision. So having only audio doesn't give good results in all cases. But then if you combine vision and audio, we further obtain the performance over using vision only. And then the other way around on the audio set, the audio, obviously it's constructed for audio classification. And so the audio results are better than the vision results. And the combination of the two further improves the performance. We've seen that these transformer architectures give excellent results for video classification. We've shown that it's important to precisely model the relation to spatial, the temporal, and the multimodal relation. Open issues are still how to design better model and how to get more data for general actions. And then also an open issue is how to do confidence prediction. And now what is future work? It's to also model not only the multimodal information, but also to model the interaction with the visual world. And the belief here is that we can learn better visual representations by interacting with the world. For here, we want to do learning by demonstration or reinforcement learning. And if you look at the example on the right, it's recent work on using a transformer for vision language navigation. So here, what we do in vision language navigation is we have instructions, an environment, and we want to predict the actions to execute the instructions. And if we use a transformer, we can actually take into account not only the present observation, but also the full history of the observations and the actions which we have performed previously. This allows us to memorize locations which we have visited before. As we can see here, for example, walk back to where you were standing previously with the second race, which is actually the red arrow here. Another problem in vision language navigation, especially if you use transformer architectures, is how to generalize previously unseen environments. The approach on the right shows a recent approach where we have collected additional training data based on Airbnb listings. So from these listings, we have collected additional rooms, concatenated them together to obtain extraction sequences and use this for additional attention. Please let me know if you have questions.
Okay, thanks so much, Cordelia, for your amazing talk. So, does anybody has question? If anybody has a question in the Zoom meeting, please raise your hand. Okay, there is no question from the Zoom meeting. And okay, no one from the YouTube channel. I just have one short question because we are also running out of time. Could you all please briefly compare the vision transformers for video, like in terms of G-flops and parameters, to previous state-of-the-art 3D channels like the X3D or slow fast?
Yeah, so we have a precise evaluation in the paper, and basically, obviously, the very huge transformer which give the best results, they're very slow, right? But if you look at this factorized model, which gives comparable results to the state of the art, our performance is actually faster, right? So I mean, obviously you need to look at exactly at the details, but there basically we have done a recent evaluation, and it shows actually that we can obtain comparable or better results for the same complexity, right? And so there actually this factorized approach is very important. And so basically, and also how you space the frames, right? What is nice in the transformer, you can completely modulate all these parameters, right? You can use more or less frames to extract the features. This is something which you cannot do with 3D convolutions, right? And then some of the very good results, they have also very large backbones, which are also quite compute hungry. But it's actually not as bad as you would think, right? It's on par, basically. And I can, if you're interested, I can send you the numbers, right? You need to look exactly at the numbers, because it's like, you can discuss it for a long time, but it's on par.
And we have some questions from our YouTube channel. Actually, I have to just pick one. Ishan is asking about, I have a general question for AVA and other existing action detection datasets like UCF101. Current datasets are actor-centric, which inhibits weakly supervised learning as neural nets focuses on action region rather than only actors. Any views to make annotations more action-centric rather than focusing on human detection? Yeah, this is the question from Ishan on our YouTube channel.
Yeah, I'm not entirely sure I understand the question. Is it about the annotation or the method?
I think his question is that the current datasets are mostly actor-centric. Like he says that it's the action region is focusing on only actors, not the action or event happening. And he's asking, is there any view on making annotations more action-centric rather than focusing on the actor or the human in the data? I think
the idea, I mean, basically you have data sets where you only have the temporal span annotated for the action, right? So there would be more action-centric. And I think the idea of AVA was to have spatial temporal localization, right? And that's kind of difficult. And then you have to have, I mean, then it's the human which is performing the action. Obviously, you could extend this to other objects, right? If you want to have an action of a dog or a car, you could also annotate this. But I think basically the idea of spatial temporal annotation is really to model the region and the temporal extent, right? And that's something which is hard to annotate, and you could obviously create other data sets. So this is not limited to human bounding boxes.
Yeah. Okay, thanks so much for your nice talk, and sorry for the inconvenience in the first joining the Zoom. And yeah, I think there is no other questions, and also we're running out of time. We should switch to the next speaker. Thanks for being.
Yeah, thank you. Bye.
Thanks. Bye.
So I think Dima is already here. Okay. Our next speaker is Dima Daman from University of Bristol. And Dima, the stage is yours.
Thank you very much. Thanks for the invite. I hope you can see my slides and you can hear me.
Yeah.
I will be presenting a bit of this talk, and also Mike, who's on the Zoom, will be presenting some of the joint work that we've done. So we'll mix it together, giving the amazing length of the talk, allowing us to talk about the variety of work we've been doing. And of course, it's great to follow Cordelia's talk. She's already mentioned our dataset Epic Kitchens, and the Vivid work that they had produced is one of the very recent works that had produced transformer-based performance on the action recognition task of Epic Kitchens. So in this talk, I want to keep this perspective of the holistic video understanding and show you an egocentric perspective to it. And a very fitting start is the discussion and the questions before on different data sets and being action versus actor centered. I'd like to kind of plot the types of videos that we've been playing with, because we call everything video understanding, but videos are so different, dramatically different on many dimensions. And I'm picking a couple here to showcase a particular notion of perspective, moving from maybe third person to what we call an egocentric of a first person perspective, but also keeping another very critical dimension, which is the dimension of how much editing or careful creation has taken place in producing these videos. And when we started doing video understanding, leading works have really relied on movies. Movies are not only third person, but also curated under very strict rules, right? If you go to a cinema school, you'll be taught about where the shots are taken and when to cut and where to take people from. You're gonna never take them from their back, for example, etc. And this is where video understanding started, and still significant types of videos are there, but increasingly we are exploring different types of videos. Amazing data sets, UCF, ActivityNet, Tumos, are on TV sport. So these are slightly less curated because these, sports men and women are not as rigid as movie actors. But again, they tend to be third person and there are clear cuts as they are produced. Of course, more and more, the world had changed. We all have mobile phones and lots of footage that we have online is mobile recordings. You carry your phone and you capture something. You might edit it a little bit before putting it, give it a bit of additional information. And of course, the extreme in this trend of perspective knowledge is if you're live streaming, right? You're in an event and you hold your camera and you're live streaming. There's absolutely no curation, but you're capturing a third person perspective. Let's try to shift a little bit into an egocentric perspective. And increasingly, we're seeing some of these YouTube videos having a mix of third person and third person or top view aspect of showing you how something is being done. So they tend to kind of be on that level, and they are definitely less curated than movies, but they're carefully edited. So they're educational and they're really helpful. There are lots of vlogs, and datasets are also be thinking about all these. Vloggers, bloggers, YouTubers who kind of carry their camera and talk over. These are less curated. They merge between different viewpoints, but they tend to be egocentric to an extent. They capture what you're doing, sometimes maybe not through a wearable camera, but what I want to present is this extreme, maybe other end, where there is an egocentric perspective. So it's a wearable camera, and data is completely unscripted, maybe on the same bar as live streaming, but with an egocentric viewpoint. So I recorded something for those who might not have played with Epic Kitchens, just to give that egocentric perspective or taste. And this is 45 minutes with audio, 45 seconds with audio. There is a lot in this video. We can start describing it, and the level of detail we can include in this short 45 seconds is going to be very long. You're going to focus maybe on the person deciding which onion to cut, or finding the chopping board in the drawer, etc. And these egocentric datasets tend to be completely untrimmed. So we're capturing hours and hours of people doing tasks. And there is a lot that you can think on the holistic space, but there is also a lot you can do on all levels of abstraction, understanding maybe what they're doing, but also how they are doing it. So what do these egocentric footage allow us to do? There is a lot of actions and objects, and perhaps most of the work in this area is about actions and objects, what actions are doing and what objects are you using. There are other questions we can ask, which is, how are you doing this? And Cordelia mentioned, transferring this knowledge into, say, a robot, and that requires knowing more than what objects you're doing, but how you're doing it, maybe how skilled you are in performing a task, thinking about the why and the goals and what the next steps would be, exact moments at which a person had done something or at which you can provide guidance. And there is work on egocentric. There is a recent work from Oxford where they're building maps out of epic kitchens and tracking people around the environments. Of course, the main thing that egocentric footage does not do is the who, because this is the person wearing the camera. So that's not a question we want to ask. The questions is all about the other things they're doing, given you're capturing that from an egocentric perspective. And Epic Kitchens is a long-scale collaboration with Toronto and Catania, and a huge effort. I tend to always get the pleasure to present. But the idea started with giving people cameras and asking them to go and collect footage in their homes. This type of data collection has not been attempted like this because people don't know then how to ground truth. 2 hours of someone in their kitchen doing all sorts of things. So they tend to then go and give people recipes to implement, and that allows easier ground truth. So to allow this completely unscripted nature, but still to enable annotations and ground truth, because we're not a very big lab, we really want to annotate this data set quite efficiently. So we came up with this idea inspired by what happened in movies over the years of talking over this footage, giving us some sort of a live narration, some sort of a weak supervision, but a very strong signal that we only need to refine, giving us dense action segments. And in 2018, we released the first version, Epic Kitchens 55. And of course, it's always interesting to do something and then learn from it. So we went and refined our whole exercise by collecting additional data, by improving the narrator into a pause and talk narrator, and that's publicly available, and improve the annotations. And in people's hands since last July was Epic Kitchens 100, which you've seen also already results on state-of-the-art performance on actions. The data being naturally collected is heavily long-tailed, and the y-axis here is log-scaled. So you can see that you have a lot more of certain actions than others, and similarly for objects. We have 300 objects grouped into these categories, higher level categories. We recently closed the 5 challenges that we had open since the end of last year on recognition, detection, anticipation, domain adaptation for recognition, new and exciting challenge, and multi-instance retrieval. And if you want to know more about that, you can look at the video that we recorded on all the challenge winners and the set of winners that joined on Sunday. We're very, very grateful because you do the effort, but unless people pick it up. And so we're very grateful to all the people who participated in the challenges. I'm not going to talk more about the data set. So if you're interested, please look at the data set for more details. I want to present some of the works we've been doing around this notion of egocentric understanding and around the notion of understanding holistic videos. And I was clearly told to focus on holistic. So I selected from these recent works. These are all works in the past 2 years and something. I selected some of these that I think will be very of interest to the 33 participants we have on the call, and I don't know how many on the YouTube. So the first thing I want to tell you about is skill determination. That's very much a holistic level understanding, because you really need to look throughout 2 videos to understand how skilled someone is. You can't get it from maybe one stroke of drawing. You have to really look at the full video, and then a human can easily look at these 2 videos and assess whether they believe one is exhibiting a higher level of skill than another. So they can say, definitely the right person is doing better. On my right, I think it's on your right as well. But of course, they might disagree on why they think this person is doing it better. It could be the sonic's expression. It could be the stroke of the line. But what we wanted is to replicate this human high-level understanding that definitely the person on the right is exhibiting a higher level of skill. So in this work presented 2 years ago, we looked at the full video. And of course, we looked at all the clips of the video, and we had these ground truth annotations from Mechanical Turkers saying the person is exhibiting a higher level of skill. So PI is doing better than PJ. And we can give the whole clip through, but not every part of the video is of relevance to skill. And we don't want to annotate that. We just want to understand skill and learn from the data. So we have the CME's architecture. Then you might kind of do some sort of temporal pooling. So you average pool over time. And you have a ranking loss that say, learn something that showcases that the person at the top is exhibiting higher skill than the person on the bottom. In this standard baseline, you would be treating all bits of the video similarly. More intelligently, you can add some sort of a learned attention weight that learns that certain parts of the video are more relevant to skill than other. And in this work, we showed that you can add an additional disparity loss that makes the learning more stable. But after doing this task, we looked at the results were good. It was really doing a good job for many actions that we've tested, either drawing that we've recorded in the lab or some stuff like braiding hair that we've collected from YouTube. But mistakes were not being picked up as parts of the video with high attention weights. So it wasn't really weighting these mistakes with high attention, even though a human would say a mistake is very informative to understand the level of skill of a human. So in this work, we've then looked at maybe having multiple attention weights, and up to this moment, they're exactly the same, but they are trained to behave differently by a rank-aware loss. That one module attends to what's good in the skill, and the other one attends to what's not so good. So we call them high level and low level attention. And if we look at the output of what they actually learn, you can see that the low skill is consistently picking up similar tasks, but also of relevant to what we call skill. So in applying eyeliner, it's someone removing bits of the eyeliner, and that's evidence of low skill. And in the origami, it's people undoing the fold. And on the other side, with the high skill, you can see in the origami, they're firming the fold. And interestingly, in drawing, we've picked hesitation, so moments of pausing to think, as evidence of high skill. The same behavior is evidence of low skill in other types of tasks, say cooking or applying makeup, but in drawing, just pausing to think about your next stroke is evidence of high skill. So again, this is looking at all the video, but understanding that parts of the video will better exhibit an element of skill. And for the works I'll present, there will be web pages for you to look at the code, the model, and the data sets. The other work that I want to showcase is related to understanding various modalities. And Cordelia's talk also noted modalities and how their influence on understanding videos can really be very impactful. In this work from last CVPR, we looked at modalities where in this case they were RGB and motion, so RGB and flow. And we had this 3D CNNs, and you can then do some sort of late fusion and decide the action. And if this is trained on, say, one of the kitchens of Epic Kitchen, so one environment, and then you try and evaluate it on another environment, we understand that there is some sort of a shift. So you're seeing different stuff, and accordingly, training on only a single environment is unlikely to generalize. And looking at the feature maps of the RGB space, you can see that in what you would call a source, so that's what you train on, and the target, that's what you would evaluate on, the features don't overlap. So clearly there is a clear domain shift. So what we noted here is you might have access to footage from the new kitchen, but you don't want to re-annotate. So we've introduced a self-supervised task given the multiple modalities that come in the video. And that task's role is purely to look at whether a video and an RGB come from the same action or from different actions. So this doesn't need annotations. You just look at whether they are from the same action or not. And you would train this binary loss of yes or no in a self-supervised manner, both on the first and the second kitchen, the one for which you have labels and the one for which you don't. And just doing that gives you these nice clusters. So it starts to merge or join stuff that are related to the same class or the same action. It doesn't overlap all the features, but it gives this clustering. With that, you can add the standard adversarial loss with a gradient reversal layer, and this then on both your modalities, and this then allows you to overlap your features. So this is the RGB space, and you can see the standard, which is called the source only. So the two videos in blue and red are shown below, and they're really far. When you add the self-supervision loss, they're already getting closer, but they don't overlap, but they're clustered into these cutting classes. And of course, using the combination of the full model, you can align them and you can recognize correctly this action in a new environment without additional labels. And this work basically has formed the base of the UDA challenge I told you about with modifications. So have a look at both the paper and the challenge if you're of interest. I also pause on this work, which we called retroactions, because it showcases where video has been quite underexplored. And I'll give an example and then we can take it from there. So this is the video. And if I ask you to give this video a label, an action class label, then you would say this person is closing a box or closing a container. I hope you agree. Let's watch it again. In fact, this video never existed. This is the video that was captured. And what I showed you was a time reversed version of this video. Time reversal in video understanding has been used as a signal for self-supervision under the assumption that if you reverse time, then the video is no longer a valid natural video. In this work, we first did the experimental study of showing people videos, some of them reversed, some of them in forward time. And we showcased that for many object interactions, these are reversible. By nature, they're reversible. We close and open something and then close it again and then open it. It's not the same as water falling down the waterfall, which is the standard example of this arrow of time or forward time notion. So we showed that you can actually reverse many videos and create new examples of exactly the same class, say moving this handle from left to right. Equally interesting, or maybe more interesting, you have these dualities where you can reverse the video and create examples of another class, like the open and close example I've just shown. And of course, there are videos that when you reverse, they break the concept of time and they are irreversible. And while these have been studied, the first two examples have been underexplored. So we looked at the something data set because it gives this fine-grained understanding. And we picked some of the examples where there is this duality. So we have examples of someone digging something out of something, right? And we would then flip these and train this other class, which is covering something with something. Oh, burying something in something, and the reverse would be digging something out of something, or covering and uncovering. And what we do in this case is we have only one class, so we don't have access to the training data of the other class. We just would reverse the first one and train our classifier. Now in testing, we want to test with the standard data test set. So the test has not changed. It's the training where we have removed access to all those classes that you have, all those examples in training. And that's why we call it zero shot, because we don't have any example of uncovering. We only have examples of covering, which we have reversed. So if you want to look at this work, really think about many of our augmentations that we're doing in video and think whether they're relevant, particularly when it comes to object interactions. And a work we presented this CVPR on few shot understanding, it's looking at whether we can actually learn the cutting example I've just shown you, but only from two examples, and where we are with this notion of few shot. So typical few shot understanding is where we have a query and we have something that's known typically as a support set. So you have a few examples of a few classes, and what you aim to figure out is whether the query belongs, to which of these classes does the query belong. So the objective is to learn a classifier using this support set that can classify this query. And all prior works, prior to this work we presented this CVPR, is they compare each video to each video in the support set. They compare the query to each video in the support set separately. Some effectively using an element of time warping, but then they assume that, one video is the best match. In this work, we started thinking differently, inspired by work recently published in Images called Cross Transformer, that looks at parts of a particular object, say a plane, and it tries to find evidence for that part in every image in the support set. But of course, patches in videos are not enough. Actually, frames are not enough. And inspired by earlier work that looked at maybe pairs of frames or triplets of frames as a good representation of videos, we propose our approach, which we call Temporal Relational Cross Transformer, TRX. We start with a video and with all the videos in the support set together. And then we would represent the video by pairs. So we have, this is trained end to end. So we have our backbones, and then we take the backbone in pairs. So we create this pair representation, both for the query and for the support set, because one frame is not enough to recognize the action, but two might be. And you can then do take all the possible pairs in the support set of all the videos, and you can do a cross transformer. So you have your query linear map, your keys, you can do a softmax, and you can then take your support set with the value of the transformer, and that gives you this that we call a query specific prototype. This you can compare to your query. Now this has attended to what's relevant to that pair of frames from the query in the whole support set. And you can do that for all pairs in your query. And accordingly, you can create a good understanding of how well does this query match all examples in the support set. And just in case pairs are not enough, and we show that for some fine-grained actions they are not, you can do the same for triplets. You're sharing the backbones. So this looks huge, but actually most of the memory and the inference is in the backbones, not in TRX. And you can do the same, and then you can average your evidence between different tuples, pairs, triplets, quadruples, etc. And also in the paper, we show that you can actually sample these and produce quite comparable performance and exhaustively. This work is currently the state of the art on all benchmarks of few-shot learning, on all the data sets that have been used for few-shot learning before. And we showcase that it's particularly useful because of this notion of looking at all the videos in the support set as you attend to more shots. And Toby, who's led this work, has produced a very, very nice GitHub repo. If you want to do anything to do with few-shot, I recommend that you start from there, because he's not only implemented our work, but all prior work with matching performance. So you can start from a clear GitHub that gives you a good starting point for few-shot action understanding. Right, time to give me a break, and I'll hand over to Mike to tell you about semantic similarity in vision and video.
Hi everyone, hopefully you can see my screen. So yeah, I'm Mike, and I'll present our work on semantic similarity in video retrieval, which was presented at this year's CVPR, like the main conference. So to begin with, just kind of what is video text retrieval? We have a video on the left, and we want to find the corresponding caption from the right. And we want to rank and retrieve what is the correct caption for this video. From this example, we can see that it's clearly a man is peeling fruit carefully and neatly. But for other examples, maybe this isn't so clear. So when we looked into these data sets that people were using for video retrieval, we actually find that there are many cases where choosing the correct caption is quite arbitrary. And when we look at it, we have two main problems where we have lots of relevant captions which are being considered as irrelevant. And also there's no way of kind of ranking more relevant captions than others. And we have a completely irrelevant caption here being treated the same way as a potentially quite relevant caption. When we looked at this, it's because current methods are making this following assumption, that there exists only one corresponding caption for every given video and vice versa. When we look at the data sets, we see this is clear to see for lots of different examples, and especially for UCook2, MSRVGT, as well as Epic Kitchens. And these are the three data sets that we look at in this paper and investigate the issues with this instance-based assumption. So the first thing we want to do is maybe look at the problems with this assumption, but how do we evaluate this? Well, we know from looking at the captions that there are many different captions which could be considered as relevant. And if we do that, we can see that we'll have cases where maybe the method performs better or worse than the true results that were performed. So when we do the evaluation step, as other methods have, we look at the best and worst cases, as well as the normal performance. And this gives us a chart, something like this, where we can see current methods on the right, as well as a simple baseline on the left. And you can see that the range of performance is very high considering the scores of the method, and it can be even unclear as to how much better these methods are beating the baseline. And we also see this for MSRVGT, as well as Epic Kitchens. So with this, we wanted to move to semantic similarity for video retrieval, and we had two main goals for this. Firstly, we wanted to move from a one-to-one relationship between videos and captions to a many-to-many relationship. So we have lots of different relationships between both the videos and the captions that they were not collected for. We also wanted to allow for differing levels of similarity. So we know that these top two videos both contain potatoes, but it's clear that for this video on the left, that the top caption is the most relevant. Yet if you are searching for a video of someone making a potato recipe, maybe this video is somewhat relevant as well. However, annotating many-to-many relationships is far too expensive in terms of time and money, and scales horribly with larger and larger scale data sets. So how do we relate this video with a new caption? We just define this as S of xi, yj, and we first make an assumption that a caption sufficiently describes a video that was collected for. So we have this caption on the right, and we assume that this sufficiently describes the video here. With this in mind, we can now define a proxy function that relates the two captions instead of using this relationship here, which is very hard to find. In the paper, we introduced 4 different proxy measures based on bag of words, parts of speech, synsets, and the meteor scoring function. And we can see that whilst these tend to give different scores for different captions, they tend to rank the relevant captions highly and do a good job of that. And we find that this performs well when we compare it to human studies as well. So how do we evaluate this semantic retrieval? Well, we now have multiple relevant captions with differing levels of relevancy. And in order to do this, we propose using the normalized discounted cumulative gain metric. And this gives us scores between 0 and 1 on how well the method is performing. Now, when we compare instance-based retrieval on the left to semantic similarity retrieval on the right, so we have a different performance for each of the 4 different proxy measures, we can actually see some surprising outcomes. Firstly, you can see that the performance between the MLP baseline, so a simple baseline on the left, as well as current methods, for instance retrieval, they're clearly beating the baseline. But when we go to semantic retrieval, we can see that they're actually getting pretty similar results. And in some cases, the baseline is actually outperforming the current methods. And when we looked at this, we actually find that these current methods are overfitting towards finding these corresponding captions, which are kind of quite arbitrary. So how might we want to train better for semantic similarity? This is the final thing that we look at into the paper. And first, I'll just go through how we generally train for instance-based video retrieval. And this is using triplets as the learning objective. So we start off with our query, a positive example, which is the corresponding video, as well as all the negative videos in the set. And we want to ensure that the distance between the query caption and the positive video is smaller than the distance between the query and every negative within the batch. When we move to semantic similarity video retrieval, we first choose a threshold. And this allows us to group all positives within the dataset on a query basis. When it comes to training, so during each epoch, we can then sample a single positive from the set, and then we can learn as normal. So we want to ensure that the distance between our query and our positive example is closer than the query and the negative example for all of our negatives. And when we do this, we actually find that, first, training for semantic similarity gives you a boost in performance over training for instance-based retrieval on all of the different proxy measures. But also, regardless of the proxy measure that you train for, you actually get a nice boost in performance as well. So when we look at the yellow bar, which is using the part of speech metric, we still get a boost in performance over the instance-based metric, although still training for bag of words is best. So in conclusion, current approaches assume only a single caption is relevant for a video, and we find that this assumption breaks for all popular video retrieval datasets. To overcome this, we propose semantic similarity for video retrieval, and this allows us to have multiple relevant items with differing levels of relevancy. Thanks for listening for this part of the talk. We have a website up, which includes more details, as well as the paper. And we also have a GitHub repo, and this includes code to train and evaluate your models for this new task. Thanks, and I'll just hand back over to Dima.
Thank you very much. Okay. Sure. So I hope we're back where we were. Thanks, Mike. Yeah, if you really are doing any retrieval, I encourage you to look at the code base, because you'll then prove that your method is actually outperforming rather than overfitting. In the last bit of the talk, before I take your questions, I'll tell you a little bit about audio. And of course, we had a very good introduction about audio and how audio is important in Epic Kitchens from Cordelia's work. I just maybe show you some of the examples of why we decided to use more audio, because when we were annotating the data set, we realized that we can't really annotate start and end time of when the person actually turns on off their blender without audio. Once you hear your audio, your ability to do start and end times changes dramatically, like this. So in case someone was sleeping, I've woken them up. Also, it allows you to understand, I told you about skill, it allows you to understand the skill level. If we watch this video without audio and ask you which was the hardest hit, you wouldn't know, and that's where audio makes a big difference. And in the work we presented in ICASP this year, we looked at the types of sounds in current video datasets that have strong audio, like Epic Kitchens or VGG sound, and realized there are two quite distinct types of sounds that we exhibit. We call the left one harmonic sounds, and the right percussive sounds. And if you don't work in egocentric, this is still relevant because the same exists in, say, VGG sound. So in this work, which actually when we won Outstanding Paper Award in ICASP, we were looking at the fact that in humans, there is a strong evidence that the ventral dorsal stream has this two approaches to attend to high spectral resolution, and also, so that's even in the audio, not in the video. It's understood in the video, but there is similar evidence in the auditory system of having these two ventral dorsal streams. So inspired by what we've seen in video and the success of types of architectures that attend to different frame rates in the video, we have this auditory slow fast, where basically we're having a slow stream that looks at a low temporal precision of the audio and a large amount of channels, and a fast stream that has fewer channels and higher temporal resolution. We're having a multilateral set of connections, and importantly, separable convolutions. Because while in images, the two dimensions, the H and W are actually homogeneous, in spectrograms, they're very different because the frequency and the time aren't really. We're putting them in two dimensions, but they're not exactly the same. So we have separable convolutions. And the work is doing really well on audio-only performance on the Epic Kitchens test set. So I think this is purely audio. So I think Cordelia was showing something like 13, I think, here. So we're getting a clear boost on audio only by proposing the auditory slow fast. And we can clearly show that on VGG sound, it in fact is matching what we expect. So things like, cat hissing or whale calling are in the slow stream, and things like playing drum or tap dancing are being better recognized by the fast stream. Right, and the remaining bit of the talk, I want to pay attention to one aspect that we need to do more of in video understanding, which is trying to understand what our models are learning. And this is work led by Will Price. This is very much his contribution to the way we're thinking in the lab about videos. Take a video in, we know that we can put it into a model, and we know we can monitor the performance of that particular class. However, the contribution of the individual frames to this class, of course, if you don't see any frames, you can make a prior probability assumption. So the prior of a class, you can predict that without seeing any frames. But assuming you see 6 frames, their contribution, their individual contributions to the model's performance is very different, because some are better evidence of a particular class than others. So in this work, we're doing this very systematically, but at the same time in an efficient manner, which is part of the algorithm in the paper. So as you add a single frame, you can see the change in performance, and you can add more frames and have your model attend to more frames and look at the difference in your output prediction. And these have to be attributed to the frames you've added. But of course, frames get added in random orders. So you need to do all possible combinations of frames to actually understand the attribution of a particular frame. And in fact, some frames are harmful. So actually incorporating them into the set of frames you select will result in your actual ground truth performance being worse. So they are negative attributions. So this is an example. Remember, these are attribution methods, so they're like grad cams. They're showing what the model is doing. So you have trained the model, and then you look at the attribution of every frame, and this is from the something something data set. And the class is show that something is empty. Clearly, the person is actually trying too hard, so they're flipping the glass and then coming back. And the model is clearly saying those flipped frames, those frames of the flipped glass are having negative contributions to knowing that this is showing something's empty. And we have a live dashboard for you to select any class in the something something data set and then any examples. And then you can, look at these examples and look at the contribution of every frame and see which frames exactly does the model respond to as, these are the most influential frames in making that decision. And really looking at correct examples and incorrect examples is very helpful. And just off the press of Tom, who's a summer intern, done a brilliant job in taking the same work and giving us a dashboard for Epic kitchens. So this is not yet public, but I wanted to showcase that to you. So this is a class of opening a drawer. And very interestingly, you can see that I'll go back to the very beginning. You can see that the performance of the attribution of the individual frames for the verb and for the noun are distinct. So at the very beginning, there is the motion of opening the drawer. And so it really is seeing it. And by the end, the motion is less. So the action evidence is less. But the noun, the influence of the noun is different because you don't see the drawer at the beginning and you see the drawer at the end. So in fact, attending to different parts of the video can give you different understanding of the verbs and the noun. Sorry, I'm skipping. And this is another very good example of opening closing a fridge, and it's incorrectly recognized as opening. And by looking at the attributions, you see that the model is actually smarter than the labels. Because what this person is doing is they attempt to close, but then at some point they're actually opening the fridge again, taking something, and then eventually closing. Yes, it's true that in the whole bit you have a closing action, but then the individual frames are giving you different evidences, and the model is correctly recognizing which frames are attending to opening and which frames are attending to closing. And in fact, changing the number of frames you're passing to the model will give you different predictions because you are either including or excluding these fine-grained understanding that is beyond the holistic label. And this is another good example of cutting a tomato, where I like the fact that the high points are when the person is actually cutting, and the low points is when the person is moving the knife. And this model is a TRN model. It's not really designed to do that, but it had learned actually to attend to the exact moments at which actions are actually happening. Looking at these gives you lots of high hope in the evidence. And if there is time, I'd like to show you this live. But before I switch my screen, if you're asking yourself, are there enough data in egocentric vision? Should I do egocentric vision? Then if you've been in different workshops in CVPR, you hopefully have heard of the Ego 4D dataset. So this is coming towards the end of the summer with lots of annotated footage outside the kitchen, very much in the same line of Epic Kitchens. Give people cameras and let them collect what they do in their daily life. And this is an effort of a big team, including Bristol, and led by Kristen Grumman at FAIR. So, right, I will give the conclusion and then switch to the dashboard. I believe holistic video understanding goals depend on the video source, and that's where we started. Movies are not the same as how-to, are not the same as egocentric. Egocentric videos offer this unscripted footage. There is plenty of potential as well as plenty of challenges. The value of audio and language cannot be underestimated, and the risks cannot be underestimated. Frame attribution methods do offer insights, new insights, into what we need to do next to understand videos. There are already large-scale egocentric vision, and massive scale is on the way. And I get the pleasure to present this, but this is hard work of a very large not very large, of a medium-sized, very dedicated team. And you've met 2 of the team now. Until we get the questions, I'll try to share my screen and show you the dashboard live. So this is the dashboard that allows you to then to select the verb and a noun and then select an example. And then you can see, for example, this is closing a cupboard. You can see the attribution of these individual frames, and you can change the number of frames that the model sees. And this is another cool example where there is evidence of cupboard at the very beginning. Then there is less evidence of the cupboard. And at the end, there is more evidence of cupboard. But in fact, this is a different cupboard. But the model still says there is more evidence of the cupboard. And you can really select various types of actions, say opening a fridge. And you can, again, look at the parts of the video that attend better to this example. And then at the very end, where maybe the person is no longer opening, move to the next action. In fact, the model is very good at saying, this is no longer opening. This is now a different action. And if you're doing anything in untrimmed, I encourage you to look at these attribution methods. I am 5 minutes to go for questions.
Okay, thanks so much for your amazing talk and wide variety of topics that you had covered. So I don't see any question from the Zoom. We have a question from the YouTube channel. Ali has asked that due to the nature of video, repetitive patterns in sequence of frames compared to other dataset samples, do you think the capsnet and routing concept can contribute to the architecture of attention?
The capsnet and what?
Yeah, the capsnet and routing concept in the capsnet, I think, can contribute to the architecture of attention. I'm not really sure what he means. I've also asked for clarification, but he has not answered yet.
So let's not talk about maybe a specific architecture. Does attention make a difference in these types of videos? Absolutely. Mm-hmm. But doesn't attention make difference in all types? I would say, I think there was a question before about the notion of actor-centric. And, you know, if you can consider the hand an actor, then again, there is a lot of interactions around hands, but they're moving a lot more in the frame than, say, people in third person. So both spatial and temporal attention here is hugely significant, and you can't get away with detectors. Right. So in that sense, maybe novel architectures can prove significant, and we've seen that transformers, spatial temporal transformers, are already giving good results on this type of data set. Did I freeze?
Okay, thanks. And I also have a question regarding the explainable AI part. Can you hear me well? Because
yeah, I think I froze shortly. Yeah.
Okay, no worries. Have you compared your experiments with, like, for example, the LRP methods for where you were like just checking out which frames are contributing more to the final prediction?
Yeah, so we compared to the various types of approaches, both in terms of, so the main difference that we have over those other approaches is that we're actually doing the work of taking a frame in and out and testing the model fully. So to an extent, we're really doing the bit, but we're doing it fairly efficiently. That's why the code out there is really helpful. We showcase that we're better able by doing that to attend. And this is actually a fairer way because we are in fact measuring the impact of a frame to all combinations of possible frames. So with that in mind, with the fairness aspect, the fact that we're building on this foundational aspect from game theory, we are definitely getting better performance. But that is exactly by not really guessing. We're actually going into the sequence and removing one frame at a time from all combinations and training models that can take a variable number of frames. But as I said, crucially, doing it efficiently so it doesn't take very long for you to produce these attributions.
And can you also just say, for example, these findings are causal, like that the contributions of the frames in the score that you find are like a causal relation, or it's like just a correlation that you say that we are finding some stuff there, but we are not sure?
So this is based on the model, right? The model is trained, and then you are interrogating the model for what it had learned. As I showed you in the example, really the model is trying to get best evidence. And in fact, best evidence in actions tends to be motion, distinctive motion. Best evidence in objects tend to be size. So when the object is the biggest possible size in the image, that is the case. So that's so cool, because I wanted to show this other dashboard, because the work we've done was on something. So we didn't have this to verb noun. And because we've done this work over the summer, and we wanted to plot the same way we have been learning for epic kitchens, that this two output of verb and noun, we're starting to discover that they are actually in conflict. What is the action and what's the object isn't exactly in the very exact location within the frame. Hot off the press, I think there is a lot of food for thought for us as well as for others.
Yeah, and just one other minor question regarding this, because it's really interesting to me, and maybe I didn't get this part correct. Maybe you've done it. I'm not sure. Just asking to make sure. For when you say that you're adding the frames to your model, so is it like that the model is seeing various video chunks or clips with different temporal lenses?
Correct.
Yeah.
So we have a multi-scale model.
Affecting the results, maybe it's
I think I would suggest you look at the paper for details, but we have a multi-scale model trained jointly. So in some sense, it's very similar to how TRN operates. So it's trained jointly, but we can interrogate it by feeding variable number of frames. So in fact, when I show you 8 frames, we have fed this model into all combinations to give you the attribution of that particular frame, assuming it had seen nothing and only this one, or it had seen any 3 and only this one, of course, in order.
Yeah. Okay, great. Thanks so much. Let me see if there is any other question. Okay, no, we don't have any other question from the YouTube channel and no one on the Zoom. So thanks again for your nice presentation and your nice talk, and thanks for being with us today.
Thank you.
Bye. So now it's time for our oral sessions or oral papers. So the next oral paper is Integral Action, Pose-Driven Feature Integration for Robust Human Action Recognition in Videos. I'm not sure if
just minor thing I would like to add. So maybe like all the speakers for the session, like it's approximately 7 minutes talk and 2 to 3 minutes of Q&As. So it would be great if you guys could just fix it with the timeline. And second thing is, so you guys are going to share your slides. And also the second thing is, it would be great if you could, if the main speakers could put their first name, first last name _ P, which is the presenter _ the paper ID, so that you could easily be made a co-host, so that Mohsin could easily co-assign you. And yeah, great, thanks. Go ahead.
Okay, thanks Vivek for the information. And okay, so is the presenter online? Is it?
Yeah, I'm here.
Okay, perfect. Then the stage is yours.
Should I start?
Yeah, can go.
Okay, thanks. Can you see my screen?
Yeah.
Okay, let me start then. So hi, I'm Kyung-Sin Moon of Seoul National University, Korea. Thanks for inviting me to this great place. Today I'll talk about our oral paper, Integral Action, Pose-Driven Feature Integration for Robust Human Action Recognition in Videos. So out-of-context action videos contain videos whose action class and context has weak or no correlation. For example, this video shows a man is surfing on the yoga pad, and this video shows a man is bowling at a playground. Unfortunately, most of the recent human action recognition methods are easily fooled by these out-of-context action videos as they learn undesired correlation between action class and context. For example, they classify the top video to doing yoga by being dominated with the yoga pad. Also, they classify the bottom video to playing soccer by being dominated with the playground. Then, what makes the existing method vulnerable to the out-of-context action videos? This is because most of the data set mainly contain in-context action videos whose action class has strong correlation with context. For example, videos in kinetics captured a swimming pool contain people swimming. Therefore, models trained on kinetics tend to classify videos captured at swimming pool to swimming by only focusing on background, even when people are skydiving. This is undesired correlation between action class and videos. To resolve this bias, one can try pose-based action recognition methods. As human pose only provide human motion information without context, it might be robust out-of-context action videos. However, the absence of context makes them vulnerable to in-context action videos, as shown in this video. This video contains barely visible human, and context play an important role. Pose-based methods fail on these videos. Let me summarize previous approaches. The appearance-based method utilizes context information. They are strong on in-context action videos, however, weak on out-of-context action videos. On the other hand, pose-based action recognition method utilize human motion information. They are weak on in-context action videos, however, strong on out-of-context action videos. Our integral action is proposed for robust action recognition on both in-context and out-of-context action videos. Let me introduce the overall pipeline of integral action. First, an appearance stream takes RGB video and extracts the appearance feature using TSM. In a parallel way, a pose stream takes a pose video and extracts pose feature using TSM as well. From the extracted pose feature, it predicts a gating matrix, which gates appearance and pose features for the integration. The gated features are integrated for the final action recognition. Our first contribution for the robust action recognition is a pose-driven feature integration. The pose stream decides how much appearance and pose information to use. It effectively prevents our system from being dominated by the appearance information. For example, when the gating matrix is predicted in an appearance-driven way, it could not prevent the bias, as the gating matrix is predicted from the biased context information. On the other hand, our pose-driven approach can effectively prevent the bias by predicting the gating matrix from non-biased human motion information. The second contribution for the robust human action recognition is a priority for pose, which is a simple regularizer. It enforces the predicted gating matrix to prefer pose features. Therefore, it prevents the integration from being biased toward the appearance stream, which arises from the dataset bias. So how does our integrated action actually work on in-context and out-of-context action videos? When the input video is in-context action videos, the pose feature is not enough. Therefore, integration produces large G value to use much appearance feature. On the other hand, when the input video is out-of-context action videos, the pose feature is enough. Then it produces small g to use little appearance feature. This table shows the accuracy comparison between appearance only, pose only, and ours on in-context and out-of-context action videos. Our integral action produces robust results on kinetics, mimetics, and TRGPD compared to appearance only and pose only approaches. This table shows accuracy comparison between appearance-driven, pose-driven, and both-driven feature integration on both in-context and out-of-context action videos. Our pose-driven feature integration achieved best result on mimetics with marginal accuracy loss on kinetics. This table shows accuracy comparison between previous feature integration methods, such as appearance and pose stream score averaging. Without our pose priority, all feature integration methods suffer from low accuracy on mimetics, while producing similar results on kinetics. Our pose priority is necessary to prevent our system from being dominated by context information. Without our pose priority regularizer, a model is automatically trained to strongly prefer context information from the appearance stream due to the dataset bias. As the figure shows, when there is no regularizer, G values are biased to large values, which prefer appearance context information. These are, sorry. So our integrated action produces robust results on all three data sets, including out-of-context action videos. Note that ours produces much better result on mimetics than appearance-based method. Also, it produces much better result on kinetics than pose-based method. These are qualitative results. First, let me show result on in-context action videos. The appearance only on ours produce good results, while a pose-based approach fails as it does not have context information. These are more results on in-context action videos. And these are results on out-of-context action videos. The appearance-only approach fails by being dominated with the context information. For example, in the top figure, the appearance-only method is dominated by bobbers, so it produces clean and jerk. These are additional results on out-of-context action videos. Finally, let me show some interesting examples where both appearance-only and pose-only fail, while ours succeed. In the second figure, appearance-only approach classified the video to drinking by seeing lots of people and lights. On the other hand, the pose-only approach classified the video to playing volleyball by only seeing the body pose of the man. Ours integrated both information and produced the correct answer, a plague saxophone. Thank you for listening.
Okay, thanks so much for your presentation. Is there any questions regarding this paper? We don't have any question on YouTube channel yet, and from the Zoom. Okay, there's no questions. Thanks so much for your presentation, and thanks for attending our workshop.
Thank you.
Sure. So the next paper is, just a moment. Okay. The next paper is rethinking training data for mitigating representation biases in action recognition. Unfortunately, the author couldn't attend the live session because of the time difference, so he has sent us a recorded talk, and I'm going to share my screen with you, and then I'm going to play this talk with you. Just a moment. Share my screen with you, and then I'm going to play this talk with you.
Hi, I'm Kensho Hara. In this presentation, I introduce my work about rethinking training data for mitigating representation biases in action recognition. First, I talk about the overview of this study. Video datasets for action recognition are mainly divided into generic and fine-grained action recognition datasets. When we train 3D CNNs on each type of dataset, we can acquire different feature representations. The research question of this study is, representation biases acquired by using a different type of datasets are different or not? So why should we do research about such question? I talk about the background. Spatiotemporal 3D CNNs are effective in action recognition and recently often used. But some studies showed video datasets for generic action recognition have biases toward recognizing not dynamic motions, but static cues. And 3D CNN trained on such datasets tend to ignore temporal information in videos, even though the temporal information is important in action recognition. On the other hand, fine-grained action recognition datasets are expected to have small biases because such datasets consist of videos in a specific domain. So in this study, we examined training 3D CNNs on various video datasets in order to build the models that properly leverage temporal information to recognize actions. We compare the biases of models trained for both generic and fine-grained action recognition tasks. As the representation biases in this study, we use accuracies for cases in which the input frames were shuffled during testing. If the biases of trained models are large, the models perform well even using the shuffled videos, because the shuffling videos destroy temporal information of videos and the biased models ignore temporal dynamics. So we compute log ratio between the accuracies on original and shuffled inputs and use as the definition of representation biases. And as a recognition model, we use 3D Resident 50 in this experiment. And we use this dataset in the experiments. For generic action recognition dataset, we use Kinetics 400, moments in time, ActivityNet, UCF11, and HMDB51. We also use something v2, Gesture, GIM288, and Diving48 for fine-grained action recognition datasets. We mainly conducted 2 experiments in this study. Here, we explain the first one. In this experiment, we examine representation biases of video datasets for both generic and fine-grained action recognition tasks. We assume the biases toward static representations are different between generic and fine-grained recognition datasets. We confirm the assumption by training 3D Resident 50 on each dataset. And this is the result. The accuracies are different based on difficulty and number of training data of datasets. So here, we focus on the log ratios of the accuracies between the original and shuffled inputs. When the log ratio is large, the accuracies on shuffled inputs significantly are decreased. It means the model properly leverages the temporal information. As you can see from this table, the log ratios of generic action recognition datasets are small, and the ratios of fine-grained recognition datasets are large. So this result indicates the biases learned from fine-grained action recognition datasets are smaller than those of generic recognition datasets. Next, we explain the second experiment. We explore the transferability of the models trained for both generic and fine-grained action recognition tasks. Here, we assume models with large biases toward static representations can work well on datasets of generic action recognition, but perform poorly on datasets of fine-grained action recognition. We confirm the assumption by fine-tuning the model trained on each type of dataset. This is the result. We show the results of fine-tuning on UCF11 and Diving 58 datasets. UCF11 dataset is a generic action recognition dataset, and Diving 48 is a fine-grained action recognition dataset. The model pre-trained on large-scale generic action recognition datasets, such as kinetics and moments in time, achieved high accuracies on UCF11. But accuracies on Diving 58 are lower than the accuracies of fine-grained recognition datasets. even though the number of training data of fine-grained recognition datasets is significantly smaller than generic action recognition datasets. These results indicate the biased representation trained for generic action recognition degenerates the transferability to fine-grained action recognition. So this is our conclusion. In this study, we examined training 3D CNNs on various video datasets. From the experimental results, the representation biases learned from fine-grained action recognition datasets are smaller than those of generic action recognition datasets. And the biased representation trained for generic action recognition degenerates the transferability to fine-grained action recognition. So using fine-grained action recognition dataset is a better way to train the model that properly leverage temporal information. I'm sorry for I can't discuss directly here. If you have any questions, please feel free to contact me by email. Thank you for listening.
Okay, if you have any questions about this paper, please write the author an email and ask him. Unfortunately, as I said, due to the time difference, he couldn't join us. So we're going to start to the next paper. The next paper is MDMMT, multimodal transformer for video retrieval. Okay, the presenter is with us, and yeah, you can go on.
Yes, do you hear me well?
Yeah.
My name is Maxim Zabraev, and I am going to present our work, multi-domain multimodal transformer for video retrieval, which was done with my colleagues from Lomonosov Moscow State University and Huawei Moscow Research Center. Main points of our work are: we are solving the task of text-to-video retrieval, where we are searching video segments using textual queries. Our model is designed for general usage. Our goal is to decrease the bias for any specific test data set. Our model extracts and fuses information from different modalities, such as video, static images, and sound. As a result, we managed to create a single model that shows state-of-the-art performance on different benchmarks such as LSMDC and MSR-VTT. The formal definition of text-to-video retrieval task is: there is a set of videos G. There is arbitrary textual search query Q, where Q is a natural language description of video we would like to find in G. The task is to find the most relevant videos from G for the query Q. Our work is based on multimodal transformer architecture. The main points of MMT are: it uses several pre-trained frozen neural networks to extract sequence of features from different modalities. Then obtained features are aggregated by transformer encoder into the single video embedding. BERT model is used to obtain the single textual embedding from query Q. Then the cosine similarity is computed, which is treated as a score between the text and the video. There are dozens of data sets which can be used for a video retrieval task. Some data sets consist of segments from movies. Some data sets consist of random videos from the internet. Most popular data sets are MSR, VTT, and LSMDC. Such data sets consist of pairs, video segment, and textual description. The most common metric for text-to-video retrieval is R5. The definition of this metric is shown on this slide. What was the motivation for our work? Before we start our research, we collected large gallery of random videos from the internet. Then we tried to use the state-of-the-art approach, MMT, to search video segments using random textual queries. We found out that MMT works poorly. It happened because MMT was over-specialized for small training data set. So our goal is to create the single model that will work well with any videos and any search queries. Additionally, we want this model to show good performance on any test dataset without fine-tuning. Our main improvements over MMT are: we use stronger pre-trained feature extractors. This is very important to use good feature extractors, because if feature extractor doesn't extract some information from an input video, this information will be lost in the final embedding. We've tested a lot of pre-trained feature extractors and picked the best ones. Additionally, we used significantly more data for training. We combined 8 different data sets into the single large training database. As a result, we managed to create a strong model and significantly reduce the bias for any specific data set. In the first 3 rows of the upper table, we trained 3 models. As you can see, if a model is trained only on MSR-VTT, it shows good performance on MSR-VTT test. At the same time, it shows poor performance on other tests. We observed the similar situation for all data sets. As you can see in the last row, that if we combine all data sets, the model will work well on all data sets. At the same time, without fine-tuning. The bottom table represents 4 recent main approaches in text-to-video retrieval task. In the first row, the MMT approach is shown. The authors used 7 modalities and trained different models for different tests. The second row is our solution. Compared with MMT, we use only 3 modalities and trained a single model for all tests. As you can see, we improve the result of MMT by 10% on both datasets. The third approach is an image-based clip, which shows good results on many vision tasks. We tested this solution on MSR-VTT and LSMDC without fine-tuning. The last row represents a recent state-of-the-art clip-for-clip solution. Here is the author's fine-tuned clip for downstream datasets. Unfortunately, the authors trained different models for different tests and haven't published pre-trained model, so we do not have and can't cross-test their models. The important thing is log linear generalization law. Here we show how R5 depends on training dataset size. The x-axis represents dataset size in logarithmic scale. The y-axis represents R5 metric. As you can see, R5 grows according to log linear law. We still have not observed the saturation or plateau. The main thing here is that if we want to train a strong model, we have to significantly increase size of training dataset. Conclusion: we present MD-MMT for video retrieval task, which is improvement of original MMT, where we use to the best of our knowledge pre-trained feature extractors and significantly more data for training. Our solution achieves state-of-the-art result on MSR, VTT, and LSMDC benchmarks using a single model without fine-tuning. There is still a big room of improvement because we observe log linear R5 growing depending on the training data set size. Our plans are, first, to enlarge the training database. Second, to use end-to-end training like clip for clip with the larger training data set. Thank you.
Okay.
Any questions?
Yeah, there are some questions for you on the YouTube channel. Thanks for your nice presentation. There's a question someone has asked. It seems that the most used testing dataset for text-to-video retrieval is MSR-VTT. How the results on it are correlated with the real video retrieval?
So very good question. Let me show you this slide, and please look at the bottom table. Here, 2 important rows. This is first row with original MMT. In the third row is a clip approach. As you can see, clip shows much lower results than original MMT. This is approximately 20% lower on MSR-VTT. But As I told in the beginning of my presentation, we collected large gallery of videos and we tested MMT and clip on this gallery, and we try to search arbitrary text search queries. And MMT works very, very poor, but clip works very, very well. So I think MSRVTT is not maybe not the best test for testing video retrieval power.
Okay, thank you. Okay, there is no other questions, and we should go to the next paper. Thanks again for your nice presentation.
Thank you.
The next paper is, okay. The next paper is SAIL-VOS 3D, a synthetic dataset and baseline for object detection and 3D mesh reconstruction from video data. The author is with us. The stage is yours.
Okay, hello everyone. I'm Yuanting from UIUC. I'll present our work, SAIL-VOS 3D, which is a synthetic dataset, and we established some baselines for object detection as well as 3D mesh reconstruction from video data. For 3D shape reconstruction given as input, an image or a sequence of frames, we want to predict the 3D shape of the object appears in the image or frames. This is an important research problem for 3D understanding and has applications in augmented reality, gaming, and 3D object recognition. Here, I list some common 3D datasets: ShapeNet, SunCG, and ScanNet. Some of them capture only a single object at a time, and some of them focus only on indoor scenes. Importantly, these datasets contain either static images or capture only static scenes. They don't permit to study 3D scene understanding with dynamic shapes using the temporal information. In order to create a 3D video dataset capturing diverse and dynamic shapes, we collect SAIL-VOS 3D. We use the game GTA 5 to collect data. With good visual quality of the game engine, the rendered images are realistic. There are various scenarios in the game and different weather and lighting conditions. Importantly, we can get ground truth annotations from the game. Here, I show a video sequence of the SAIL-VOS 3D dataset. And here is the corresponding mesh data. We collected consistent annotations across frames. That is, objects are tracked. In order to get the ground truth, we hook into the direct 3D graphics pipeline. Note that before the geometry shader stage, the shaders can only read but cannot write to the memory resources. To collect the mesh data, we create and attach a geometry shader to the vertex shader such that we can string the vertex data to buffers in the memory. To collect the data, we play the cutscenes in the game and get the RGB frames. We hook into the direct 3D graphics pipeline to get annotations, including instant segmentation as well as amodal segmentation. We also record the depth buffer and also the meshes. Besides, we label the semantic class of each object, and there are 178 different categories in total in the proposed SAIL-VOS 3D dataset. Here, I show the dataset statistics and compare with other common 3D datasets. The proposed SAIL-VOS 3D dataset consists of more than 400 videos, more than 200,000 frames, 178 different object categories, and more than 3 million annotations. Comparing to the large-scale synthetic dataset, SunCG, Selvo's data set. Selvo 3D captures videos on both indoor and outdoor dynamic scenes. And compared to the Kitty datasets, which captures dynamic scenes, Selvo 3D has much more annotations, around 3 million mesh annotations, as opposed to 40,000 point clouds. We evaluate the shape reconstruction quality using Mesh AP on Selvo 3D. Compare the baseline pixel to mesh, a mesh-based method, Pix to Vox, a voxel-based method, and Mesh RCNN, a hybrid method using both voxel and mesh representations. We also propose a baseline video to mesh, which uses the temporal information by making prediction conditioned on shape estimated from the previous frame. We evaluate using different splits based on object size, occlusion rate, and video length. We found that our video to mesh approach benefits from using the temporal information and outperforms the baselines on occluded objects and also on objects appeared in long clips. We tested a Selvo 3D trained model on a real video from the Davis dataset. We found that the predicted shapes are reasonable even though the model is trained entirely on synthetic data. Here's another transferring example. To assess the use of synthetic data, we study transferability. Specifically, we use the Selvo 3D pre-trained model and fine-tune on Pix3D dataset using different amounts of Pix3D training data. In the low data regime, where only 10%, 20%, and 50% real mesh data of Pix3D are available, pre-training on synthetic data is beneficial. The model pre-trained on Selvo 3D outperforms the model without pre-training on the low data splits. To conclude, we propose Selvo's 3D dataset, a video dataset for object reconstruction. The dataset includes annotations such as 3D meshes, depth, object bounding boxes, and segmentation, providing ample opportunities for 2D and 3D scene understanding from video. We established the benchmark and baselines for evaluating 3D object shape reconstruction from video data. You can find more information on our website. Thanks for listening, and I'm happy to take any questions.
Thanks for your presentation. Let's see if we have some questions. Okay, there is nothing here. Okay, is there any question regarding this paper from the Zoom or no? Thanks again for your presentation, and now we should go to the next paper. So the next paper is object graphs using objects and graph convolutional networks for bottom-up recognition and explanation of events in video.
Hello.
Hi.
So, can I start?
Yeah, sure.
Okay, thank you. So, in this presentation, I will talk about our new method called object graphs, which is using an object detector and graph convolutional networks for the bottom-up recognition and explanation of events in video. This work has been developed in collaboration with my colleagues Andreas Goulas, Damialos Ganalopoulos, and Vasilis Mezaris, our lab director. So the recognition of high-level events in unconstrained video is a major topic in multimedia understanding. For example, here we can see an event landing fish video describing a landing fish event from the trick-built multimedia event detection dataset. Most approaches in this domain are top-down. They use an event label to implicitly focus on frame regions that they are mostly related with the event. Recently, bottom-up approaches have shown quite promising performance. For example, in the visual question answering domain, because they exploit the discriminant information of semantic objects. For example, here we can see a fish object, a hand object, and a fishing pole object. Here we can see the block diagram and architecture of our method, object graphs. We assume an annotated training set of N videos and C classes. Then we perform a keyframe sampling in order to represent each video with Q frames. Then an object detector and a CNN feature extractor is used to derive K objects for each frame, the ones with the highest degree of confidence, TOC. So each object is represented with an object class label at a degree of confidence, a bounding box, and a feature vector. The feature vectors are used to construct an adjacency matrix A, which includes two transformations and an inner product of the resulting vectors, and encompasses Lenamur parameters, a weight matrix W and two weight matrices W's and two bias vectors P's. The agency matrix is normalized in order to be in the region, each element of it to be in the region 0 and 1, and also the sum of the summation of each elements at each row to be 1. So we have one agency matrix for each frame. Subsequently, the agency matrix and the object feature vectors are passed to a GCN. The output of the GCN is averaged, pulled with a respective layer in order to derive one simple local feature vector for each frame. The CNN feature extractor is also applied to the overall feature, to the overall frame in order to derive a global feature vector. These two feature vectors are concatenated, and they are passed to the sequence of the feature vectors is passed to an LSTM, which provides a single feature vector for the whole video. This feature vector is then directed to a stack of fully connected layers and provides one score for each event. The network parameters are learned via a cross-entropy loss that is using the event labels as the target labels. Therefore, the parameters of the GCN's agency matrix implicitly learn to amplify the contribution of the objects that are mostly relevant to the event. So we ask ourselves how to use the agency matrix at frame level in order to derive the object that mostly contributed to the network's decision. For this, we resort to the weighted in degree or width of a vertex, which have been used in other domains. For example, in order to assess the popularity of a person in a social media, and they are computed as follows. The width of a vertex K corresponding to object K at frame J is the summation, the aggregation of the elements of the kth column of the jth agency matrix. The object detector may detect several instances of the same object class in a frame or a video. For this, we use average widths. That is, we compute the average of the widths for each object class at frame and video level. For the experimental evaluation, we used two data sets, the YILIMET, which is a track-fit style video data set consisting of 10 event classes and approximately 2,000 videos, And the FCVT dataset, which is a large-scale multi-label YouTube video dataset, consisting of 239 classes, mostly of them real-world events, and approximately 90,000 videos. Our methods compared against the top scoring methods in the literature. Here we see the evaluation results for the FCVT and HeliMed datasets on the left and right table. We see that we have improved the state-of-the-art performance by 0.2% for the FCVT and 4.14% for the HeliMed. However, the second best method, which is ARNet, is using an efficient net backbone, which is a much stronger network in comparison to us. The equivalent method, AirNet, that uses the ResNet backbone, comparing with them, we achieve a 3.3 performance gain. Concerning the explanation results, here we see a frame from a video that was correctly recognized as a wedding ceremony. In the right bar plot, we see the objects with the highest degrees of confidences, and we see that these objects provide a general overview of the scene. For example, head, sky, people, man, woman, hair, but they are unrelated to the recognized event. On the other hand, in the middle bar plot, we see that the objects with high widths indicate the frame regions where the network focuses to recognize the event. For example, for the object couple, we see that the frame region that it focuses explains well, it's highly correlated with the underlying event. Here we see another example of a video labeled as working on a woodworking project, but has been misrecognized as a person attempting a boar trick. In the bar plot, we see that the two objects with the highest widths, video level widths, are the skate park and the skate park. So the respective regions in the video influence the most the network's decision. We also note that the wood construction roof highly resembles a skate park, as we see in the second frame here, and it is detected as such by the object detector, which explains why this video has been mislabeled. Closing my presentation, I would like to mention that this work has been supported by the EU's Horizon 2020 projects Mirror and i4Media, and our code is published available in this link. Thank you for your attention, and I will be happy to answer any questions.
Thanks so much for your nice presentation.
Thank you.
Is there any question regarding this paper? Okay, so there's also no question on YouTube channel. So thank you again, and we are going to the next paper.
Thank you.
The next paper is COCON, Cooperative Constructive Learning. Is the author with us or the president?
Yes, I'll share my screen right now.
Okay.
Awesome. Hopefully everyone can see this. Hey everyone. Today I'll be presenting our recent work, Cooperative Contrastive Learning, a self-supervised approach for multimodal video representation learning. Anyone using the internet today can appreciate the amount of data being generated, especially the massive amount of videos we've been generating. Sadly, not all of this data is usable to train machine learning models due to the lack of annotations. However, there have been recent advances which allow us to learn without the presence of explicit labels. Self-supervised learning has demonstrated how to utilize large unlabeled datasets to learn effective representation. Contrastive learning has proved to be a great framework for the same. And there are quite a few notable works that have demonstrated its use in learning good video representations. Let's quickly go over the idea behind contrastive learning. Similar instances should be represented similarly, while different instances should be represented differently. It sounds pretty simple. However, the only issue remaining is defining similar and different. Most works utilize simple rigid constraints that samples from the same video are similar, while things from different videos are different. And let's take a look at this in action. So we have two videos here, and both of these represent people doing wall push-ups. And what would happen is that instances which come from the video on the left, they'd be similar between themselves, while the ones on the video on the right are similar. However, instances from both of these, they are treated differently. And that seems intuitive because what's happening appearance-wise, the things on the left are much different than the things on the right. Let's now take a look at how we utilize contrastive learning in detail. We utilize a technique called contrastive predictive coding, which allows us to learn representations while optimizing in the data space. And what we do is we model videos as a sequence of frames and utilize this learning task in order to learn representations. And keeping this in mind, let's revisit our original motivation, that the samples from same videos are similar while everything else is different. Let's think about it. Would this be a correct assumption to make? What if the two different videos are representing the same action, or they're representing something similar? We would still discriminate between them, which means we'll try and have different representations for something which represents the same entity. And learning with such an assumption, as expected, would encourage low-level discrimination between things which ideally represent the same thing. So let's see what was happening earlier. We were treating both of these videos differently, even though they would both represent doing wall push-ups. But what we want is that both of these should be similar. The ones on the left, the instances sampled from that video, of course, they should be similar. The instances from the right should be similar, but they should be similar amongst themselves too, because they represent things, a person doing a wall push-up. Now let's take a look at how we attempt to fix this in our approach. We propose CoCon, cooperative contrastive learning, where we use multiple views of data to gain some insights regarding our instances. And then we use these insights in a cooperative manner to improve representations for all the views involved. The intuition being that instances which are not obviously discernible in one view can be in another. Now let's take a look at an example where we use multiple views of different instances. So we have an example of person doing squats. We have the optical flow information, the RGB, and the human key point information. And another example of another person doing squats, however, in a different outdoor setting, leading to different illumination and appearance. If you look at the embeddings for each of the views, we may find them embedded in a different manner. So you have the flow embeddings, RGB embeddings, and the key point embeddings. However, even though the RGB embeddings are pretty different, the flow and key point embeddings are somewhat similar for them. And this encourages the RGB embeddings to also be close by. So we use this cooperation to somewhat correct inconsistencies present in different embedding spaces. Formally speaking, our approach consists of two main components. One, independent learning of these view-specific representations, and the other is cooperation, which enforces consistency between the learned view representations. And that sort of wraps up the approach section. And now transitioning towards our results, we first take a look at the views we actually utilize for our experiments. Given our overarching goal of action understanding, we utilize RGB, optical flow, segmentation masks, and key points. It should be noted that the last two modalities are generated using an off-the-shelf detector and contain a lot of noise, but we still observe significant gains despite the prevalent noise, hinting at the robustness of our approach. In order to correctly evaluate our model, we need to take a look at three aspects: the impact of cooperation, the impact of views, and finally the performance of our model. We use UCF, HMDB, and kinetics for evaluation. We first pre-train models using the different self-supervised approaches, and then we proceed to fine-tune the learned model. So we're effectively using downstream performance and action classification as a proxy for saying that is our representation good or not. So let's first take a look at the cooperative aspect of our model. We observe our approach, COCON, leads to good performance when compared to alternatives such as single view learning and cooperation through maximizing mutual information. And this increase in performance is seen across both the views, both RGB and optical flow, the two views we were using for this set of experiments. And now that we've seen the benefits of cooperation compared to some alternatives, it's natural to think that adding additional views should improve the extent of cooperation, ultimately leading to improved performance, which is actually what we observe. We observe a consistent increase in performance across all views when using all the modalities. So random means when we fine-tune without any pre-training. CPC represents training with a single view, and COCON represents when we train with all the four views together. We notice that we notice an increase in performance even for low-dimensional modalities such as the human pose key points and the segmentation mask. And finally, we take a look at our overall model and how it compares to others. We report performance of comparable models which use similar backbones and observe that our approach is able to outperform the mentioned works. More details and discussions are present in the paper. So now we've seen the quantitative benefits, but there's still some interesting results remaining. We see that when visualizing COCON's video features, we get much more meaningful clusters as the number of views increase. We color code the action classes such that similar colors represent similar actions. And what we observe is with single view, this is somewhat the embedding space you get. But however, as you increase the number of views, you see that the colors sort of aggregate together, leading to somewhat more meaningful clusters. Another interesting feature is we see a much better consistency between the nearest classes across different views. We also note that the nearest classes suggested through these approaches, especially through COCON, are much more meaningful compared to the single view variant. And finally, we observe that we're able to perform some form of soft alignment between different video clips. The heat map on the right highlights similar regions and associations that we are able to infer using our learned representation. This wraps up our talk. Please feel free to check out our paper for more details and our GitHub repo to check out the code and results. Let me know if there are any questions.
Thanks so much for your nice presentation and your nice job. So is there any question regarding this paper? Actually, you can also continue asking questions in chats if you miss the question answer of any paper. Okay, thank you again. And we are going to go to the next paper. The next paper is...
Sorry, Mohsin. I think that there's a 30 minutes break right now. It's between 2:40 to 3:10. We have a 30 minutes break, and then the session starts in 30 minutes.
Yeah, but we have some other papers. Can we?
So I think that we should stick to the plan that we have, and then we have like a 1 hour block for the oral session too, and then we have the whole schedule, right?
Okay.
Yeah,
Okay.
based on the program online, there is a 30-minute break between paper 6 and 7.
So I would suggest, like, if you guys want to stay and get to know each other, we can utilize this time of chit chat and getting to know each other. Otherwise, we leave the session open and we connect in 30 minutes from now. Okay, guys, then see you later in 30 minutes.
Hey, Vivek.
Hey,
How was the break?
I got some food.
Cool. Yeah.
Just on time, so that's great.
Okay, I started the recording. Actually, I resumed the recording. And let me see if we are, yeah, we are also live on YouTube. We're back. And so just wait for some minutes, everybody gets online. Okay, I think we should first start the second oral session, and then we will go to our speakers. Okay, let's see, there are some people joining. Okay, I'm going to start. Is the presenter of the next paper with us now? Yeah, okay. So, welcome back, everybody. I hope you enjoyed your break, virtual break. And the next paper is learning to segment actions from visual and language instructions via differentiable weak sequence alignments. The presenter is with us, and yeah, the stage is yours.
Okay, so can you see my slides?
Yeah.
Okay, so hello everyone, I'm Yuhan Shen from Northeastern University. I'm going to present our work on learning to segment actions from visual and language instructions with differentiable weak sequence alignment. This is a joint work with Lu Wang and Ethan and Hanfa, and this paper was also presented at the main conference of CVPR 2021. So our goal is to address the problem of unsupervised action segmentation in instructional videos. Instructional videos are tutorial videos that teach you how to perform tasks, such as changing tire. To accomplish a task, we need to execute a sequence of task-relevant actions, referred to as key steps. The goal of action segmentation is to localize those key steps in videos. In instructional videos, visual demonstrations are often accompanied by narrations, which describe the actions. Therefore, narrations can be used to more effectively segment the actions. Most prior works in unsupervised action segmentation only use visual data. Therefore, they cannot use the rich information from narrations. A few prior works also use narrations. Some works assume temporal alignment between the key steps in two modalities, but this is often violated because one may describe the one or few key steps before or after performing them. Besides, most works use pre-computed features and don't have the ability to do feature learning. To address these limitations, we propose a new framework to simultaneously learn from visual data and narrations. To do so, we develop a soft-ordered prototype learning module to extract key steps from both modalities, and also propose a new class of sequence alignment methods. Our key observation is that the sequences of visual and linguistic key steps are weakly aligned. The key steps in two modalities may not be temporally aligned, but the order of them should be similar. And here, weakly aligned means that they don't have to be the same. Some key steps may only be present in one modality. Besides, we take advantage of the weak alignment to perform self-supervised multimodal feature learning to improve performance. We propose two soft-ordered prototype learning modules for visual data and narrations, which learn a sequence of visual prototypes and a sequence of linguistic prototypes in a joint embedding space. Here, each prototype represents one key step in the format of a video segment or verb phrase. We assume that the two sequences are weakly aligned, so we propose a new differentiable weak sequence alignment loss to find the one-to-one alignment between the two sequences. while allowing some items to be unmatched. We minimize the distance between aligned pairs to learn better features and better prototypes. After feature learning, we can assign each video segment or verb phrase into one prototype based on the distance between the video segment and the verb phrase and the prototypes. Then we can get the segmentation of the videos. To illustrate how DWSA works, let's first consider a simplified case of two symbolic sequences. Suppose we want to find the weak alignment between them. The first step is to insert empty slots in either sequence to allow unmatched items. Then step 2, we compute pairwise alignment cost between the two sequences using a preset cost function. Then step 3, we run dynamic programming to update a cumulative cost matrix. After the whole matrix is updated, we can get the total alignment cost. We can also get the alignment path by backtracking. To extend to more general cases, we use a continuous distance function between the prototypes as the alignment cost. We also replace the minimal operation with soft min to make the loss differentiable and derive the backward propagation algorithm. We compare our approach with existing unsupervised methods on two data sets of ProCell and crosstask. Overall, we improved the state of the art by about 4.7% on both data sets. We also replace our DWSA loss with soft dynamic time warping loss, which is a classic sequence alignment loss, and it leads to much lower performance. That's because dynamic time warping has strict matching requirements and doesn't allow unmatched items. We also evaluate step detection, where a model has to only detect a single frame for each key step in each video. The goal is to detect the most distinguishable frame for each key step. Our approach outperforms all unsupervised baselines by at least 6%. We also achieve comparable performance to two weakly supervised methods, even outperforming one of them. Finally, we show the qualitative results of the alignment between the visual prototypes and linguistic prototypes before and after feature learning using our DWSA loss. Before learning, the model can hardly find meaningful alignment between the two modalities. After learning, more aligned pairs of the verb phrases and the video segments refer to the same actions, hence improving the performance. That's all of my presentation. Thanks for your attention, and I'm happy to take questions.
Hey, thanks so much for your nice presentation. So let's see. We don't have any question from the YouTube, but so we have a question from the chat. Ehsan has asked the first question is, how do you make the dynamic programming step differentiable to use in your model optimization?
Okay, so because we in dynamic time warping, there is a minimum operation, and we use a soft min to make the minimum operation differentiable, and that's why we can make the dynamic programming loss to be differentiable.
And
the second question is also answered now. Yeah.
Okay. Yeah, I was checking.
Thank you.
And I felt that you got the answer. Okay.
Okay, thank you.
Thank you. So we're going to the next paper, paper number 8, training vision transformers for image retrieval. The presenter is with us. The stage is yours.
Hi, can you hear me and see the slide?
Yeah.
Okay, perfect. So today I'll present the training vision transformers for image retrieval paper. This is work with a collaboration with Natalia Neverova, Ivan Laptiv, and Hervé Jougou from Facebook AI and EMEA. So in this work, we mostly focus on image retrieval, but all the methods and maybe the insights we have in this paper can possibly potentially be directly extended to video with maybe different transform backbone like Vivid or Transformer. So in this paper, we mostly think about two tasks for retrieval: category level retrieval, where we have a query image and to find all other images with the same semantic category. So this task is in zero-shot setting. So like with the data sets are split disjointly with the conditional classes. So like the training set and testing set have completely different categories. And in this work, we use the Stanford line products, CUB and InShot. But also we focus on the more classical retrieval problem of like instance retrieval between images of the same instance, like typically landmarks in different viewpoints and conditions. And it's also zero shot. So training is done with like Google landmarks or the structure for motion data set, and testing happens on the Oxford and Paris data sets. So the more standard retrieval pipeline, so we have an encoder. In recent years, typically it has been a convolutional encoder like Redmond 50. Afterwards, the encoder outputs some feature maps of some resolution, for example, 7x7 feature maps. And we need to have a global image descriptor to describe this image. So for category object retrieval or category level retrieval, we have simple pooling, like max pooling, average pooling is typically adopted. And for the particular object retrieval task, more advanced pooling like generalized mean pooling or RMAC can be adopted. Finally, we have an objective function to train these descriptors to learn about the notion of similarity and dissimilarity, and they can come with different flavors like classification-based objective functions or pair-based like contrastive loss and neighborhood component analysis. So in this paper, we touch on each of those components. So for the encoder, our main question is to study the transformer encoder instead of convolutional encoder, and in particular, we study the D8 small model. For the descriptor, we don't do pooling, and we study how the class token and transformer can be used as a global image descriptor and how it does. And finally, for the objective function, we use the contrastive loss, but we also study and propose a differential entropy degradation, and we'll touch on each item. So I think in the workshop, like many people have to mention transformers, so I'll try not to talk too much about this. The important point I want to mention is that to be in fair, we use the D8 small model that has comparable number of flops and number of parameters as Resident 50, and maybe with a little bit more accuracy on ImageNet. And this will be the main comparison between D8 small and Resident 50 across the paper. So this is like overview of our method. We use the Siamese structure or setup. We have like two images. They will be broken into batches, and each batch would be linearly projected into patch embedding. And then we add a class token at the input, and then we pass through a vision transformer, of course, sharing weights because it's Siamese setup. And then finally, the class token in the output will be used as the global image descriptor. And then we learn with contrastive loss and differential entropy degradation. So let's talk about one item at a time. So for the descriptor, pooling has been the most adopted method for since we're using convolutional features. But however, the class token has more capacity to learn. Since the class token in the beginning, it has across all the layers of the model, it has access to all the patch features of all the image globally from the beginning to the end. And you can think of it as it's a feature where you can read from all the image features and write to itself across all the layers, aggregating it such way it has way more capacity to learn something maybe non-trivial compared to maybe a more simple pooling operation. And then empirically, we can notice that across both tasks and across all data sets, we can see that indeed the class token has superior performance across all tasks compared to even to GM and maybe other pooling methods. And the next question is that are actually transformers in the first place good metric learners? So to do this, we compare a D8 small model with Resident 50 for using 3 different metric learning methods. And we intentionally used 3 maybe different flavors of metric learning objectives, like normalized softmax, which is more like a classification method, a scalable neighborhood component analysis, which is more pairwise or instance-wise, but with soft weighting of the negatives and positives, and then contrastive loss with more hard weighting or hard negative mining. And across all methods, DIT small has clearly better performance, which maybe enhances our intuition or confirms our intuition that transformers are good metric learners in general. Just like to mention, the contrastive loss that we adopt in the rest of the paper is the flavor with the cross-batch memory, so that we don't have only the negatives from the batch that we have, but also from momentum encoder, and that we save in a memory bank or memory queue, similar to maybe Moku, and also like the CVPR2020 paper from Wang and a collaborator that's doing this. And it's have very strong performance with maybe very basic contrastive loss. But now we can maybe quickly revisit the contrastive loss. So we have the positive term, which tries to maximize the cosine similarity between positive pairs, and also the negative portion that minimizes the cosine similarity between negative pairs. But also we're only interested in the negative that are hard and confusing, that we have a more consistent training signal. That's why we have a margin. And on the right, we look at the mutual information setup. So intuitively, we want to maximize the mutual information between the representation and the label, such that to do this, we can minimize the entropy of the representations if we know the label. So if there's the same label, we want all representations to be similar. Otherwise, we want the representations to have high entropy. And we can actually factorize the contrastive loss with the same point of view. So the positive term corresponds to the conditional differential entropy. When we have the label, we want everything to be agreeing, while we don't know the label, or that the label is different. We want all the representations to be different. And to notice, and also maybe to study this, we study here a resonant safety model. And the resonant safety model, we can see that before any training, so if we just get the ImageNet features and use it for the retrieval task, we can see that all the principal components have a high contribution in the representation. And here we're like showing the cumulative energy from PCA. So all the components have contribution. But after training with like a vanilla contrastive loss, you can see a very strong collapse in dimensions. And only very few dimensions have maybe high contribution. But then if we add regularization from differential entropy, we can see that this enhances. So here lambda is like a gradation coefficient for the regularization. And here we just use the Collier differentiable entropy estimator as a way to do this. And we can see as we increase the lambda, more and more components and more structure of the code is used. Afterwards, we can maybe skip this part. Like we can just show that this small model has more naturally robustness to this collapse phenomena compared to the resonant model. And we see that empirically, we can see a consistent improvement for the results across both architectures and across all hyperparameters using this regularization. And the same here, we see for the distribution of the cosine similarity and the range of all the distances, we can see with the entropy regularization, we have better separation. Also, we take more range of the cosine similarity, which helps with thresholding and so on. Finally, with the results, we achieve state-of-the-art compared to all other methods for category level retrieval. And more impressively, I think, even with the compressed version with only 128 dimensions, we beat all the previous methods with the exception of one that uses much higher dimensionality. And for particular object retrieval, it is also the case. However, in the table below, say that the state-of-the-art convolutional networks still are the state-of-the-art, because for particular object retrieval, we need to use high resolution images, while transformers struggle with this due to the quadratic complexity. And the final slide, we just want to mention the recent work that we had from a week ago, Excite, which actually addresses this problem of quadratic complexity and offers a transformer model with linear complexity in the image size. So thank you, and please questions. Sorry for being too long.
Thanks so much. And it was nice that you also had added this recent work in your slides. Okay, is there any question regarding this nice presentation? So we don't have any on YouTube channel, and I don't see any questions in our Zoom chat. Okay, thanks so much again.
Thank you.
Thank you. So we are going to the next paper number 9. On identified video objects, a benchmark for dense open world segmentation. So is the presenter with us?
Yeah, I'm here. share screen. Can folks see my screen right now?
Yeah, we can see your screen.
Okay, cool. Let me start the presentation. Yeah, so today I'll introduce about our work called Unidentified Video Objects, a benchmark for dense open world segmentation. This work is done by Matt, Heng, Du, and I from Facebook AI Research. So first, I'd like to introduce a bit about the motivation, right? Why we are introducing a new benchmark. So if we look at the current state of the art detectors, they work very well under the closed world assumption, which basically means they are very good at detecting the in-taxonomy objects, the objects whose categories are inside your training data. However, real world is open. So in real world, we may see lots of objects that are outside your training data or outside your predefined taxonomy. So if we look at the cases on the right, we can see that this is just a very normal real world scenario where someone is exercising inside the gym. But both the state-of-the-art Mascar scene, trained with 80 code categories, fail to detect most objects in this scenario. And if you scale up your taxonomy, we use Google Cloud API, which is supposed to detect more than 550 objects. It still failed to detect most objects in this scenario. And if you look at the Mascar scene example, it even detects something that is not actually an object. For example, like it detects some part of the background as a refrigerator, or detect part of the barbell as a parking meter. However, we also have the intuition that humans can handle open world pretty well. Humans can have the concept of unidentified flying objects like UFO, but we don't even know what that is. Possibly with Cusack motion, humans are able to detect things or without even recognizing what they are. So the question we try to answer with this data set is that how can we get from the previous slide to something like this? Before I jump into the data set details, let me first ensure you guys that this is a valid problem. We first argue that open world is actually very difficult. So the more than typical deep learning based methods are very top-down driven. For example, the RCN families, they can achieve state-of-the-art performance, but they typically rely on strong contextual cues and they couple recognition and detection, which means that not only, before I actually detect this object, I need to know what it is, and then I make the proposal to detect such an object. In this example, the detector may fail substantially when there's no contextual cue of a person near the skateboard when it's trying to detect the skateboard. On the other hand, if you look back, there are lots of classical approach that are bottom up. Examples like superpixels or voxels. They're non-parametric models, so they are agnostic to your training data. They won't be biased towards specific classes in your training data. However, they offer inferior performances, and also they have no notion of semantics, so you need to rely on tools such as selective search to construct object proposals. So we understand that the problem is difficult, but why we are trying to solve? If the problem is difficult yet low impact, it's the type of problem we try to avoid. We think open world is very important. First, the ability learning to segment the open world will give you ability to handle novel or what we call unseen objects, objects that are not seen in your training data. This is very crucial to applications like embodied AI, such as robotics or autonomous driving. On the other hand, if you are able to segment all the objects presented in a video or an image, this enables the holistic understanding of image and video, which ties really nice to the theme of this workshop. If you are able to segment all the objects, you can do object-centric reasoning. And by reasoning on top of the objects instead of on pixels, you can scale to arbitrarily long video, which enable long-term video modeling as well. So with such idea in our mind, we present this data set. I identify the video objects to study the open world. So what a data set, open world segmentation data set requires, right? We want to exhaustively annotate all objects presented in the video. and it ought to be taxonomy free. Means that we don't first define a list of object categories to segment. Instead, we rely on the annotators to bottom uply spot objects and annotate them. So you will satisfy this requirement where all objects presented in a video are segmented. And we have two splits of UVO right now. First is that their videos are densely annotated at 30 FPS. There are more than 1,000 videos annotated in this way. And second, we also provide a sparse split where we annotate approximately 9,000 videos at 1 FPS. On average, there's about 17 unique object instances per video. Let me put this number in context to compare with previous data sets or related data sets. Previously, when people work with video segmentation, we rely on awesome data sets like Davis, U2VOS, and U2VS. But as we can see from the taxonomy, they rely on a certain taxonomy. For Davis, it's more like about salient object or moving objects. For VOS and VS, they rely on fixed predefined taxonomy. In addition, the objects per video for this previous data sets are much smaller, like 10 times smaller than our data set, which simulates more of a real statistics of the open world. So objects are very dense in real world, but they were not actually captured by previous data sets. And to put the total mask annotation we have in context, in total, combining the dense and sparse set, we have more than 1 million mask annotations in total in this data set, which is on par with the popular image instance segmentation data set, COCO 17. So recap of what we have right now, most current state-of-the-art method focus on the closed world setting, where you have a predefined taxonomy during training, and you try to detect objects only in the taxonomy. However, open world segmentation requires you to detect all objects, and it is essential for us to enable object-centric reasoning or long-term video understanding beyond reasoning on pixels. We believe open world video object segmentation is very hard, so we encourage folks to compete in our UVO challenge at ICCV this year. I'll try to take questions right now, but I'll play this video so to give a sneak peek of UVO. Cool. So folks, if you guys have any question, feel free to ask me right now. If not, I'll just play this video and we can wrap it up.
Is there any question regarding this paper?
Cool. So I guess I'm done. Again, please consider participating in our ICCV challenge this year. And for more information, please search our paper on arXiv. Thanks a lot.
Thank you. There's just one question on YouTube channel. Someone is asking new number of object classes. This is not just the question.
Yeah, so when we design the data set is annotated in a class agnostic fashion. So we don't have a predefined list of categories. However, we do plan to provide class label for the 80 COCO categories. And for anything not belong to COCO categories, we'll annotate them as something like unknown or non-COCO.
Okay, thank you. So we're running out of time. We should go to the next paper. Thanks again. The next paper is learning video representations from textual web supervision. I think the presenter is with us. Yeah.
Yes, 1 second.
Always.
All right, okay, that's visible.
Yeah.
Okay. Great. Okay, hello everybody. My name is Jonathan Stroud, and today I'll be talking about our work on learning video representations from textual web supervision. This work was done while I was an intern at Google and a student at the University of Michigan, and was done with collaborators from both Google and Princeton. So to start, let's consider how we learn video representations today. The prevailing paradigm for many years has been to train video models on large amounts of labeled data. Usually this involves first collecting a lot of videos from the internet, then labeling each video with a category or class label. We then train the model to perform classification and transfer the backbone model to other tasks. The issue, of course, we know is that these labels are very expensive. Data sets like kinetics that have hundreds of thousands of clips can take tens of thousands of human hours to label. So as we look forward to creating the next generation of video data sets, it's clear that we can't just scale up this process forever. So let's take a closer look at the first step in the process. We can collect videos from the internet by searching for them online. So what happens when we search for a video on the internet? So we observe that search results on the internet already do a pretty good job of labeling the videos for us. So if you search for rock climbing on YouTube, you get rock climbing videos. This is made possible by the metadata which is attached to each video, such as the title and the description, which make references to the video content. And in many cases, it's not actually necessary to do any human labeling. So in addition, you'll find that videos on YouTube come with lots of rich information that goes just beyond the term that you search for. So along with the video title, we can look at the name of the channel which uploaded the video. We can also look at the description, which contains lots of important keywords, or we can look at user-defined tags, which are available but not visible in the interface. We propose that this metadata can be used as the supervision signal for training video representations that are both powerful and generalizable without any need to manually annotate class labels. So specifically, our contributions are, first, we collect a large-scale data set with 70 million video clips and over 22 years of video. Second, we leverage rich supervision from the text data to train video representations. Finally, we show that this improves accuracy on downstream tasks. So starting with the dataset collection process is straightforward. First, we collect a list of search terms, which cover lots of common human activities. Then we search YouTube for each term, and we collect the top 100,000 videos from each set of search results, along with their associated metadata. And we select a 10-second clip per video. For the search terms, we use the Kinetic 700 action categories. But conceptually, you could use any set of search terms that you like. This results in a data set with 70 million videos, which is over 22 years long. There's no human labeling required to repeat any part of the process other than choosing the search terms. So for each video, we collect 4 pieces of textual metadata: the title, the channel name, the description, and the tags. We encode these with a pre-trained BERT checkpoint and average pool over the tokens to get a representation. We then use a 3D CNN to encode the video frames and produce a video representation. We train the video representation by making it match the fixed metadata representations. This is accomplished by using an additional prediction head on top of the video embedding, which is fed into a ranking loss. When we want to use multiple pieces of metadata, we can use multiple embedding heads to predict the representation of each type. In this case, we use multiple ranking losses, and each are assigned an equal weight. Okay, so now moving on to results. We first look at 2 versions of our model, one which uses only the titles and one which uses all of the metadata. For each, we train the model at increasing dataset sizes to see the effects that the size has on performance. We find that our model continues to benefit from more data even at extremely large dataset sizes. When using 70 million videos, we achieve an increase of 10.1% on HMDB 51 compared to MIL-NCE, while also controlling for the backbone architecture. Surprisingly, we find that the titles-only approach outperforms the approach which uses all forms of supervision, but only at large scales and not at relatively smaller scales. Okay. At the relatively smaller scale of 500,000 videos, we show that each metadata signal individually can be used to pre-train a model, which is better than training from scratch. Titles are the best individually, but we do see complementary benefits when we use multiple pieces of metadata at the same time. So we ask, why is there a different behavior at small versus large scales? Like, why do we see complementary benefits at small scales but not large scales? So one possible explanation is that the statistics of these metadata signals change as we grow the data set. So with our data collection process, collecting a large data set necessarily means including more low-ranked search results in the data set. And these low-ranked videos have quantitatively shorter descriptions, fewer tags, and longer titles than those at high ranks. So they're clearly different. But we can also speculate that these metadata signals might just be too noisy relative to the high-ranking signals to be useful at large data set sizes. So this finding demonstrates the one really important challenge of collecting web scale videos, which is that video quality degrades as we grow the data set. So not all videos are created equal here. So here we compare our approach with two similar approaches, AVTS and MIL-NCE, which use large scale video data without class labels to learn representations. We find that our approach performs significantly better on two downstream action recognition tasks, HMDB51 and UCF101. And this is controlling for the same backbone model as MIL-NCE. When we switch to a more powerful R3D50 backbone, we see another large jump in performance. We also compare with several unsupervised approaches on Kinetics 400 and 600 and find that our model outperforms these methods when using the standard evaluation setup, which uses frozen embeddings. We also demonstrate that our model outperforms a baseline with unfrozen embeddings, but here we only have a comparison with training from scratch. So finally, we show that WTS 70 million can be combined with Kinetics to achieve even better performance on downstream tasks. So for this experiment, we pre-trained the model in two stages. First, we train on our unlabeled WTS 70 million data, and then we train on the labeled Kinetics data. The resulting model is then fine-tuned on the target task, HMDB51, and we can show that increasing the amount of supervised training data further increases the benefit. So this indicates that our method is complementary and not in competition with existing supervised approaches. So to recap, our contributions are: first, we propose a large-scale data set for webly supervised learning. Second, we propose to use the text metadata in that data set as a rich source of supervision. And finally, we show that this approach leads to improved accuracy on several downstream tasks. So yeah, that's all. Thanks for listening, and I can take questions.
Okay, thanks for your nice presentation. We have a question from the Zoom chat. Dima has asked, did you do any random checks to the quality of the data? Out of 1,000 videos, how many are relevant to the text in the caption?
Yeah, so we don't do any quantitative analysis here. I mean, anecdotally, I'd say there is a lot of noise in the data set. You know, we show some examples in the paper and the supplementary of like some examples of good and noisy samples from the data set, but I don't have a good estimate of the proportion that are relevant to the search term. I think one of the advantages here is that even if the search term isn't relevant to the video, hopefully the description or the title or some piece of metadata is.
Okay, thank you. So is there any other questions? Okay, so thanks so much again. And
yeah, thank you.
We're going to the next paper. The next paper is parameter efficient multimodal transformers for video representation learning. Is the author with us or the presenter? And one just quick note to our attendees from the YouTube channel, please ask your questions in advance because there is a small latency in broadcasting on YouTube.
Hello, can you hear me?
Yeah, sure.
And can you see my slides?
Yes, clearly.
Okay, thank you. Hello, everyone. I'm Sang-Ho Lee from Seoul National University Vision and Learning Lab, Seoul, South Korea. And today, I'll be presenting parameter-efficient multimodal transformers for video representation learning. Our goal is to learn from unlabeled videos by leveraging audio-visual correlations. And as a solution, we train multimodal transformers in a self-supervised manner. Multimodal transformers have been widely used in vision and language tasks. However, due to the large memory requirement of transformers, they rely on pre-trained components such as language BERT. But the problem is, we do not have any pre-trained components in the task of audio-visual representation learning. Thus, we need to train models end-to-end, and so we need to reduce the model size. In this work, we propose a first end-to-end trainable audio-visual transformers by using a novel parameter reduction scheme. And we propose a novel content-aware negative sampling for contrastive learning objectives. Our model achieved competitive results on visual-only, audio-only, and audio-visual downstream tasks. First, let's talk about our end-to-end trainable model. Our model has two modality-specific transformers and one multimodal transformer. Visual and audio transformers each model dynamics of each modality, and multimodal transformer jointly learns audio-visual dynamics. To train our model end-to-end, we aggressively reduced the number of model parameters. Our model originally has 128 million parameters, and by using our scheme, we can reduce it to 4 million without performance drop. And this results in up to 97% parameter reduction. Then how can we do that? Based on rolled out recurrent neural network mechanism used by recent transformer work, Albert, we can share the parameters across layers. This reduces the number of parameters up to 21 million. Furthermore, we may share the parameters across all modalities to the extreme cases. However, it restrains from modeling different dynamics of each modality. So, we instead perform low-rank factorization and keep parts of decomposed weight separate for each matrix W, sigma and V here. And so, we model different dynamics of each modality while reducing the model size most. Using this technique, we successfully trained our model end-to-end and demonstrated the validity of our scheme on an audio-visual classification benchmark called kinetic sounds. Our method achieved comparable or slightly better performance than any other parameter reduction schemes while reducing the model size most. We could not train the no-sharing model because that model cannot be loaded on even on a single Titan V100 GPU with 4 input sequences. Next, we propose a novel negative sampling for the self-supervised learning task, masked embedding prediction. The goal of masked embedding prediction is to identify the correct masked input compared to a set of negative samples. In the MEP task, composition of the negative set is highly crucial because it has a large impact on the learning dynamics or the complexity of the task. We basically sample negatives from the current mini-batch, but if we take only 2 easy negatives, we cannot learn useful information from the task. On the contrary, if we take only 2 hard negatives, the convergence of model is too slow. To address this problem, we propose a novel sampling technique called context-aware negative sampling, content-aware negative sampling. We first compute the distance between the CNN feature of target input xt and that of every sample xi in the mini-batch. We then sort samples in ascending distance order and keep only the middle 95% of samples. This eliminates two similar or two dissimilar samples compared to the target. We then stochastically choose negative samples based on the similarity. The stochasticity allows us to ensure the diversity of negative samples while favoring hard negative samples. And this makes the MEP task effective. Experiments on kinetic sounds demonstrated the efficacy of content negative sampling. It achieved better performance than sampling only hard negatives from the same sequence, or sampling too many easy negatives from the whole mini batch. Also, we investigate three modality fusion strategies: early, late, and mid fusion. The early fusion uses a single multimodal transformer with 12 layers, and the late fusion uses two unimodal transformers, each with 12 layers. The mid fusion uses two unimodal transformers, each with L layers, followed by a single multimodal transformer with L layers. Experiments on kinetic sound shows that the mid fusion strategy achieved the best performance. Since the model with the early fusion cannot take audio only or visual only input, and the model with the late fusion has poor performance, we use the mid fusion as architecture. Lastly, experimental results on several downstream tasks show the versatility of our model. It achieves competitive results on various downstream tasks. In summary, we proposed the first end-to-end trainable audiovisual transformers by using a novel parameter reduction scheme, and we proposed a novel content negative sampling for context learning objectives. And our model achieved competitive results on various downstream tasks. Thank you for listening.
Thanks so much for your nice presentation. Is there any question regarding this paper? Okay, so yeah, there's no questions regarding the paper. Thanks again.
Thank you.
So we're going to the next paper, and the final paper, Just Ask, learning to answer questions from millions of narrated videos. And so is the presenter with us? Yeah.
Hi, can you hear me and see my screen?
Yeah.
Okay, great. So I'm Antoine Yang. I'm delighted to talk to you about our recent work, Just Ask, learning to answer questions from millions of narrated videos. This is a work we've done at INRIA Paris with Antoine Mich, Joseph Sivich, Ivan Laptev, and Cordelia Schmid. Video question answering is a promising proxy task to evaluate video understanding because it can be easily evaluated with a metric like accuracy, and because it involves all sorts of different computer vision skills, such as recognizing actions, colors, objects, and this at different spatiotemporal granularities. This is also what makes it difficult. Deep learning models to tackle this task require lots of training data. However, obtaining manually annotated video question answering data is expensive and not scalable. In this work, we tackle this issue by automatically generating large-scale video question answering data from narrated videos directly, relying on language models trained on text-only annotations. We show how video question answering models can benefit from such a data by tackling this task without any manual supervision of visual data in a setting which we denote as a zero shot, or by fine-tuning our pre-trained model. We rely on a weak supervision scheme. We make use of narrative videos which contain natural speech, which makes our approach scalable. And the weak correlation between the visual content in narrative videos and the speech has been shown to help on various tasks in previous work, such as text video retrieval or action recognition. for our generation pipeline, we also rely on language models that are trained on a text-only annotations. So we make use of a manually annotated question answering text corpus, SQUAD, to train 2 language models, an answer extractor transformer and a question generation transformer. We argue that this manually annotated question answering annotations are easier to obtain than video QA annotations because it doesn't require anyone to watch a video, etc. In detail, our pipeline takes as input raw narration together with the video and automatically outputs video clip question answer triplets. It leverages the previously described question generator and answer extractor models to generate, given the speech, a question and an answer. And then we also make use of a sentence extractor that helps to make a unit of sense out of the raw narration, which is completely unordered originally. This sentence extractor is also used to extract a start time and an end time for the output video clip. Applying our pipeline to the videos from the How-to-100M dataset, we obtain and generate the How-to-VQA69M dataset, which is made with 69 million question answers, about 1 million videos. I show you just a couple of examples of annotations below. So with the input speech that is given to the question generation and models, and the generated outputs. So as you can see, there are a couple of examples that are pretty good, like the one on the right. Meaning, by good, I mean where the video helps to answer the question and the question and answer makes sense. But there are all sorts of noise in How-to-VQA69M. So as shown in the second examples, there are lots of examples that are also incorrectly generated because the question answer generation procedure is automated, and also because of the speech isn't a very curated data. Also, the speech doesn't always describe the video content, which is why there are some samples where the speech isn't related to the video, and the question and answer as a result aren't related to the video either. For our experiments, we use a video QA model that is made up with a video question transformer and an answer transformer. We train it with a contrastive loss where the negatives are sampled with the different answers in the batch. And we also use a masked language modeling loss for regularization. For evaluation, we manually collect a new video QA evaluation benchmark, which we denote IVQA. Its particularity is that it contains multiple ground truth answers for each question, such that we have a more fine-grained evaluation. So our first evaluation setting is the zero-shot video QA task. So we compare to a couple of baselines. So our video QA model, which we denote VQ80, is pre-trained on How-to-VQA69M. We compare it to its language-only variant, Q80. And we also compare it to a variant of the same model pre-trained on How-to-100M with a standard pre-training approach. So as shown with the quantitative results below, our model outperforms these two baselines, showing first that the point of the visual modality in the generated How-to-VQA69M, and also the advantage of task-specific pre-training over task-agnostic pre-training on How-to-100M. I'm now showing you a couple of examples of zero-shot video QA results. So as shown on the examples below, our model compared to the two other baselines has a better multimodal understanding and makes a better use of the visual modality compared to the two other baselines. I'm maybe gonna let a little bit these examples. And to finish, I'm just showing you the results after fine-tuning of our video QA model. So after fine-tuning, we find that our model outperforms the state-of-the-art on 4 different video question answering datasets: MSIVD QA, MSVD QA, ActivityNet QA, and How2 QA. So to sum up, we automatically generate a large-scale video QA dataset, How2 VQA 69M, using text-only annotations and unarrowed videos. And we show that our video question answering model highly benefits from training on this data. First in the new zero-shot video QA setting, and also after fine-tuning. So that's it for me.
Thanks so much for your amazing talk. And so, is there any question regarding this presentation? No, we don't have any questions on our YouTube channel, and also I don't see any questions in our Zoom. So thanks so much for the presentation. Yeah. Okay, I think we are done with the paper presentations, and the next talk is from Carl Vondrik from Columbia University. He's now with us, and he's usually on time. Yeah. Okay, Carl. Yeah, the stage is yours.
Okay, great. Let me share my screen. Let's see. Okay, my slides are all visible and everything. And let me pull up the chat. I'll try to monitor the chat too. Yeah, thanks everyone for joining, especially on at the end of the conference and on a Friday night or Saturday morning, depending on where you are in the world. I'm going to talk about some work that we presented just yesterday at CVPR. It was presented at a bad time. It was presented at 4 in the morning for us. So I wanted to advertise a little bit here. And this is a project that, we just started working on this because we found it intrinsically interesting. We didn't really know where this would go. But we kind of just got interested in this and excited about the technique, and we started to explore it. And it led to something really cool that I'm very excited about. And I really think this is a big step. And right now the really common task in video research and self-supervised learning is basically about trying to predict the future. This is taking over the field somehow. This is everyone's working on this problem. Like, can you predict whether it's in video or in images or in language or in speech, right? Can you learn some model that can predict what is going to happen next? And we often hear from neuroscientists that the human brain is a predictive map, right? We're always trying to predict what's going to happen next. So we watch a video like this, and what do all these predictive models do? Is what we try to have it solve some for multiple choice tests, right? What are they going to do next? And maybe it's actually a test here on the Zoom chat. What does everyone think? What is going to happen next? Are they going to A, handshake, B, kiss, or C, hug? One vote for B. So it's pretty obvious, right? It's pretty obvious that, hey, these three gifts, and we're pretty good at this. We're pretty good at predicting the future. You're not predicting meetings can happen next. We're not bad, right? Here's another example, right? Watch the video carefully. What are they going to do next, right? Is he going to sit down? Is he going to jump, or is he going to dance? Oh yeah, okay. There's some debate here in the chat, but yeah, he's gonna sit down. There's no trick question here. It's not always this easy though, right? When you watch this clip, right? What's gonna happen? What's gonna happen here? Are they gonna handshake? Are they gonna high five? Are they gonna eat? You can't say, right? I actually don't know the answer. The answer is in season 2 of The Office. So if you really know the answer, you got to go watch the Office. And this problem basically doesn't make sense in predicting here, right? It doesn't make sense to try to predict what they're going to do from these options. The problem is not solvable if you're forced into these 3 choices. Now, I think all of us here, we're smart people, and we know these are not the only 3 options that there could be. If I told you have to tell me a sentence, what are they going to do next? And you say, no, I'm not restricted to these options. Just tell me in plain English what is going to happen next, right? Probably what you would do is you'd want to hedge your bet, right? You wouldn't be restricted to just A or B. You would hedge your bet. You'd predict an abstraction, something higher level, saying, well, they're actually going to greet each other. And so this is a project that 2 PhD students in my group, Didek and Rishi, started working on last year. Is how do you build these predictive models that can basically hedge the bet, rather than being restricted to the features or the categories that we define for some task? Can we build these predictive models that actually can predict an abstraction, can say what can they be as confident as they possibly can be, but not in anymore, right? And just figure out what is the predictable structure in a video. So to motivate the approach here, I want to first talk about how most of these predictive models work. And this is something that everyone learns in kind of machine learning 101, but I think it's worth reviewing here, because it's actually going to motivate the approach that we're going to take. So in any predictive model, your typical setup, right, is that you have some observation as your input. This might be the red frames, right? You observe the path, the red frames here. And you want to predict something about the future. You want to predict the unobserved blue frames in the future in some embedding space. And usually this is some Euclidean embedding space, right? And the problem with this, and the problem with all these approaches is that, well, there's actually uncertainty here, right? There's not a single, blue point in the future that could happen next. There's actually a distribution of several different points that could happen next. And so when you train these predictive models with just some regression loss, right? What we all know is, well, you get the regression to the mean, right? If there's any uncertainty with any type of regression, then rather than predicting one of the points on the manifold, right, you just regress all of those together and get the average, which often is meaningless. It doesn't have any meaning, right? There's no meaning to it. And so there's a variety of approaches in predictive modeling. And this is what makes the problem interesting in some ways. And there's a variety of approaches being developed trying to overcome this problem, right? GANs are one way. A lot of work trying to use GANs, right, to force the predictions to at least be on the manifold. There's a lot of work in probabilistic models too. How can you, rather than making a point estimate, can you actually estimate the full distribution of the future? And so this is a really active area of research, trying to build these predictive models and trying to overcome this problem where you get regression to the mean. So we started thinking about the same problem here. And we started thinking, maybe this actually isn't a bug. Maybe regression to the mean actually isn't a bug. This actually could be a feature. And the fact that, basically when you regress to the mean, you're somehow hedging your bet, right? This is maybe a good thing, right? You don't know what's going to happen, so you want to predict, you want to hedge, you want to predict the abstraction. And so this is what I'm going to tell you about here is an approach that actually is going to, rather than trying to fix this problem, it's just going to embrace this problem as a good thing, and use regression to the mean as a way to form abstractions for prediction. Now, to do this, though, I have to talk about a topic that often makes undergraduate students cringe and really, they run away when you start talking about this. But it's super exciting, and this got us very, very excited about this. And we got to go back to very basic things, right? I mean, I think in computer vision and machine learning, we have this problem of citing papers from just last year. We need to go back thousands of years, basically, to go fix this problem. So I'm probably not citing all those Feld's paper in CVPR here, right? But if we're going to try to go far back, and we have to go all the way back to basically the axioms of Euclidean geometry. And these are there's kind of, everyone's familiar with Euclidean geometry. This is the geometry you know and love. You live in Euclidean world, very intuitive to us. And it turns out that for Euclidean geometry, in order to drive all the various rules about triangles and about squares and circles and everything, you really only need 5 laws. There's only 5 axioms that you need to assume in order to drive everything that there is about the geometry. You only need these five things. And these 5 things are so basic. It's kind of funny to even have a slide about this because they're so basic. But we need to go through them because we're gonna change one of these things, which makes this whole approach work. And so, what are these 5 axioms? Well, the first one is pretty straightforward. Is that there's one and only one line segment between 2 any given points. So this is basically defining what a line segment is, right? If you have 2 points, that makes a line segment unique, right? All you need is those 2 points to describe what a line is, right? What the second axiom here is that any line segment you have can be extended continuously to a line, right? So you can just keep the lines, you can take the line segment and just keep going, and that becomes a line. And this is basically defining what a line is. The third axiom is also straightforward. Hopefully everyone agrees with this. Is that there's only one circle with a given center and any given radius, right? So in order to find a circle, all you need is just the center of it and the radius for it. Pretty straightforward things. You learn this in high school or before. The fourth axiom is kind of so basic. I can't even draw a picture for it. I really struggled to draw a picture for this. It's just that all right angles are the same. Now, the fifth axiom is very interesting, and this axiom actually has been there's been a lot of controversy about this axiom for the last thousands of years. Euclid didn't think you needed this axiom. He believed that this axiom was redundant, that you didn't actually need this fifth axiom because you could derive it from the first 4. He believed this, but he could never. When he wrote his book on Euclidean geometry, right? He can never, prove everything without assuming this, and he really didn't like that. He really didn't like that. You have to have this fifth axiom. It seems too complicated. It seems like this should just follow from the first 4 principles. And so, what does this axiom say? It says something actually very important about space and geometry. Is that given any straight line, and it's a little complicated, so I think the picture is very helpful here, is that given any straight line and a point that's not on that line, right? So here's a line and a point not on it. There exists one and only one straight line which is going to pass through that point and never intersect the first line. There's only one possible line you can draw through this. And we can look at this and believe it, I think, right? I mean, there's only one possible way that you could draw this line, and that's what it is, right? On a 2D plane, there's no other way you can draw that line. And so the question here is like, this axiom seems to be special. What is kind of why do you need to write this down? What happens if you don't assume this axiom? And it turns out that if you actually change this axiom, you can drive completely different types of geometries. If you violate this axiom, you don't assume that axiom, you get these entirely different class of geometries. There are non-Euclidean geometries. They have these really bizarre and counterintuitive properties. And the geometry we're going to talk about today is this non-Euclidean geometry called the hyperbolic geometry. And this is just, I know we've had just so much fun exploring this geometry because it's so weird. And there's all these crazy things that happen inside this geometry, but it basically lets us lets us build new types of predictive models just by changing what the geometry is. And what the hyperbolic geometry says is it has all the first 4 same axioms, but the fifth axiom changes to say that there's infinitely many lines which can pass through that point, right? And never intersect, right? And so this is a little unusual, right? I'm saying from this, right? In hyperbolic geometry, there's actually infinitely many lines you could draw that will go through that point and never intersect the first line. Okay, so let's look at some examples here, because this whole space starts to get pretty unusual. And so you know, hopefully your brain is not too fried from CVPR, because this is really, I don't know, it's quite mind bending. So if you haven't seen this before, right? So I'm going to show you some examples. And so on the left side, I'm going to show you Euclidean space. These are going to be kind of the geometry that you're familiar with. And on the right side, I'm going to show you what the same thing looks like in hyperbolic space. Okay. So it's going to be important. The origin here on the left is always going to be the plus sign. That's always, you're always going to know where the origin is, because that's going to be the plus sign. That's 0, 0, right? And on the left is a square in hyperbolic space with this fifth axiom, right? You have two parallel lines and a point, right? That's just on a single line. There's only one possible parallel line you can draw in Euclidean space. On the right side, I'm showing hyperbolic space. This is one of the models of hyperbolic space. There's actually many different models for hyperbolic space. This is just the Poincaré disk model, which is the most popular model in machine learning to use. Origin is also the plus sign, and it's often visualized as a disk. And what happens here is actually infinity here is actually at the boundary of this disk. You're actually seeing the entire space inside hyperbolic space right now. This is the entire space. The infinity is at the boundary here, while the origin's at the plus sign. This is not true in Euclidean space, right? In Euclidean space, you know, there's infinity is off the slide, right? Infinity is not even visible in Euclidean space, right? But in hyperbolic space, you actually are looking at infinity here. And so if we draw this fifth axiom in hyperbolic space, right? Here's what a line looks like in hyperbolic space. It kind of, you know, to your eyeballs, it probably doesn't look straight, right? You have Euclidean eyeballs, and so it doesn't look straight to you. But this is in fact a straight line in hyperbolic space. This geodesic here is a straight line in hyperbolic space. There's a point; it's not on the line. And what the fifth axiom says is that, well, there's actually, you know, infinitely many lines that are going to go through that point and never intersect with that first line, right? There's infinitely many parallel lines, right, to this first line. All of these lines up here that I'm drawing here, they're all parallel to that first line, right? It is wild. I mean, this is when we first started reading papers about this. This was just so cool. I mean, it just was. We just wanted to do something with this. This is really, you know, we were just so curious about this. So there's many different, you know, there's many different types of ways that you can model hyperbolic geometry. There's not unique model hyperbolic geometry. The most common one is called the Poincaré disk model. This is the most widely used one in machine learning, just because this makes gradient calculation easier. The other models, it's much harder to calculate. The gradients are not as precise, and so the gradients are much stronger to calculate in the Poincaré disk model. And the way this model works is basically you have a hyperboloid that's shown in blue here. This is what a hyperboloid is. You can think of a hyperboloid as a hyperbola that's been rotated around some axis, right? So you get this hyperboloid, and all of the points are living on the surface of this hyperboloid. Okay. And so what that means, right, is when you start to calculate the distances between things, the shortest path between them is no longer just to go, you know, including this distance. You actually have to be on this manifold. You have to stay on the hyperboloid. That's going to be the shortest path. And so all these points on the hyperboloid are getting projected onto this disk here. So, you know, this and that's how you're going to calculate the distance. So I don't want to get into too many of the technical details here, because I mean, really the best way to learn about this is not through a talk, but just by carefully reading a book and going very slow, right? To really appreciate each step. But this is just to give you a little bit of intuition about kind of a little bit more about this geometry. And the way you calculate the distances between these points is not just your L2 norm anymore. That's not, you can't just do Euclidean or Manhattan distance. That's not the way you calculate the distance. This equation here, a scary equation here, it gives you the hyperbolic distance between 2 points, A and B. Okay. So this area has been just exploding in recent years. This kind of like many good ideas in computer vision, hyperbolic geometry actually was first used in NLP for modeling hierarchical structure. And we'll talk about why. I'll give you some more examples in a few slides about what makes this kind of what makes this geometry so attractive for machine learning. But really, one of the original kind of landmark papers here was from Facebook AI from Nickel and Kayla, where they were learning Poincare A embeddings, also with the Poincare disk model for word embeddings. And ever since then, it's just been exploding in all these different areas. It's being used in social networks and graph embeddings, for example. There's a lot of work just at the last CVPR. There was a lot of work. There's doing hyperbolic representations for computer vision, or either it's, for example, doing zero-shot recognition or even embedding hierarchy of actions. And so this area, I mean, this is it's brand new, right? I mean, this is well, it's not brand new, right? It's thousands of years old, but it's brand new to computer vision and machine learning. And I'm really excited about where this is going to go. And one of my goals here is really to convince you that maybe you should think outside of the Euclidean box, right? And you should think about non-Euclidean embeddings and all the different advantages that they're going to have for your computer vision and machine learning problems. Okay, so just to give you some more intuition to the space, just so you can start to get a little more understanding as to what it means for this geometry to kind of have a different fifth axon. Basically the generalization of a line is called the geodesic. This is the shortest path between things. So in Euclidean space, this geodesic looks straight to us. That's the shortest path. Right? The shortest path between these 2 points is just that straight line. While in hyperbolic space, there's a lot of scare quotes in this definition because they're being quite informal here. But geodesics don't look straight, right? With your Euclidean eyes, you looking at this visualization, it doesn't look straight to you. But in fact, this geodesic is the shortest path between those points. If you were standing here and you wanted to get to this point, the quickest way in hyperbolic space would be to move along this path. If you were to go this way instead, if you were to take that path, it would take you a very, very long time to get there. Anyways, this is actually turns out to be a key property of this space. So the reason why there's so much interest in this in machine learning. So let's go back to the mean a little bit, right? We were talking about the mean, and this mean is often viewed as a bug, right? But maybe we can actually view it as a feature, right? And so what does it mean take the mean? I mean, one of the things I really like about hyperbolic geometry actually is that it really forces you to be very clear in what your definition of points are. It challenges you on what does it mean? What is addition, right? What is a line, right? And so it's actually been a great device actually for teaching too, because you really have to come to grips of what are these things that you just take for granted, right? And so, anyways, a mean, right? What does it mean? If you take the midpoint between two points, there's this interesting property about hyperbolic space when you take the mean, and that the mean is closer to the origin, right? So if you have these 2 points and you take the average of them, it's not here. The average is not here. The average is actually, closer to the origin. And this is kind of when things started to get interesting for us. We were like, okay, we had this regression to the mean, and here's a geometry where this mean has this interesting property where it actually getting closer to the origin, right? This is all of a sudden things are starting to click, right? I mean, this geometry actually lets us turn some, to put structure into something that is often viewed as a bug, right? Okay, just a few more examples, just because I just have so much fun exploring this space. Kind of I get it's been hard to kind of focus on all my other duties as faculty, because there's so much fun reading up on different properties here. So here are we're visualizing triangles in both Euclidean and hyperbolic space. And so on the left is the triangle that you all know, and on the right is what a triangle looks like in hyperbolic space. And so, you know, again, the shortest it's bent, right? It's a bent triangle because informally, right? It's bent because the shortest path between these points is the curve towards the origin. One of the interesting properties about hyperbolic space is that the angles of the triangle add up to be strictly less than 180 degrees, right? In Euclidean space, you have this invariant, all the angles always add up to 180 degrees. It's just, you can't, that's always true, right? In hyperbolic space, that's always never true, right? And so it always has to add up to be less than 180 degrees. And some other cool properties about this actually is that in hyperbolic space, the area of a triangle is actually determined by the angles. So this is, you know, kind of weird. It's not true in hyperbolic. In Euclidean space, right? The angles don't determine the area here. In hyperbolic space, the angles determine the area. One of the other properties I want to mention here about hyperbolic space is that basically, because of this property that the angles don't have to 180 degrees, it's actually impossible to have a square in hyperbolic space, or even a rectangle. There's no way to actually have a rectangle. The rectangles just don't exist in this geometry. Quadrilaterals, you know, four-sided shapes exist, but rectangles and squares are impossible to construct in hyperbolic geometry. It's just because there's no way to have two triangles next. You can't have two triangles that are basically, what is a rectangle, right? It's two triangles, right? You can break them into two triangles, and the angles will never add up to 360 degrees. And so basically, it's impossible to have this shape. I often start thinking about what are shapes that are possible in hyperbolic space, but not possible in Euclidean space, right? I mean, this is a very weird space, very counterintuitive to us. Okay, so the last property I want to show, which is going to motivate why there's so much interest in machine learning in this space, is about basically the density of this space. And maybe this is best visualized through a circle. So in Euclidean space, right, here, we're showing us a circle. Here's the origin. Here's the circle defined, you know, by the radius and the origin of that circle, right? And what is a circle, right? And again, this gets to the point of you have to be very clear on defining what these shapes are. And so, what is a circle? What you know, really, what is a circle? And then a circle is basically a set of points, right, that are the same distance from the origin, right? And so, anything on this boundary of the circle is the same distance from the origin of that circle, right? That's basically what a circle is, right? Here's what a circle looks like in hyperbolic space, right? So all of the points on the boundary of the circle are the same distance from the origin there, even though the origin is kind of, it looks to us that it's skewed to one side, right? And the reason for this is that as you move away from the origin, your space is actually getting exponentially more dense. There's kind of, there's more room inside your geometry as you move away from the origin, right? So as you walk, you know, as you're here, right, you start taking, if you just take a walk from this origin towards the boundary of the space, you just have more space as you keep walking along, right? And it should actually be intuitive at this point, because remember I defined that this is infinity. The boundary of this Poincare disk is infinity. And so you can never actually get there. And the reason why you can never actually get there is because each time you take a step away from the origin, you have to do exponentially more work each time, right? Okay. So there's been a lot of, you know, hyperbolic space has really bended many people's minds for a long time. I wanted to show an example. It was really impressive from MC Escher, who you know, is an artist, had all these awesome, you know, art drawings. You know, you've seen all the impossible constructions that he's done, and probably in various computer vision and perception talks, right? But he also was able to draw art in hyperbolic space. And what's very impressive about this is that he was able to draw in hyperbolic space just using a compass and a pencil. He didn't need a computer, right? So he was actually able to draw art in hyperbolic space just by hand, which is very, very impressive. And it actually illustrates this basically the density of the space very well. So here's some fish, and here's some bats. And if you look at the bats, actually, the area of every single bat here is exactly the same. So the area of this bat is the same as the area of that bat, is the same as the area of that bat, is the same as the area of that bat. And so this is actually a very, very good, besides just kind of being cool art, it's actually a very, very instructive example, because it shows you how this space is laid out and how you get, there's so much density inside this space, right? As you go to the boundary, you get more and more room. And so this is basically the main observation. The same observation that Escher used to create this art is the exact same observation as what's been making this geometry take over machine learning recently. Is basically about how this space can be very efficient at embedding hierarchies. You can think of hyperbolic space as like a continuous tree. If you want to, if you want to, and that's basically what this is. It's basically a continuous version of a tree. The reason for this, just to be a little technical here, is we can talk about the distortion of this space. And so we can look at basically a tree in Euclidean space that gets embedded. A tree gets embedded in Euclidean space, and also a tree that gets embedded in hyperbolic space. Okay, and here we're showing this is showing a very simple tree. This is in Euclidean space, right? And this is a tree where here's the root node, and then all the children are kind of one distance away, right? The tree distance here is 1, tree distance here is 1, right? Now, let's talk about the distortion here, right? Because what you'd want is that the distance between these two nodes here, what you want is the distance between those two nodes actually to correspond to the tree distance, right? Which is 2, right? You'd want this node to be 2 away from each other, right? But in Euclidean space, it's actually impossible to embed this tree where the Euclidean distance corresponds to the tree distance. There's no matter how hard you try, there is no way that you can lay out these nodes such that every Euclidean distance is going to correspond to the tree distance, right? The best you could possibly do is what we're showing here. The best you could possibly do is get these to be square root of 3 away from each other. That's the best you could do, when it really should be 2. And the reason for that is because, well, if you were to move this a little bit, then you have to move all the others too, and it's just it becomes impossible. And so this is what defines the distortion of the space, where Euclidean space is always going to have for any non-trivial tree, any non-trivial hierarchy, there's always going to be a distortion. In this case, it's 2 over the square root of 3, right? You want this to be exactly 1, right? That there's no distortion if this is 1, but in Euclidean space, it can never be 1 for some non-trivial tree. And this gets much worse as you have complex trees, right? This is a really basic tree. Really, you want these really deep trees. So basically in hyperbolic space, because of how you get more space as you move away from the origin, you can always embed trees without distortion. So you need very few dimensions in order to embed a tree. And it's basically just an excellent inductive bias for a hierarchy. Anytime there's any hierarchy in your problem, hyperbolic space is just going to provide a great inductive bias for your machine learning algorithms. One of the things I love about this, though, about hyperbolic space, is that it's actually continuous. So you don't have to debate ontologies. There's no debate about is a sandwich a hot dog a sandwich, right? There's no debate about kind of the order of the ontologies here, right? It's just it's continuous. You can embed this directly into your machine learning through any gradient-based optimization, and you can basically learn the hierarchy. You don't have to sit in meetings debating ontologies. You can learn all this here. And so that's exactly what we're going to do. That's exactly what we're going to be doing with our predictive models. Is we're going to be training our predictive models in hyperbolic space so that this hierarchy about predictability can emerge. Right? We're going to be trying to learn what is the hierarchy about what actions someone might do, and so that it's organized, right, in terms of the predictability, right, in terms of being able to hedge a bet, right. When you watch this clip at the beginning of the talk, you have no idea, are they going to fist bump? Are they going to high five? Are they going to power shake? Are they going to wet fish shake? Are they, there's all these different types of handshakes and palm smacks, and you have no idea. You don't know, right? You cannot predict at the leaf level of this ontology. But what you would do, right, what any reasonable person would do is they wouldn't say, I have no idea. They would say, well, I can go up the hierarchy here, and I can say, I don't know about power shake or wet fish shake, but I do know that they're going to greet, right? That is something I'm really confident about. They're going to either hand contact or greet. I know they're not going to eat or dance or sleep. Those are things I know it's not going to happen, but I can be confident that they're going to greet. And so by training predictive models in hyperbolic space, what this paper shows is that this hierarchy basically emerges. And you can learn what is predictable about the future. Okay, so let me give you a little bit more technical details so it's not all snake oil here. So here we're going back to our predictive model where you have your input frames in red, and then you have your future frames in blue. You don't know, right? And so again, you're trying to predict a representation about the blue frames just from the red frames, right? You want from the red, you want to predict something about the blue. And these blue points can be embedded into the hyperbolic space. It's just like Euclidean space, right? We can embed it. We can have a hyperbolic embedding, and we embed those frames into a hyperbolic space. But again, the same problem occurs: is that there's going to be uncertainty, right? There's not a deterministic mapping from the past to the future. There is intrinsic uncertainty here, right? And so there's actually many points that are valid things that could follow from the red. So if you train a predictive model in hyperbolic space, you try to regress these points in hyperbolic space, what happens, right? You still regress the mean. It's still the same thing you do. But what the mean actually corresponds to in the space is a parent of all the possible things that could happen, right? The mean of these points is a parent node in this unobserved hierarchy, right? Just by taking the mean, right, which is the solution to the optimization problem. It's going to predict the parent node or some abstraction about what are all the things that could have happened. And so the way that we interpret this space actually is that your distance from the origin gives you your confidence, right? If you predict towards the boundary of the space, that corresponds to predicting a leaf node in this hierarchy, and you're very confident about what's going to happen next. At the same time, though, if you predict at the origin, you're basically saying I have no idea, right? The origin is kind of the root node of this tree, which is the root of all possible actions. The root node corresponds to this philosophical action, I do, right? That's all the origin is. It's saying anything can happen. You're totally uncertain. And anything in between is going to be different varying levels of uncertainty. So I think this is a very natural representation for uncertainty, right? This is how a person would predict, right? They wouldn't say, there's going to be a handshake with probability 0.385. They're going to give you they're going to pick what level in the hierarchy they want to predict that, or automatically select what level of abstraction should I make the forecast at, and then from that level, then make your prediction. And so the way we implement this is actually just through the standard contrastive learning objective that everyone knows and loves. So the equation I've written at the bottom here is the same contrastive learning loss that you see all over the place. The only difference here is that we're computing the hyperbolic, or computing the distance. The way we calculate similarity is not the Euclidean distance, but it's actually the hyperbolic distance, right? So there's two terms here, right? The usual contrastive loss. You have the positive term saying, the true future Zi, right, should be close to your prediction Zi hat, right? In some embedding space, according to your hyperbolic distance, while at the same time being far away from all of your negative examples. Okay, so yeah, here's kind of the typical neural net, just to kind of make this very concrete how this is actually all implemented, right? You have some video frames that are being fed in, goes through your convolutional net, goes through LSTM, and you're trying to predict a representation about the future. But you're computing all these similarities in hyperbolic space. And so this network that we're showing here is actually a straightforward extension of dense predictive coding from the Andrew Zisserman's group. It's just we modified it to be operating in hyperbolic space rather than operating in Euclidean space. And just by doing that modification, do you get this representation of uncertainty, and do you get this hierarchy? There's one detail I want to mention real quick here. We're following the standard self-supervised kind of setup that everyone has adopted here, where you do your pre-training on unlabeled data, right? You train this predictive model on unlabeled video, train it for as much data as you have, as long as you possibly can. And after you train the self-supervised representation, then you want to fit a classifier on top of it in order to read out or decode what the predictions are, right? Because there's no language in the self-supervised learning area. It's just learning from video. There's no language, so you don't. It's making a prediction of what's going to happen next, but there's no way of decoding, right? What the name of that vector is. So you can kind of what everyone does, right? Is you have a classifier that you use a little bit of labeled data in order to fit a classifier to what the predictions are. So it's a little bit more complicated in our setting because it's not just your linear classifier now, it's a hyperbolic linear classifier, right? You have to drive a linear classifier in hyperbolic space. So it can be done. I think it was relatively straightforward to do. Anyways, that's in detail. So here's an example of this system in action. I'm going to show you a bunch of examples. And if people have questions, feel free to just interrupt up here. So what this is showing is a video as it plays, right? So the video starts to play. It's basically streaming. It's a streaming approach, right? And so as it plays, you're starting to make predictions about, hey, what's the last action going to be, right? The video is playing and you're predicting what the last action is going to be. And as you get more and more frames, you can get more and more confident, right? Because you have more information. The longer you watch the video, the more confident you can be about, hey, what's going to happen next. So that's actually exactly what happens inside this hyperbolic space, is that as the video plays, the predictions that the model makes get further and further away from the origin because it's increasing in confidence. So at the very beginning here, right, if you just see a single clip, a single frame, right, this is on a sports data set here. If you see a single frame, the model's not very confident yet, and so the distance is actually relatively close to the origin, and that corresponds to some high-level parent node in this tree, right? Which is saying, all I know is that they're going to do something about uneven bars. I don't know what routine and uneven bars they're going to do, but just from a single frame, it's all you can predict, right? This problem is too unpredictable at this point. But as more and more observations start to become available, right, the predictions start to move away from the origin. They're increasing in confidence, and that corresponds to moving down on the tree, or getting closer to the leaf nodes on the tree. And so this plot is showing, right, as time goes on, you increase your confidence, and then you can read out what just from your classifier that you have, you can read out what category it's predicting that they're actually going to be doing next. Let me show you some more examples of this. We've evaluated this on a couple of different data sets. This is, trained on these big unlabeled data sets like kinetics and MovieNet, and then evaluated on these standard data sets for action forecasting. So we've done this both on Hollywood 2, as well as for evaluation, as well as the Find Gym data set for sports. And so here I'm going to play a video. The video is going to play on the left here, and then the tree is going to be visualized here on the right. And as the video plays, it's going to move down the tree, right? The predictions is going to get more and more confident as it moves down the tree, right? So at the beginning, all I can say is that there's a car interaction, but then once the person opens the door, it gets very confident and say, I can move to the next level and say they're going to get out of the car. Here's another example, right? So it starts off, and all we can say is they're going to do fast human action, right? Eventually, it can expand this to say they're going to run. Here's another human interaction. And this is this is in Hollywood 2. It's a relatively simple tree. It's just a 2-layered tree, right? Play this again, right? It knows they're going to interact, but it doesn't know what they're going to interact. And then once they do kiss, it can be very confident about kiss, right? But one thing that's nice about the hyperbolic space is that you don't have to make any modifications as your hierarchy gets more complex. It's all learning based. It's all basically the gradient is basically forming what this hierarchy is. We don't have to. We never sat down like we're debating what this hierarchy is. And I love this part about this. We just kind of let the hierarchy let the hierarchy emerge. And so here's an example of a deeper hierarchy. This is a 3-layer hierarchy on the Find Gym data set. And so I'll play the video here. And so in the very beginning, it's very uncertain. There's many different types of balance beam routines that you can do. It's really confident it's a balance beam. And as it sees more and more, right, it can start to expand this and say, okay, it's going to do balance beam, leap, jump, hop, right? It's pretty confident that within balance beam, that's the category that's going to be doing. And as more and more data becomes available, right, as you see more and more of the video and watch the video for longer, as the model watches it, it can eventually expand this more. Right, and say, the full action that they're going to be doing at the very end here is going to be split jump. Here's one more example. So it knows they're doing uneven bars here, right? But you don't know what inside the uneven bars yet, right? There's too much uncertainty. There's too much variation. And as time goes on, this can expand and get pretty deep into the tree, right? This is many different levels inside the tree here. So yeah, I mean, we evaluated this on some data sets. This is showing results at doing action forecasting, where the task is basically to predict what the last action the person is going to do. We are interested in evaluating, how well does hyperbolic representations work for forecasting. So this is the key comparison for us: is how do we compare what this geometry does versus the Euclidean geometry. And so here what you're showing is showing different ways of doing this evaluation. Kind of the left side is the standard K-way classification task that everyone does about doing the forecasting, and this is showing the accuracy versus hyperbolic versus Euclidean here. And hyperbolic does better, right? It wouldn't be doing better. It wasn't doing better when we're talking about it. And the same, but you can also evaluate this on different metrics, right? You can have a hierarchical classification accuracy. So maybe you don't get the leaf node correct, but you get the parent correct at least, right? And maybe you get half points for at least getting the parent correct, right? And so these are different ways of computing this in terms of hierarchical accuracy. And still in those cases, hyperbolic space, you see a nice win. It generalizes across data sets. Here's on Hollywood 2 instead of the sports data set. Kind of you see the same types of trends. One result I want to highlight here is actually that basically the efficiency on the dimensionality. You don't need many dimensions. I mean, it's so here what this is showing on these plots is the lighter color is 256 dimensions, while the darker color is only 64 dimensions. And so in Euclidean space, when you reduce the dimensionality, you get much more distortion, and so performance drops a lot. In hyperbolic space, there's minimal drop, right? You can right, you can drop dimensionality by the order of magnitude, and there's a very small drop in performance, right? And so this is a really nice property. Is actually you can learn these models and require fewer dimensions. You know, it could be useful for compression or something like that. Here's just some more visualizations of this model. You know, no one has, as far as we're aware, no one has invented t-SNE in hyperbolic space yet. So we couldn't show cool t-SNE visualizations. Hopefully someone can go on and invent t-SNE in hyperbolic space. So what this is visualizing is the trajectory that these points make, just selecting the top two dimensions with the most variation. So as the video plays, the model is seeing more and more frames. And so what you should notice here is that basically the predictions are moving away from the origin, right? They're moving towards the boundary. This is a behavior that just happens automatically as it gets more and more confident, as there's more and more observations to form its predictions, it can get closer to the boundary here. Okay, so I think I'm running out of time, so just wanted to give 3 takeaways. I mean, I think this is a really exciting area. We are very excited about this, right? It started just, and to be honest, it just started as being curious. Like we didn't really know where this was going to go, and kind of all of a sudden it just clicked, you know. And we wrote a paper about it, and so it's really just 3 lessons I want to leave with, which is, you know, this regression to the mean is not always a bug, right? Often you can generate a lot of good research ideas this way, right? You take something that is seen as a bug and turn it into a feature, and this is exactly what's going on here. I think hyperbolic embeddings are providing new opportunities in computer vision. I really think this area is going to continue to explode. You know, it's just an idea that makes good sense. It's like hierarchies are everywhere in vision, right? I mean, this is just one example, but there's hierarchies all over the place. And I think the field often gets bad taste in their mouth for hierarchies because we have to, you know, we have to annotate them. And hyperbolic geometry is a way of doing self-supervised learning of the hierarchy. That's really what I think this is all about. And so I'm really excited about this because we don't have to, you know, debate hierarchies anymore. We can learn the hierarchies instead. And finally, you know, the last point here is this point about, you know, if we want predictive models to really kind of go outside the lab and not, you know, work in these limited data sets, you got to deal with uncertainty and what is predictable. And so these, you know, it's not complicated, right? And so it's not always clear, right, what exactly is predictable. And so this is something that we should not engineer, right? This is we should put on a machine learning hat and actually learn what are the things that can be predicted. Code is all available on GitHub. All the data is available. We even have some tutorials and much longer talks and pointers to resources and courses to learn all about this. We have this very cool URL, hyperfuture.cs.columbia.edu. One great thing about hyperbolic geometry is you can have a lot of good puns. You can put hyper in front of everything. So hyperfuture.cs.columbia.edu. Kind of all the details, all the code is very easy to reproduce. It's all in PyTorch. And we're an academic lab, so it doesn't require hundreds of GPUs, right? You can get this to work on your old computer from last year. All the work here was done by two PhD students in my group, Didak and Rushi, who really learned everything about hyperbolic geometry and boldly investigated it. So they had to jump through a whole bunch of math that boggles the mind. So anyways, happy to take any questions, and thanks so much.
Okay, thanks so much for your amazing talk. It was really interesting. So we have a question from Zoom chat. Farrokh has asked, he has said, it's a fascinating talk. Do you have any intuition around whether hyperbolic representations can be leveraged to discover hierarchy? He says like open set settings.
Yeah, I mean, I think this geometry basically is just a good idea when there's a hierarchy involved. It's all about the density of this space. And so, yeah. If there's a hierarchy, then hyperbolic space should be something that you try. This is a tool you should add to your toolbox. And one thing I want to mention here is that one thing we were worried about when we started this project was that just getting this to optimize was going to be really hard. It seems like this could be a machine learning idea that sort of works in theory, but not really in practice. But I think I'll let Didak and Rishi comment if it was, there's a bunch of coding debugging they had to do, but it didn't seem like it. I mean, it was sort of, it took like a month of experimentation and everything kind of worked, and there wasn't really hyperparameter tuning. So, I think this is just an idea that makes sense.
Great, thanks. So, any other questions from Zoom chat? No question on the YouTube channel. Yeah, I think people are tired. It's the final day of the conference.
I know. Okay, so thanks so much, everyone. Thanks for staying. And any questions you have, just feel free to reach out to our group and be happy.
Oh, we got just one other question. Sorry. Nicholas has asked, I would like to ask if hyperbolic geometry can be used in intermediate layers, not just the final ones.
Yeah, that's actually an interesting advantage, is that you can map between Euclidean and hyperbolic geometry. It's possible to move between the two spaces. So you can, some layers can be hyperbolic in your network and some layers can be Euclidean, some can be another different type of geometry. And the advantage of this is that lets you basically take advantage of the legacy of all the neural nets that have been built. You don't have to go reinvent CNNs in hyperbolic space. You can kind of seamlessly blend this into the parts that do make sense. So when our work actually, most of it is operating in Euclidean space. It's just kind of the few layers here that are operating in hyperbolic space, really showing that this blending does work.
Cool. Okay, thanks so much again for your amazing talk.
Thank you.
So our next speaker is Sanja Fiedler. She's from University of Toronto and also NVIDIA. I think she's with us. So hi, Sanja.
Hi, guys.
Yeah. So the stage is yours.
All right, thanks for inviting me. Let me just quickly share my screen here. All right, are you able to see?
Yeah.
My slides? Okay, awesome. Yeah, so I realize that this is, towards the end of CVPR, it's almost the end. So promise is going to be a more high-level talk, all equations successfully removed. So hopefully it's going to be a kind of fun closure of CVPR. And, I don't really work on video, and this is a 50-minute talk, so this was a slight nightmare on my part, but I'm going to talk about simulation, which essentially is about, generating video. All right, cool. So as you know, I also lead a lab at NVIDIA, so I'm part-time at U of T, part-time at NVIDIA. And at NVIDIA, really the vision for the future is in 3D, right? So the vision is that anything that is built will be visualized, anything that moves will someday be autonomous, and anything autonomous will be, or maybe even needs to be simulated, right? You need to test it before you can deploy it in the real world. So really there is need for large-scale simulation and platforms that can enable physically accurate, simulation, camera-based, all sorts of sensor-based, that enables, simulation of complex virtual worlds. So NVIDIA has been developing this thing called Omniverse, which is a really amazing platform for real-time collaboration and simulation. And it essentially allows you to connect all sorts of different 3D modeling softwares. So, Blender, Maya, basically anything can just be a connector into this, simulation platform, Omniverse. And it also allows you to plug in tech very easily. In fact, like if you have a new physics algorithm, a new, renderer, or a new AI algorithm that you want to test, there's just like a Python interface into Omniverse. So it's super easy to deploy your research. So check it out. It's actually open beta is out, so you can play with it. So as you can imagine, this kind of platform is super powerful, right, for different downstream applications, such as maybe architecture, gaming, entertainment, and so on. But one important customer of this is obviously simulation for robotics, right? As we know that, before we can deploy certain robots in the real world, then you need to test them in simulation against all sorts of different challenging scenarios. So what I'm showing here is NVIDIA's DriveSim, was just the recent version was unveiled by Jensen GTC a month ago. Where really basically what you're seeing here is rendered in front of your eyes. So everything is photorealistic rendered, all the physics, lights, everything is computed in real time on Omniverse. And obviously there's a lot of content that has been created specifically for driving simulation, which is what you're showing here. So this was replicated to one part of Germany where you can see there's very accurate maps and so on. Now simulation gives you a lot of cool things, right? So it gives you perfect control over the environment, over the video that you're basically generating, right? So you have control over the maps, you have control over the weather, traffic signaling, how many and what kind of agents you're gonna put in this scene, and their behavior and so on. So you can design different scenarios that you're gonna test your ego vehicle against. Right, and if you have this kind of real-time platform, the simulation is not different than real world, right? Because all the sensor data is coming to you, physically accurate and in real time. All right, so as you can imagine, making this kind of a simulator is incredibly hard. Like this is, I cannot explain how much effort goes into this. It's really kind of like a crown to technology and art. And today I'm going to talk a little bit about behind the scenes, not really about DriveSim. I actually don't know, all the details going behind DriveSim. I'm not going to give you academic perspective on how you make simulators. And this is really coming from my very best friend Antonio and me, who started working on simulation 6 years ago. And we started from scratch. We had no idea. We had zero knowledge how to make simulators. We are computer vision people, so this was a completely new experience for us. And we created, this is after 6 years, we created this household simulator called Virtual Home, where essentially the idea is that, similar to a driving simulator, here you want to simulate household activities, right? So you want to have this virtual robots or virtual characters inside a household doing all sorts of different activities, and have different characters collaborate. And the same as you have families in a household, you maybe want to have a robot living with other humans, so you want to have different, like a social aspect of simulation as well. And similarly, as for driving simulator, here we also want to enable different control, right? You want to switch on lighting, you have different types of environment, different types of households. You can control the cameras, you can stream any kind of ground truth from the simulator, like semantic segmentation, instant segmentation, depth. You can have ego camera, you can have third person camera, so on. And really we made a huge effort on animating everything. So you can see all the characters are animated, objects are animated. And now, you can make this into a really social platform. We also enabled RL, so you can start training robots here to do stuff. So how did this all happen? Actually, the idea for this came at a Scenes from Video workshop, also called Wine Workshop, that Michael Black organized 6 years ago. So this was ICCV 2015. And Antonio and me were talking in the evening after the workshop, kind of the state of computer vision. At the time, there was all these different data sets that would be testing, depth prediction, semantic segmentation, and so on. And we really kind of felt, what is this really testing? Right? If you really want to have a robot that does things, this is only testing one part of the pipeline, and it's not even clear it's testing in the right way, right? So if I mislabel one particular pixel here, if I say this is a kitchen table and not a desk, is that a big mistake or not? We have no idea, right? It's kind of like an auxiliary task, but maybe it's also a bogus task. We don't know. We just don't know how fake this task is in light of a full system that we need to build. So we were thinking, we really need to build closed loop data sets. What does this mean? That, it needs to be a simulator where you can make actions and the world changes and you have a task that you want to perform in this environment. Okay, so after a bottle of wine, maybe even more, we had a brilliant idea. We decided we're going to build kind of like a Sims game for AI, right? I don't know whether you guys have played Sims games. So, it's basically this social game where you have characters in a household. Actually, they go beyond household, where you can do all sorts of different things in your home. You can also interact with other characters, and you get even some rewards from these games, and there's some aspect to the game. All right, so our idea was, and it was so clear after some wine, that this is the way to go. Okay, now I'm going to talk about how challenging the challenges that you face by creating a simulator, particularly when you go into this without any knowledge. So the first thing you need to do, right, is getting some assets. What does this mean? You can go online. So we built our simulator on top of Unity, which seemed the easiest at the time. And Unity has this asset store. You can go online. And even for like $35, which seems very cheap, even for academia, you can get quite a lot of assets. In fact, like here, you get a couple of hundred assets in this one package that we downloaded. And not just assets, you can even get them composed in different apartments. So this particular package for $35 comes with 6 different apartments, and you can even mix and match and build more of them. So that seems super easy. We also went online, we Googled for characters. There's this really nice page, Mixamo, which makes a lot of characters freely available. Maybe they're not super realistic, but like they're free. So that seemed very easy. And now we're at this stage, right? So we have content, we have one particular apartment, and we have this character we downloaded in T-Pose, right? And well, what do we do now, right? The story should begin here, right? All right, so the next thing that you need to do is getting animation clips. Turns out that is also not so hard. You go online again, and there's not just characters that Mixamo offers, it's also animations. So here they have actually a couple of thousand different clips of these characters doing all sorts of different cool things. And it even gives you some control over what, like the speed of the animation you want to play and so on. All right, so, you can start animating things. And the first thing you learn, because you're not a graphics expert, is that retargeting actually is not so easy. What does it mean, retargeting? You download that clip that was made for somebody, some character, and now you have your own character and you want to retarget that animation on that body. So here was us first trial of trying to retarget drinking animation. Let me play this. All right, so this character definitely misses to the mouth and kind of spills this water on top. So, that's the first lesson you learn. And the second lesson is, well, you don't only need animations. So not only for the characters, you also need to rig and animate all sorts of different objects that are in the scene, right? You want the fridge to open, you want the cabinet to open, you want the oven to be hot, so it should somehow indicate that it's hot. Toilet seat can go up and down, a toaster, a TV, like all these objects are not just like static piece of a mesh. They actually need to come to life. And that's also not so easy. So we were lucky that in the $35 that we paid, a lot of stuff was already rigged and animated. And we rigged a couple of objects on our own. So for example, the stove and TV, that was kind of our students trying to do that. Okay, so that's fantastic. We now have rigged objects. We now have animation clips, and we learn how to retarget them. So let's try this. Okay, so obviously this does not work. There's a lot more stuff that we did not consider, such as physics and yeah, all right. So obviously this is not the end. What we need to do is annotate this content. All right, which means that we need to annotate physics-related properties, mass, maybe friction, I don't know exactly what, and interaction-related properties, right? Because we want these characters to actually interact with all of these different objects, which means that we need to basically tell them how to interact. So for example, you tell the character that if they press this button here on the stove, then we're gonna play the animation clip that's gonna animate it. Or for example, for the toaster, it needs to press it here. for the fridge, it needs to grab this door and pull it in a certain direction. And if it's closing door, it's grabbing that, but in the other direction. So you can quickly imagine there's a lot of work associated with that. And luckily, then, you know, physics gets correct and things open the way they should open. Right? Just to stress, there's just so much work associated with this, right? Interactions means two different things, right? So for example, if I want to open a fridge, it's going to be different way of opening a fridge than maybe opening a laptop or opening a door, right? So even if it's the same kind of interaction, just open, there's many different things that we need to annotate with respect to the object we're interacting with. Same for sitting here, we need to annotate where to sit if it's a toilet versus a sofa. And switch on is the same thing, right? Switching on a light in a living room is very different than switching on a TV or switching on a coffee maker. And all that had to be manually annotated. Great, so now we can kind of start doing things. It's just that we're missing the global context. We're missing what we actually want to animate. What kind of activities can a human or a robot do in an apartment or a household, right? And it turns out there's a lot of stuff, right? We've all been stuck in a pandemic for over a year. So you would know that a household is the world, like everything has happened in your household. Even though it seems monotonic and it seems like there's not a lot of stuff you do every day, there's actually a lot of stuff that you do, right? And our task is going to be, we want to be able to simulate all of this stuff, okay? And kind of our idea of how to go ahead with this was looking into how humans are instructed how to do things, right? So if you go on WikiHow, it tells you rough steps you need to perform to, let's say, make a tea or some other activity, right? So we're going to similarly break down activities in a robot language, right? We're going to break it down into some sort of program that has these very simple instructions, like atomic instructions, right? Walk to the kitchen. And we know how to animate walking to a kitchen. We can just compute target location, compute the path to the kitchen, and then just play the animation walking. That's easy. Grabbing a kettle, again, we have annotated everything. We just need to animate stretching the hand in the right place that we annotated, and then, you know, putting the kettle into the hand of the character. Okay, but the activity is basically going to be a sequence of different these little instructions that's going to make this character do more things than just this like unit actions. Okay, so basically simulating activity is just going to be executing a program in a game engine where, of course, there's a lot of code that is on the side of the game engine that's going to take these little commands into account. But from the user perspective, is only going to be producing these simple commands to the game engine. Okay, and we were super proud of ourselves. We had an idea how to actually scale this so that we didn't need to write all of these different activities by hand ourselves. So we took this platform called Scratch, which is essentially teaching. It's like a little platform that teaches kids how to code. And we thought, well, this if you know kids can do it, then maybe mechanical Turkers are also able to use it. And the idea was that you give them a description of the activity, where we had another Turker actually write. So for example, here the description was go to the kitchen and take a plate. And then we asked these annotators to write a little program that would execute this particular activity. And this seemed easy enough. If you make the task easy enough by using something like Scratch, this turned out to work. So we were actually able to scale this up and collect quite a few of such programs. This is one example, like setting the table, making coffee. It turns out that there's many different ways in which you can make coffee, and different Turkers imagined that way, or maybe do coffee in different ways, which was kind of cool. So you got a program that tells you how to use a coffee maker, one with kettle, and then one that really focuses on adding sugar and milk to the coffee, right? Which is kind of really great because you're getting this amazing diversity of how people do different activities. And we made all these available online, right? So if you have a robot, they can just go online and download all these little programs they can use to simulate activities in virtual home. Great. And then the latest addition to this platform is making it social. Like everything I talked about so far was just a single character inside this simulator. And Antonio and his students made it parallel timeline. So you can actually have multiple different different characters interacting and doing things here. And there's all sorts of challenges that you can create as a part of having this multi or social platform, right? You can have one character that has a task to execute a particular activity where you give it a step that they need to perform to finish that activity. And then you can have another robot that needs to help the other robot, or a human robot, let's say, to perform that activity faster. And since this is all RL based, you can train these RL agents to help each other, which is cool from all sorts of perspectives, for example, for analyzing emergent behaviors and things like that. So all that is available, so go and check it out. All right, so one thing that hopefully we have learned from this is that creating a simulator, even if it's academic and simple, it's actually super time consuming, right? This is us after 6 years of work. It's definitely not scalable. Right now, we still have these 6 apartments that we're using. If you play these clips, it looks like it lacks diversity because we're bounded by these animations that we downloaded, which seems a lot, but it's actually not a lot. And really the question is about, how can we scale this up? So what is the simulators 2.0, right? Where maybe we want to actually introduce AI into all parts of this pipeline. Okay, so now I'm going to switch gears a little bit, and I'm going to talk about our efforts to basically introduce AI on each of these steps that you're going to see here. So the first part is just getting the assets. In fact, this is one of the major roadblocks that we see now, because if we're going to have a trained robotic simulator that's going to train robot working in this simulator, it needs to have a lot of different environments to train. Otherwise, we're going to see severe overfitting. All right, so we want to scale just the amount of environments, amount of assets, and so on. Hopefully, by not paying a large cost. So there's a couple of things that I think we need to solve, or at least I want to solve, is kind of end-to-end synthesis of everything, right? One thing would be synthesizing the maps, for example, city road layouts, if it's a map of a city, or a floor plan, which maybe is an easier task, which I'm going to skip for now. And synthesizing objects in these maps, so buildings and cars, pedestrians, or into indoor scenes, different fridges, sofas, and so on. And the last, of course, is the asset itself, right? So how can we have not just the 6 characters, but maybe 20,000 characters, 20,000 sofas, 20,000 cars, and so on? How can we scale that up? So here is our little effort on being able to synthesize maps. And in fact, synthesizing city road layouts was harder. So we focus on this part. Where essentially, I'm not going to go into details, but we have this graph generating network that is treating the entire city road layout as a graph where nodes are control points, and then any 2 nodes connected, it means a straight road connecting them. Let me just play this video just to give you an idea how this works. So here it's trying to generate different cities, and we give it like a content code, so a city code, so that we bias the style of the cities being generated. Berkeley will look different than Toronto. We can make it interactive, so an artist can say, I want to have New York like anchor here, Toronto kind of anchor here, and the rest is generated. The same model can actually also be used as a prior for parsing, which means that you can take aerial images, parse them, and then since it's a generative network, you can modify it different ways, and that gives you variations of maps. So here is a couple of these maps. And you can procedurally add maybe other things inside this map to have like an entire city fully synthesized. All right, so the next thing is, well, now we kind of use this procedural model, but it's still very crude, right? It only has maybe some buildings, right? We wanna populate it in realistic ways. So this is really kind of hot off the press with intern Despoina who's been working on this. So the goal is to, have AI synthesize indoor layouts, right? You want to be able to sample all sorts of different layouts for all sorts of different rooms. You want to do completion, which means that maybe I want to decide I have certain objects in this particular floor plan, synthesize the rest, and maybe even suggest, what should I place in certain parts of the room. And the nice thing about here is we had this transformer architecture that is order independent, meaning that I can be synthesizing or I can be anchoring any objects in any order, and I'm not going to be affected by that. I can complete by not being affected by what the user has already specified. So here's a couple of sample bedrooms. Looks quite nice. And with respect to past work, it's really nice because it's real time. So all past work actually took a couple of seconds or even more to generate. This is real time, so it can really be used for interactive tasks. But the kind of aspect that I love is that it generalizes so well to floor plans that it has never seen during training. Like here, this is Despoina actually kind of drawing very obscure looking floor plans. We condition on that and then we synthesize. These are like just different methods, and ours is here. And you can see that, it kind of learns not to place objects in where is a hole, whereas other methods kind of place a bed, even though here is a hole. And even for this very obscure floor plans, you're able to synthesize really nice looking rooms, which is awesome. And it can also do completion and some other stuff. Now, of course, you're going to ask me, how did you train this transformer? And I'm going to be honest, I'm going to say we used a couple of thousands of rooms from this 3D front data set. And then you're going to say, oh, but if you have a few thousand rooms, then why do you even need to synthesize? Maybe for training robotic SAS, you actually need a lot more. I'm not going to go into that. But we also have work that tries to do this entirely from pixels, so no annotation at all. So how can you still synthesize different scenes or different object layouts by not having that kind of supervision of bird's eye view bounding boxes? Okay, and really kind of the trick that we use to make this to work is rely on some rules, right? So here we're going to use a probabilistic grammar where someone has specified rules for outdoors. So, a road can have a bunch of different lanes. On lanes, I need to place cars. A sidewalk is next to a lane, and then people and trees are next to sidewalk, and so on. So these are simple rules that might not be so hard to write by someone, because we want to write them very loosely. We don't want to have really hard specification for where exactly we're going to be placing each individual object with respect to its parent. Okay, so we essentially want to take these very coarse rules, and we want to learn aspects of this model. We want to learn where exactly to place this object relative to its parent, like the distribution at least of location, height, pose, colors, or whatever from data. Okay, so we had this method called metasim, which takes scenes that are sampled from the prior, and then it learns to rearrange objects such that the render scenes look similar to real scenes. So just using something like MMD, so distribution matching losses. And then a follow-up would be, well, maybe we want to learn structure too. We don't want the artist to tell us there is always 2 or 3 lanes. We want to learn the distribution over the structure. So how many lanes, by just, again, looking at the data. I'm not going to go into detail, but I was surprised how well this can work by not having a single pixel annotated. Everything is just looking at images or videos and without any annotation. So here on the right is samples from Kitty, on the left is samples from this like badly initialized probabilistic grammar with a very bad prior. And this is by learning both the structure as well as this attribute. So, how many lanes and how many cars, and then where exactly to place them. and some videos that basically show how this model is optimizing scenes during training. You can see that very quickly it learns how to align objects with the road and then bring pedestrians closer and so on, so that it looks more realistic. Cool. All right, so now we have object layouts too. So the last thing that we need for content synthesis is 3D models, right? Where maybe the goal would be, want to take an image and we want to output like some sort of graphics-based representation. So 3D vertices and faces, a mesh, right? And maybe we want to output also some semantics, right? In materials, maybe this animal is furry and the car has a metallic body. And we want to maybe annotate parts, because if I know this is this part of the mesh is an eye, I can actually animate it, rotate the pupils and so on. And if I can predict skeleton, maybe I can also animate this little koala here. And I want to do it everything from just single images, right? Apple has released this amazing capture app. I'm impatient. I don't want to wait a few years before Flickr becomes all 3D content. There's already millions of images online for pretty much anything you search for, like cars, buildings, and so on. All right, so we wanna solve the following problem. We want to take an image and we want to train a neural network that's going to predict all these desired properties, mesh, light, and texture. But we don't want to have supervision over here. We don't have it. We only have images, right? And we're going to do this by essentially plugging this prediction into a renderer that renders an image. And now if this render is differentiable, then now I can basically backpropagate losses that operate directly on the rendered image and input image. So something that compares it to images. I can backprop this after training this particular network. Okay, now it turns out that this actually does not work. You do need to have multiple views of the same object during training, or this is kind of cheating, like it's just going to produce a flat mesh, a plane, and a flat texture, just copy the original image. And the way to solve it is just have multiple views of the same image. And we used a super cool trick to solve this problem. We actually used GAN-generated views of objects during training. I'm not going to go into details, but essentially you're going to use StyleGAN to produce multiple views of the same car. And then we can just use this for training this network. And that kind of leads us to GANverse 3D, which takes an image, produces a mesh, produces a texture that it can paste on the mesh, and produces also a part map. And I'm not going to talk about today, but if you've been at CVPR, check out dataset GAN. It essentially also produces really detailed part annotations for these 3D predictions. And this allows you to do super cool things because now you know where is the windshield. So you know the windshield is transparent. You know that the body of the car is metallic. So you can have proper materials placed on this asset. And if you also know that something is a front or a back headlight, you can animate it, right? And if you know that something is a wheel, well, maybe you can just put a rigged wheel instead of the predicted wheel. And then you can have like fully animatable 3D model. So let's look at some results. So if we're going to feed in this image, and here is our 3D model, it's predicted real time. So you can just get this model out. It has this part map. And now because we know the part map, we are just animating it. Here is one more video just to show you this is scalable. So here comes an image. Here is the asset. It's not the same as being artist created, but it's not so bad given that the cost is nothing. The cost is me snapping a photo. Cool. The materials look pretty nice too. And again, everything can be animated. And of course, we don't do this only for cars, right? Anything that is available abundantly, you can train the same model. So we train it also for birds and horses. And of course, there's some challenges still left. For example, the birds don't have legs because that seems to be very hard. Segmentation doesn't see legs, and then optimizing the mesh for that tiny legs is hard. horses have super weird backs. Why? Because almost no photographs contain a back of a horse. They're so tall, no one is taking pictures of their backs. So there's some, artifacts like that. But basically now we're working on scaling this up to just many more 3D assets. Awesome, so now we have assets. The next thing we need to solve is animation clips, right? All the stuff we downloaded was probably obtained by mockup. So having people in a studio with all that heavy suit on them and then performing different things, kind of acting different animations out, right? Which we can argue whether that's realistic or not, right? So the whole degree would really be kind of building this virtual human module that can animate, pretty much anything that humans are able to do, and they do all sorts of crazy stuff, right? So I really think kind of the scalable way of training or synthesizing this motion is by looking at videos. Okay, the videos there's so many YouTube videos online, right? We should be able to learn, how people do things from those videos. So this is another paper, actually, it's also hot from the press, that is trying to go from video. It's basically running pose estimation from these videos. And then we're doing physics-based correction on those poses. Because 3D pose estimation, particularly if you do it frame by frame, is super, super noisy, right? Because depth is ambiguous. If you have any occlusion, let's say on the feet, it's just going to go ballistic. And really kind of our idea here was we're going to have physics as a prior and then correct this 3D pose estimation by basically making these trajectories physically plausible. Okay, and then, maybe that gives you really good estimates and you can retarget those to meshes and things work out. This is my only slide with equations, but I'm not going to go into these equations. It's basically just trying to tell you that physics is a really good prior for denoising 3D pose estimation by basically telling it what forces are not possible, and optimizing contact and optimizing for smooth motions, and the fact that feet cannot go into the ground and so on. Okay, and there's been a lot of work already on these aspects. It's not like we invented this. I think the nice aspect of this work is that we're able to optimize for contacts as well in a soft way, where previous work typically had to have them labeled. And we're also optimizing for the parameters of the body, so the bone length and so on. So all this is jointly done with this physics-based optimization. Let me just play this video. I'm going to have 2 seconds of rest while you watch this.
From videos. Here's an overview of our method. We first detect poses from raw video. Then we transfer the motion to a physical character. This is then used during a physics-based optimization to correct using physics-based losses. We aggregate the motions from a large database and use them to train a motion synthesis model. Now we compare our method qualitatively. Our method is the physics-based method, and the baseline is a kinematic method with physics losses removed. In all of our videos, results from the physics-based method will be displayed on the blue character, and results from the kinematic baseline will be displayed on the green character. Now we show the ability of our method to disambiguate depth. In this comparison, we overlay both the motion from our physics-based method and the baseline on videos. On the left panel, we have the input camera view, which is used by the pose estimator. In the middle is the reference camera view, which is not used. And on the right, we have an orthographic side camera view. From the side camera view, it is clear that there are great foot floating artifacts on the kinematic baseline, which are not present by the physics-based method. Our method aligns much better in the reference camera view than the kinematic baseline. This demonstrates the superior depth disambiguation afforded by physics-based losses.
Let me go a little bit further in time.
Estimation results
Here,
on
these
videos
are
in the wild.
pretty cool.
Here's a tennis serve. Notice the contact forces on liftoff and the large contact forces on touchdown. Here is a sprinting motion. Our corrected motions are of sufficient quality to be retargeted to realistic meshes. Method on the large-scale human 3.6M dataset and visualize our results in a combined scene. Note that all of these motions were obtained from pose estimation on videos only. These motion clips can be...
All right, I'm gonna stop there. It's, I guess, the first step, but at least I see this as a scalable direction, right? There's still a lot of problems to solve. The character is too occluded, it still doesn't work very well, and just improving the quality itself, but it's a promising direction. All right, awesome. So that kind of gives us a good 3D pose or animation estimator from just monocular videos, but we're still missing more stuff, right? So we know that human behavior and interactions are so diverse. There's so much richness into them, right? People bully each other, they rescue each other, they give speech, they cite conference, and the interactions are so just difficult to model, right? And for that purpose, we kind of looked into movies a couple of years ago, and where the thesis is that movies are like a trailer of your life, right? You see these characters in all sorts of different situations. They interact with each other. Their relationships evolve. They deteriorate. They maybe come back again. And we should be learning so many exciting things from movies. So we really went ahead and we labeled a full bunch of movies, 50 movies, with scene graphs. So we wanted to label the situation, so kind of the context of the interaction, bullying and the scene, like this is happening in a field road. We labeled all these different characters along with their heads, I guess, with the face tracks. All of their attributes. So for example, this character in the scene was compassionate or worried. All of their interactions. So for example, here would be hit, and maybe they used rocks to hit someone else, insult, and also relationships between different characters, which can end or they can start. So for example, an enemy, and we label that as well. And for most of these interactions, we even label when exactly in the video it happens. Okay, so exactly, precisely where some of this stuff happens in the video. And of course, we label the entire movie. So every single scene has its own scene graph, or we call it a movie graph for 50 movies. And now you can imagine, you can really do this holistic understanding here, right? We just did graph-based video retrieval, but you can also generate these graphs to have some sort of understanding of each particular situation, or you can have more high-level understanding of behavior, like predicting reasons why someone hit the other character and so on. But really what I wanted to kind of mention over here is this scene graph here with all this information is almost useful for a graphics engine. You almost know what you should be synthesizing. You know that there's a couple of characters over here. You know what they're doing to each other, right? And we maybe have animations for them already. You know exactly when they're happening. So you kind of have the timeline. So really what we're missing here is maybe objects, which you can get by running some detector, 3D information, which maybe you can do structure for motion, gives you some sort of a rough depth. And maybe you can go and annotate some additional spatial information. For example, what we did here. So this is collaboration with Mohammed. He hired a film student, and he kind of annotated in bird's eye view where the characters are looking, so their gaze, and where kind of roughly they are with respect to each other and respect to the camera. Camera here is this black circle over here. Okay, so imagine that you really have this kind of holistic understanding now with even 3D information, and we are really stuck at a point where a lot of this stuff is annotated. You can start doing really cool things, right? So you can take a clip like this, Forrest Gump clip, and you can turn it into animation. Not perfect because depth estimate is not going to be perfect. Not bad. Here's one more.
She said they was my magic shoes.
All right, Forrest. You can open your eyes now. Let's take a little walk around.
All right, so now I can imagine that if you're able to turn all movies into this kind of animations, then maybe we have everything we need, right, to generate this in the future. And this is really work in progress over here. Okay, so maybe just like the last 2 minutes, I'm gonna spend on, what might be a simulator 3.0, right? So here was breaking down into all sorts of different components, graphics-based components, right? From content to animation and so on. The real question is, can we just learn everything end to end? Can we learn to simulate, directly from video? And for certain domains such as driving, this data might be easy to get, right? You can quickly have cars driving around and basically recording from cameras. Okay, so we've been working in parallel to all these efforts on neural simulation, where really the idea is to kind of emulate a game engine, right? If you think of a game engine, it receives an action. So imagine a robot making an action or a user making an action. Then there's a game engine like Virtual Home that essentially renders the next frame. So we want to replace that game engine by a trainable neural net, right? That is going to observe all sorts of screenplay from a game and try to learn it, right? So at test time, we want to still have a user produce actions, but then a neural network is going to be painting all the frames. Okay, I'm not going to go into details. I don't have time, but here is a little video that shows this model in action. This was trained on Pac-Man game. Kind of observe the little tiny mistakes it's making. Like the world is not 100% consistent, but it has learned that food needs to disappear. And kind of they couldn't get rid of this ghost. The neural network kept pasting this ghost that follows Pac-Man. And the cool part of this is that we released this code a couple of months ago, and just a week ago, someone downloaded that code and trained it on Grand Theft Auto. I'll play
Welcome everybody to GAN Theft Auto. What you see here is me playing inside of a neural network's environment. This neural network was trained by watching a bot play Grand Theft Auto 5 on this particular stretch of highway, learning how to generate new frames from previous frames and player input. So every pixel you see here is generated from a neural network while I play. While generating the visuals or just improving them is interesting too, and there has been some interesting work lately with neural networks improving the visuals with Grand Theft Auto 5, in particular in attempts to make it look more photorealistic. This is something much more than that. The neural network in this case is the entire game. It's handling what happens when you press a key to turn left or right. There are no rules.
I'll stop it here. 550,000 views in a week. I wish my videos got so many views. And, just to kind of wrap up here, in parallel, we have been training GameGAN 2.0, I guess, the next version that's specifically targeting driving. So here I have an example on Carla without any actors. And then here on the right side is this DriveGAN, this new model, trying to imitate more complicated environments. I'm gonna skip the exact model. I'm just gonna show you this because it's quite cool. The fact that it has controllability. So look at the bottom, it has driving controls, but it also allows you to control the content you want to render. So here saying is pasting, I want a car here, and I want to control this kind of weather. So it can change the weather and different things as well. I have more stuff, but I think I need to finish, so I'll stop here. Thank you. Are you still there?
Yeah, thanks so much for your nice presentation. Yeah, we're still here.
All right.
Yeah, so first let's see if there is any question. No one? Okay, no question from YouTube. I think people have gone to sleep now here. And also on Zoom, we don't have any questions yet.
Oh my God, everyone is gone. So maybe we should finish here and I can also have a weekend.
Yes, I had a question here. So I was curious, like this kind of differential graphics and like physics-based rendering. So all these setups that you shared were mostly results often using differential graphics, right? So, but physics-based rendering, which is using like Blender or things, you can of course obtain the scene parameters and simulate a really nice 3D scene or like, so those kind of things I am seeing nowadays, like we have TensorFlow, differential graphics and things like, we have that. So do you also do, when you do this kind of experiments, you always do physics based and also differential graphics, or what are the different kinds of approaches generally you go with? Like one could be like, I don't know, could you say a bit on this?
Differential graphics, I think it's a very exciting direction. I think it's not as mature yet, right? So typically what you do is make these renderers differentiable, but that is somehow constrained in a sense that it can only handle like one object, or if it's handling a more complicated scene, it's really good initialization of how many objects and so on. So I would say that just going from images into a complete 3D scene is, first of all, it's an ill-posed problem, right? So that needs to be trainable. But second of all, is not like something that's ready today. I think it's hard. And I showed one example where we're using differentiable graphics to train like image to 3D. But just to record a video of me driving on the road and hope that this is going to translate into a beautiful 3D scene with all the assets, I think that we're still very far away from there, right? So, but I think, marrying this graphics-based renderer, which requires a lot of manual work, and then data-driven simulation is the future, right? So I think, work on combining the two in differentiable ways is the way to go.
Yeah, great. Thanks. It's like something I'm also looking at. So I would connect with you sometime, some other time. Thanks.
Yeah, sure.
Yeah.
Thank you.
Can I also ask a quick question? We have time, right?
Yeah. Cool.
Okay, thank you. Thank you for the great talk. One thing that was very many interesting things. One of the aspects that was quite interesting to me was the physics-based human motion synthesis and simulation, and in general, like pose estimation. And one of the problems that you brought up, you mentioned, was especially if you run pose estimators frame by frame on a video, you're going to have a very inconsistent and very jittery estimation. What is your approach besides what you've explained today, using the physics-based models for building proper pose estimation models for from videos? I'm coming from a, say, healthcare related application in which pose data is quite important for you, and being able to remove the noise and the jitters can be very helpful in the downstream application. So how do you see these physics-based models can be applied to solve those problems in video-based pose estimations?
Yeah. Like I said, I think it's just an amazing prior to have, right? We know that human motion is physically plausible, and we know the laws of physics. And if that physics is differentiable, then great, we can train everything end to end and have these constraints that we know are there in reality, right? But it's hard to just impose on pose estimation, particularly if it's frame by frame. So I think it's a great direction to go, right? Because then we can maybe avoid to have all these supervised data, and we have like a very nice prior to denoise our 3D trajectories.
Right.
I'm not sure exactly
The problem is that the physics is still again in a single image frame. So
oh no. The physics is on our entire trajectory. So essentially, you're chopping your video into frames. You're getting 3D pose estimates in each frame, and then optimization goes over the entire trajectory. So you want to denoise all those 3D pose estimates such that you have physics loss as well as some log likelihood of the poses.
Thank you.
Mm-hmm.
Okay, thank you, Sandra, for your great talk, and also it was a nice.
Thanks for inviting me. Bye, guys.
Sure. Bye. Have a nice weekend. So our next speaker is Christine Goman from the University of Texas, and I think she's with us. So,
yes. Hello. Let me share my screen.
Yeah. Sure.
Okay. Great. Well, hi, everybody. Thanks to the organizers for having me here. This talk is going to be about first-person video. And so this is video captured from a wearable camera. And I'm going to focus on some of our recent work trying to look at first-person video as a way to understand interactions between people in the world and agents in the world. Okay, so let me jump right in with the motivation that's kind of from afar, just kind of what brings us to this kind of video data. So we know and love so many influential data sets like the ones I'm showing here with massive collections of images and video from the internet in almost every instance, where we get to learn about and test ourselves on what's really the web perceptual experience. And these photos and videos are challenging in their own right, but they also have certain special properties, which are that they're taken by people, right? So these are intelligently captured visual streams or visual photos, and they're also disembodied. So by the time they reach our data sets, they're kind of out of the physical context of what those moments were about. And that's how we, in our methods, receive them. So pros and cons to each of these things, in fact, but it does make us draw a contrast between what's required if we start thinking about egocentric video, where the first person perceptual experience is not curated like those photos or videos. It's every moment in time unfolding in front of a person who is actually driving what we see based on their own actions, their attention, and what they're trying to accomplish. And you'll notice that that can often mean, for human egocentric video, high object person interaction or environment person interaction. So kind of two different animals and requiring, as we'll see, kind of different techniques and also different opportunities of what we can do, what we can learn from long form egocentric video. And that's what this talk is kind of headed towards, moving us in this research from the disembodied web photo regime that is important for certain applications, but not the whole story, and allowing us to move into challenges at the brink of action, and perception. So thinking about visual learning in the context of agents that can act and choose actions, have their attention, and even perceive with multisensory data. We're good agent examples of that, we humans, including children, but also the platforms that we might want to address, like in augmented reality with wearable cameras, or with mobile robots or manipulating robots, where the egocentric view is also central. These are the kind of things that we need to tackle or understand this shift in order to enable those applications. Okay, so that's kind of the big picture motivation for much of the work in my group right now. And this talk is going to zero in on certain parts of it, again, where we're thinking about first-person perception, specifically towards interaction-based learning. And I have actually 3 segments to this talk. The first one, I want to look at visual affordances. So this will be about anticipating what can a person or agent do where, in a space or with an object. And after talking about those kind of methods, then I want to give you examples from our work where we're trying to translate what agents learn about affordances into action. So being able to understand a space, understand objects such that they can be more easily used. And then the final briefer part of this talk, I'll shift to talking about data. And I'll give you a model that's trying to be smart about egocentric video data together with traditional third-person video data. And I'll talk about a large-scale data effort that's work by not just us, but a large consortium of universities. Okay, so that's the format for the remainder of the talk, and I'm going to start right now with affordances. And when we talk about affordances, we mean moving from pure recognition or even mapping to functional understanding. So looking at a 3D space like this, we would do smart computer vision type processing. We could do things like map it, run SLAM, or perform recognition of objects and scenes. But the layer that we wish to pay attention to here is to think about mapping a space by its functionality. Okay, so being able to look at a space and understand where different behaviors or actions are possible. So this would allow us to move from naming to using. And I hope you can see already, this is relevant for this goal I'm talking about of closing or bringing together action and perception. So where does egocentric video come in? Well, we're going to use it as a means to learn those functions. And ego video, like another sample I'm showing here, is quite rich for this because it's both a persistent 3D space. If you talk about a long egocentric video, uncurated over course of not just maybe minutes, but hours or even later days, then you're getting a persistent 3D space in which a person does a variety of actions. So we can start looking at ego video to reveal for us, what a person might do next, what areas in an environment are key for activities, which ones, and how can a space be used, whether it's happening now or has potential to happen like an affordance. Okay, so we looked at egocentric video as a special cue for trying to extract that kind of information. And the first technical idea that I want to present is our map of an environment called ego topo. So topo for topological. So the idea is to think of video not as a stack of frames or not as a 3D volume on which to do convolution, but something more structured. And so the ego topo model is a structured video representation in which we take the streaming egocentric video and organize it into a graph in which each node of the graph is consistent, coherent in terms of the activity a person could do there and or the objects with which they would interact there. So if you think of a kitchen as a larger space, then an ego topo graph would break that kitchen into different stations where different kinds of activities and objects get used. Okay, so each node is consistent in activity, and then the nodes are going to be linked based on their temporal proximity of how people visit the different spaces in that video. Okay, so this places us somewhere between a metric understanding of the space and a pure video understanding of the space, which would just look at pixels and frames, to something that's more structured. And I'm going to show you how that's valuable in just a moment. So how do we construct these graphs, or what will it give for us? It's going to allow us to two things: reason about first-person behavior. So we could pick up through these graph encodings how visiting the fridge often led to pulling out something, taking it to the cutting board or the sink in some particular sequence. It also will allow us to reason about environment affordances, like again, what can I do where? Where am I more likely to cut an onion versus pour salt? So let me say a bit more about the approach. So we're after a topological graph. The first thing we do is train a localization network. This is going to be a network that's trying to look at frames of video and decide if they belong together in the same node or not. And we use a mix of properties from which to learn this network. So one is fairly traditional, are they visually similar? Are they consistent in their homography such that they're geometrically stable from view to view? But we also use some properties from the video, like the temporal proximity and time, as well as whether the frames have similar action or object distribution. And so those would be things that would lead to frames being linked in a node, and vice versa, visually dissimilar or separated in time would be not linked. So now taking the video in sequence, we'll just look frame by frame and create new nodes as necessary according to that localization network. So if it's different from all existing nodes, it's new. If it's similar, it gets added as a visit to that node. Okay, so stream through the video, start assigning frames and clips to nodes. And then when you're done, you have a graph like the one emerging on the left for this environment going in fast forward on the right, where again, each node is consistent in the activity or objects used. And this whole format or map of the space is now exactly driven by human action. And this is special, right? In terms of organizing the space by how a person uses it. Okay, I'm going to show you then next what that'll do for us. I want to highlight two tasks. So the first one's anticipation. Okay, so far what we have is an encoding of the video. Now let's use it for anticipation. Anticipation means basically future recognition. So if I've observed so much of the video, say some percentage of it, can I predict all the likely actions that could happen next? And you could imagine sweeping through fractions of videos you've observed versus fraction of videos you need to anticipate. Now, this is a task that's receiving increasing attention in the literature. What's special or hopefully interesting about the way we're posing it here is it's long-term anticipation. So rather than say, anticipate what's happening in the next 1 second, we'll anticipate future actions in these long ego videos that could span anywhere from 5 to 45 minutes. Now, I think that the structure of ego topo is important to try and tackle a long-term task like this, because to really answer this question of what are the things that are probably going to happen in the next 5 minutes or more, we want to have an organized, structured record of the things that have happened before that could lead to that future. So using ego topo, let's just add a little bit here where we'll have a node level representation for each of the nodes, pooling over all the visits to that node for that entire video. And then we'll use a graph convolutional neural network to summarize this entire encoding in order to classify, anticipate the future actions. So what you're training this thing for from this GCN is to label the likely future actions, you know, a probability over each of the possible actions. Okay, so when we do this anticipation task on 2 data sets, EPIC, which is a large kitchen ego video data set, and the Georgia Tech data set, which is shown on the right, we're seeing pretty encouraging results where the accuracy for the anticipation task is enhanced by this structured encoding. And this is true both against some simpler video models that are treating the video as pure video, you know, stacks of frames or 3D convolutions, as well as some methods that do more complex temporal aggregation with a bit more structure. Okay, so this model can look at video and anticipate what's going to happen next. And it's very much set up to do this, right? Because it's learning from how people use the space. Now, the second task I wanted to show you using ego topo is for environment affordances, where we want to be able to predict everything that's possible in a given space. Now, the challenge is if you have some training video, it'll be labeled and observable for certain actions. Like here we see turn on the stove, even though there's a small array of other actions that are certainly possible here. So if you're training a model that's anticipating affordance, you want all these labels preserved, right? So you'd like to be able to predict all of these, even if in a particular training video, it's just the one. So we can show how ego topo and its structure helps us here for learning affordance. And the main idea is to think of these graphs one by one across environments and then link them from environment to environment. So an environment is a kitchen, say. So I have one video graph ego topo for this kitchen, and I have another for some other kitchen. So what we do is try to link nodes that share functionality between one physical space and another. And we can do that by looking at the object and activity distributions observed within those nodes. Now, why you do this? Well, now we can inherit labels or propagate labels from the one space to another, such that we can expand the set of labels that are available to train an affordance-based model. Okay, so now you have video clips that have inferred label sets based on connectivity from space to space that's determined based on human use of the spaces, so that we can share these labels. And now you have an enhanced set of labels to train the affordance model. So when we do that, now the second task of affordance prediction means taking video clips in and inferring with what chance would I expect to see, even though I don't see it now, would I expect to see any given action. And so here are a couple small examples for a subset of the available actions. Like on the right, each of these bubbles is a clip of video, and from it, we would anticipate how likely filling the cup versus pouring the water or anything else is to happen there. And the key with these models is you can make these predictions even for an unfamiliar space, right? So by definition, the new video coming in is a space we haven't encountered before, but we're able to look at it through the lens of how do people use these kinds of spaces to anticipate what would be possible where. So again, evaluating this on the data sets I showed you before, but now for affordance prediction, we see some encouraging results. Here in this case, we're interested in, well, what would baselines do if they propagated labels like we do, but instead did it in a purely 3D manner based on shared location in the space or based on visual similarity of the space. And compared to both of those, we see more robust affordance prediction using the egotopo graph. Okay, so egotopo is about predicting about affordances, and it's a way to encode video that goes beyond stacks of frames or 3D convolutions to think of the space as organized by people's travel patterns and activity or interaction with the space. Now let us continue on this thread of affordance, but I'm going to jump down a level in granularity from environments to objects. So an environment, it's, as you just saw, it's saying, what could I do in these spaces as I approach them? With objects, it's very similar, but now we're saying, where would I physically touch, or how would I touch an object on what region in order to do a certain action, like adjust the lamp versus toggle the lamp. And here we've developed a model called interaction hotspots that will use video anticipation kind of ideas to localize regions in the frame that appear to afford an action. So basically we've trained an action recognition pipeline, but then we train it to map to those likely actions from images or frames of the object at rest, meaning when no one's interacting with it. And so what these are some results using that interaction hotspot model. You can see now that this bowl looks mixable, although the person's not yet mixing it. Same with this pan that appears just behind it. So these color codings are for different afforded actions, like you see listed at the bottom. The ones I'm listing are just the ones that are most frequently happening. So these objects, look washable, including the knife sitting to the left, even though no one's washing it just yet. Here are these jars to the right look openable. That's the cyan. The door also looks openable. And so the system is learning from video directly by watching people do things with objects, how to anticipate for new objects that aren't yet in use, how, which of these verbs would they likely afford and where. Okay, and this is different than what you get if you run state-of-the-art saliency like I'm showing on the left in yellow, because saliency will find important looking parts of the frame, but ours will, with this interaction hotspot, will code what's being seen according to which actions are possible there. Okay, and so this approach, interaction hotspots, we've certainly evaluated for how good is it at finding these correct spatial regions where actions are possible. And we are comparing both to other methods that are supervised weakly in a variety of different ways, saliency, eye gaze, other things, as well as strongly supervised methods that do more traditional recognition pipelines, saying here are parts of a pot, for example, that are mixable, hand labeled. And what you see is that the approach we propose is coming in much more accurate than any of the weakly supervised methods, and even starting to compete with those hand supervised traditional methods. All right, so using these interaction hotspots, we'll get to an agent use in just a minute, but I wanted to come back to the recognition challenge itself and how it might be affected by us having models that understand function or understand interaction. And this is a very preliminary result that I'll share, but what it is to look at standard object classification. So you've got these images, you want to know which object's in there. And if you train an off-the-shelf reasonable model. You'll get some of them very well, like the ones on the left, which are refrigerators, but you'll miss others like those on the right that are just unusual for their viewpoint or the context of the object. Okay, so these are refrigerators, but we missed it with this baseline. However, our idea was to try to put into practice what we know, or what cognitive scientists know about how people understand new objects, even with little experience with them. And part of our understanding is built on being able to look at an object and think about how it would be used, which is exactly what interaction hotspots are attempting to reveal. So what we did is code the images, not just by their ResNet features, but also by these interaction hotspots. For example, for the fridge, holdable and openable were two prominent affordance regions. So we're coding in that feature space as well, and then training low shot recognition systems. Low shot meaning you have very few. Here on the left, as few as 5 samples labeled for each category. And what this initial result shows is that by anticipating how the object would be used as part of the representation, not only will it let us do some action, as I'm about to say in a minute, but it also just helps basic recognition because we have this encoding that reveals function that's agreeable or consistent across the instances, even when the more superficial visual changes are less consistent. So I think this is an exciting result, like saying how understanding of function and affordance actually comes back to help even classic recognition. Okay, so far I've talked about affordance. Next, I want to move into action. I'll briefly show you how we're training robotic agents right now in simulation to be able to leverage those visual affordance to do things. And then again, at the end of the talk, I'll talk about data. So 2 examples I'm going to show you briefly here. One is a dexterous robot hand. So this means it's a multi-fingered robot end effector, 24 degrees of freedom. And it's, to some extent sharing morphology with the human hand. And it's going to be dexterous because it has all this kind of fine-grained control, if we can learn policies to let it be intelligent about how it moves its own hand. And our idea here is to provide a prior to this agent to learn where to grasp at objects based on their visual affordance. So human-made objects are often made for human hands. And this is a good alignment point because both we've got the robot with the human-like hand and we've got object affordances that we're learning from things like I showed you just before, from images and video, so that we can have agents that look at objects and expect where a person would, for example, start to grasp them. So we have, in this case, a CNN model that will look at new objects in the robot's point of view, anticipate the regions that are good for grasping, and then bias the behavior of that agent while it's training a grasping policy to be using those regions. Okay, so the intent in doing this is to allow faster learning. So rather than bumbling around in a reinforcement learning manner for any place to grab this object, we could go right to the places that are possibly useful to grasp, better grasping as a result, and we also want to enable generalization in new objects. So what's important here is that rather than learn from a demonstration of like, this is how you grasp this particular object, we're learning a generalizable visual model that can see a new object with at least partially different properties and still predict where this affordance region would lie. Okay, so let me show you our agent in action. I've only said really in words, how this agent works. It's a deep reinforcement learning loop. And so there's a tight closed loop between the perception and action of this agent, where it's choosing how to control each of these joint positions. One moment. I've got my computer vision apprentice with me today for this talk, and he'll weigh in as he chooses, as you see. So our model is graph, which is grasp affordances on the bottom right. And again, it's this reinforcement learning loop. And so it's going to just prefer and reward actions that not only lift something off the table, but use regions that are affordance predictions from the visual stream. And I'm comparing this against some standard RL methods, ones that don't have that prior or have a different prior, like the center of mass, as well as a learning from demonstration approach that blends in imitation learning based on human demos with a teleoperated hand in order to learn, also try to learn faster. So let's just play some reels for these agents, again, ours is in the bottom right, trying to be able to grasp different objects that it encounter. And you can see that the agents that have lack the prior on the top are doing a lot more bumbling around and not able to grasp these objects. Those in the bottom that have this edge of human intelligence, priming them, do better. And in fact, ours in the bottom right is doing good, not only grasping to get the object up, but also a more stable grasp that survives these forces applied at the end of these episodes. Okay. So what we saw then is that we're learning a better policy just through my qualitative examples, and also we're learning faster. So the graph approach is this blue curve, the others are those without the prior. You can see that we can reach the same success rate with a third of the amount of training time. And why is this? It means that the agent is able to leverage all this vicarious experience from the human actions found in video or images in order to decide where to do its most fruitful actions with less amount of exploration in the joint space. Okay, so the other example with agent action I wanted to show you is to do tasks that require not just manipulating one object, but also moving about in the 3D space. So these are agents that could ultimately help us have policies that do tasks like, hey, can you bring me a cup of tea? This means you need to know where to move in the space, what objects to touch, how to use them. And there's a lot of great work happening to try and do this, including with reinforcement learning, to learn behaviors that will answer one such task from the bottom up. Now, a downside of what's usually happening today is that they're specialized, right? So you would need a policy to bring you tea. You'd need another policy to dry your clothes, right, in one of these environments. And the objects that are relevant would change. The actions you need to execute would be, of course, different. So we'd like to get away from this kind of task-specific interactions towards some baseline ability to explore a space for how to use objects and how to use the environment in order to learn special purpose behavior more quickly and with less, again, just like the example I showed you, with less physical interaction with the environment. And here too, we've been exploring how affordances can play an important role. So if you have an agent that's just figuring out what's its action space even do, what happens if I try to, execute my pickup action, and where do I need to be where it's going to succeed? Think of an agent just learning all of this from the bottom up. Well, if that agent has these visual affordance models, then it can look at the space in terms of this prior and only attempt, or at least prefer to attempt, actions where they're likely to succeed given the visual affordance. Okay, so not saying slice when in front of a trash can because the affordance suggests that's not likely, but saying slice when you're in front of a loaf of bread, for example. Now those affordances would be can be learned from video, as I was showing you, can also be learned and built up through the agent's own experience in new environments. So to then, bring this idea to life, what we did is build a reinforcement learning policy that's rewarding finding new successful actions in a new space and using as input not just the egocentric RGB stream, but also the affordance predictions that are visual, based on the visual input. Okay, so we can use both those together to more quickly find the places where actions are successful. And keep in mind, this is an exploration policy. So often when we say exploration in 3D spaces, we're thinking more navigation, purely, how do I get around and map it? Here it's an interaction exploration because we're saying get to know where you can do what kind of action. So when I play this video, we're going to see an example where on the left, we have the egocentric view of the agent. And then again, what should be familiar now, these color codings according to affordance that it predicts. And then on the right, you're going to see the full trajectory of the agent that from like a bird's eye view of where it's choosing to go. When you see a yellow dot on the right, the agent has tried an action that was successful. Sorry, green dot tried an action that was successful, yellow means unsuccessful. And on the left, you're seeing the reward tick up as the agent finds more and more things that are possible to do in this new space. right? And so it's realizing that, you know, countertops look like something where you could place things. And the coffee maker was toggleable. Some of these doors were openable, and so on. And so it's learning to find the places where these actions might succeed. And so it's not wasting actions, just doing things that aren't going to work out. And that's what a good interaction exploration agent should do. Huh? I don't know, maybe stay for a second. So this agent is good if more green dots occur than yellow dots, which is what's happening here. What I'm not showing you are baseline approaches that do other forms of exploration, but their output is to have a lot more yellow dots where it's, you know, just attempting things that just don't pan out because it doesn't understand the affordance of the space. Okay, so that's my second example I wanted to show of translating affordance to action in terms of concretely where it helps us. We've looked at several downstream tasks. So remember, we were after a task agnostic exploration policy to prepare for new tasks. And so here we are executing 4 new tasks: retrieve, store, wash, heat, where the agent needs to, for example, find something and wash it. Then what we're getting is better success rates. So faster learning, but also better success rates in those final tasks, having pre-trained this generic exploration policy. All right, so what I've shown you then are affordances coming from visual data, such affordance models that influence what an agent does so that it can learn faster, learn better policies to do things like grab objects off of tables or work its way through physical spaces to achieve different tasks. And the final part of my talk, I wanted to show you one more idea from our work for on the data side for building egocentric video models. And then a big team effort for data collection that's about to be released later this summer. Okay. So let me talk about the data motivated by this contrast. So I've already been showing you egocentric video clips and how different they are. Here's 2 examples. Third person on the left, another word for that is exocentric, and first person on the right. And you can see that even though these are very similar settings, when we see first person data, the viewpoint is different. That's the viewpoint difference from third to first person, but also the content and the purpose of capture is even different. So these are really different distributions of data. And the reality is that the amount of data we have as researchers at our fingertips for third person is much greater, certainly the amount of labeled data compared to anything we have in the first person realm. So they also differ in terms of practical scale and diversity of the data. For example, your average first person video data set, the large ones are very kitchen focused, or at least indoor and in the home focused. And that's not true for the third person data. So what do you do? Well, if you're training a video model and you want it to succeed on egocentric data, you don't necessarily want to turn a blind eye to existing third person data. And so people don't. So you can do things like pre-train from third person data because it's rich, because it's labeled, such that you have better video features, and then try to fine tune to ego video, which is a totally reasonable thing to do. People are finding though it doesn't always work so well, right? In fact, the third person can steer astray the encoder for what's going to be ultimately a first person video task, because there is a large domain mismatch for the reasons I just mentioned. So here's our idea, and this is work appearing at the main conference this year called EgoExo. We would like to leverage the third person data, but leverage it in a way that appreciates the egocentric specific properties. So rather than solely do traditional pre-training, say targeting the actions labeled in the third person data, we're going to add a series of 3 auxiliary egocentric tasks. And these will be tasks that try to elicit the features from the third person data that are ego-like, let's say. And there's 3 of these tasks. One is egocentric likelihood, where we're going to say that the features we learn from these third person videos ought to make it predictable, or let it remain predictable whether a video is like egocentric video or not. So we train a classifier for that and then use a distillation kind of loss to say this should be predictable. Secondly, we know that objects are forefront for ego video. So we'll say that The representation from we're learning here should also satisfy preservation of object labels being predictable. And finally, similarly, hand-object interaction regions. So we'll target in a distillation kind of loss again, that from the third-person video, we ought to be able to predict hands and objects. Okay, so this is the mechanism for ego-exo. Bring along the third-person data, but let's extract egocentric-like properties that are latent in those features and make sure they get preserved when we learn these pre-trained features. And so this lets you enjoy the fact that there is third-person data, it's labeled, it could be useful, but also embed egocentric signals that are specific for first-person data. And we've trained and tested on a variety of the available data sets. So we have state-of-the-art results for Charade's Ego, which is an egocentric data set in a variety of household scenarios, as well as very strong results, apples to apples, with other methods on EPIC 100, which is the largest existing first-person data set. Okay, so ego-exo, you can think of this as an off-the-shelf pre-trained model then that might help you if you're looking at egocentric video analysis tasks. Great. All right, so the very final thing in my talk today is a bit of a teaser, a short ad really, to draw your attention to a new data set that's going to be coming out late this summer. And it's called Ego4D. So Ego4D is the effort, not just of my group, but of 13 different universities, as well as Facebook AI, coming together in a consortium to provide what we expect to be the, what will be the unprecedented in scale first-person video data set from in the wild capture of people doing all sorts of daily life activities. And so this is an effort that's been going on for more than a year and a half between all these 13 universities and FAIR to build the data set and to also, hopefully use it to catalyze research in first-person video. Actually, these numbers keep going up. So there's more than 2,600 hours of content that will be in the first release. That's in contrast to 100 hours in the largest available public data set. This video comes from hundreds of locations. Some of them have 3D scans as well. There's, at this point, more than 700 unique camera wearers, and they're not graduate students. So these are people recruited from the community of different backgrounds, ages, etc., to wear the cameras. And they're doing daily life activity in an unscripted manner. And along with this research effort, or the data effort, the consortium has established a set of benchmark challenges that accompany the data that we hope will, prompt some new bits of research in egocentric video, although we expect there'll be even more that the data can support. So this project began the collection part of it in February 2020, and the release of the data in full annotated form is going to be late this summer. So I mentioned this is a consortium effort, and here you have all the team members. And what I'm drawing attention to is how strong this team is in terms of expertise. So we have leading PIs across video, prior data set efforts, and egocentric video specifically, as well as how geographically diverse it is. So with this team fielding cameras locally in each of these places, Ego4D will be a data set that gives you a glimpse of everyday activity from the first person perspective in many parts of the world. So 13 universities, 9 different countries, 5 different continents. And here's just one such glimpse. Here we'll go through a few short excerpts from what are longer ego videos in this data set. And you'll see that this is both indoor and outdoor. It's unscripted. This is people doing everyday things, whether it's at the workplace, or whether it's social events, or whether it's solitary activities at home, like cooking and cleaning and others. And it's unscripted on purpose because we'd like these videos to capture things that will assist in agent-based learning, like I was just talking about today, as well as augmented reality, where people would wear cameras and have intelligent systems that can look at the history of their video or what they're seeing now. The video is also rich with hand-object interactions, like some of which you're seeing here. Okay, and with this data, we're providing heavy-duty annotation, so both narrations, which are text descriptions of every single action that's happening in these videos at the rate of 18 sentences per minute for 2,600 hours of such content, as well as labels that are targeted to a set of benchmark tasks. And the benchmark tasks, I'm going to give you like the one slide summary of what they are that we're putting forth with the data. There's 5 of them. One, this first set of 3 kind of goes from the past to the present to the future. So looking at the past, we have a benchmark task that says, given an egocentric video, answer a question about where something is or what the state of an object is. And a great example is, asking where are my keys, and having a system that can go back and find them in the video or even in the 3D environment. Moving to the present, we have a benchmark about hands and objects or object state changes, where we want to analyze what's the person doing now, how are they doing it? And moving to the future, we treat the forecasting task. So this one I've already touched on earlier in the talk in terms of anticipation. And the question is, what will I do next? Where will I go? Where will my hands go? What objects will I use? The final 2 benchmarks are very people-oriented. One looks at a multimodal view of the video to do diarization. So who said what when? And social is a benchmark that builds on that to capture further who's paying attention to whom, or who am I speaking to. Now, the Ego4D benchmarks that this team has devised are really capturing 3 things. So first-person interaction with places, with objects, and with other people. Okay, and as I've already said, this data is yours for the using come late summer, both the data, the video, the annotations, and the benchmarks. All right, so I'm going to stop here. This talk was about learning with first-person video and doing so for affordances and then agent action. And then the last part of this talk was thinking more about the video assets and how to work with first and third-person video and towards this massive consortium effort for Ego4D. So the work I highlighted from our own team is by the folks you see listed here: Tushar, Yang, Christoph, Priyanka, and Bo. And thanks for your attention. Glad to have any comments or questions.
Okay, thanks so much for your presentation. Yeah. So, is there any questions in the Zoom? Anyone from the Zoom has any questions?
So I have one question here. So Kristen, I was curious, we are also having these issues with given this super large scale data set. So I think this Ego4D is also a video data set. So how are you guys going to release this large scale data sets and with so wide range of labels and things? So how would from academic perspective, how can we think about using it? I always find this thing hard, the large scale data sets, we also have the same issue. So do you have any thoughts on that? Because I feel that there are a few questions I often come across this thing.
Yeah. So you're concerned about, it's large data, which we always like, but then how to practically access it, including, if you're not talking about immense computational resources or things like that, right? Yeah. So we're definitely mindful of this. I mean, there's a few, ways to look at this one that we're pursuing. So one is that for these benchmarks, there is 2,600 hours total, but each benchmark will be labeled thoroughly for some 100 to 200 hours. So, I mean, that's still very large, but, you can be most interested in one benchmark and pursue just that subset of the data. Another thing we're doing is providing pre-computed features, which, people have done before with these large data sets to at least assist entry into using the data before, without having to do your own 3D conf features, from the get-go. So we hope that will help. The other thing that we, is in the works is to think about kind of mini set style pieces of these challenges so that, there could be fair and kind of sanctioned ways to use the data, whether you're talking big resources to access it or much smaller ones. And so that's another way we think might help to increase or allow use across, different places, including academic labs or smaller labs and things like that.
Yeah. Okay. Yeah. This is something. I understand. Yes. So what else? Right. Appreciate it. Thanks. Yeah.
Sure.
Okay. So we don't have any questions from our YouTube channel. And okay, Dima has a question. Yeah, you can ask your question.
Just a comment. I admire Kristen's way of doing things, not only by having her intern on board, but the structure of the talk and the fact that there is a very clear vision. So I'd like to know what's next, like a little bit of more of where do you see the ego topo, the ego exo going next?
Yeah. Well, I think that, we've clearly only scratched the surface of translating to action. And, we're also aware, I'm coming at this and my students from the computer vision side, but getting, more and more interested to understand how we can inform robotics kind of applications. And so, that second bullet of the talk is certainly just a starting point. And so I think that, for example, in some cases where we'd like to be able to do sim to real kind of exploration, and some results I didn't present here today, but are looking at how to take epic video, which Dima, you know very well, of course, to be able to train to agents, and other works we're trying to go from the simulated agents to the real agent behavior. That's a tall order and very new for us. So I think that's one thing that's next. I think another is, I'm like you, I think I'm very excited about the suite of benchmarks attached to Ego4D. And I should say to everyone, Dima is one of our PIs for Ego4D, along with other 12 universities. So, those tasks are inspiring to me, including the episodic memory, which I think is special for new work in terms of linking persistent 3D spaces to action and dynamic video. Like, it calls for that, right? It's a good test bed for it. So that would be another good example of what I think is next to try and pursue in this line of the work for our group.
Thank you.
Okay. Thank you again for your amazing talk and for your effort. And yeah, thanks for being with us.
Yes, thank you for having me.
Sure. So it is the final moments of our workshop. So I'm just going to use this moment to conclude, and also I'm going to introduce our channel for our challenge for our data set. So let me just share my screen, and just a moment, sorry. Okay. Yeah. Yes, as you may be familiar with our dataset, holistic video understanding dataset. It has about 500,000 stream video.
Mohsen, your screen is frozen.
Yeah. My Zoom is crashed. Just a can you hear me?
Yeah, sure.
Sorry, my Zoom crashed, so I don't know.
It's all right. So maybe we can just simply thank our speakers again, and thanks for having us. Thanks for being part of the workshop. And
yeah, thanks everybody for being with us. I just wanted to let you know that our challenge website is online, and the participants who participate and will submit to the leaderboard, we will announce the name of the winners in our ICCV 2021 tutorial. And for downloading the data, you can follow the instruction, our GitHub repository. You will just write or just fill the form, and we will send you an email. If you want, you can access the whole data. You can also retrieve the data from the YouTube as you wish. And also for the tested, we have not released the labels. If you want to participate in the challenge, or if you want to know your the accuracy of your models on the test set, you can upload your results on our challenge website, and then you will get the feedback. And again, thanks everybody for being with us. And I think even the CVPR is also over, and we are at the final moments of our workshop. If anybody has any comments or questions or whatever, I think everybody is like just waiting for starting their weekends. So I'm not going to ruin your weekend. It's almost 1 a.m. here in Germany. And have a nice weekend, and thanks for being with us.
Thanks for organizing.
Take care then. See you guys.
Bye.